Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring some of the most fascinating facts about our cosmos. The story of the universe is much more than just the stars and planets you see at night. There is a deep and mysterious architecture behind them that behaves in ways that defy the imagination. Space-time bends, distances stretch, and light from the Big Bang itself is still on its ancient journey into the unknown. Cosmology is the study of the universe on its largest scales. It looks at how space expands, how matter is arranged, and how the universe has changed over immense stretches of time. It finds patterns written into the motion of galaxies and studies the hidden structure of space itself. Even when much of the cosmos cannot be seen directly, it leaves evidence behind. Those quiet signals allow us to trace how everything fits together, from the first moments to the vast expanse we observe today. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your body soften, allow your eyes to grow heavy, and as your mind begins to settle, allow the day to gently fade away as we travel through the cosmos together. Let's begin. There are more stars in the universe than there are grains of sand on our entire planet. When you look up at the night sky, the countless stars twinkling seem almost endless. But the reality is even more astounding. The total number of stars in the universe surpasses every grain of sand on all the beaches of Earth combined. Each star is a blazing sphere of plasma, some much larger or smaller than our Sun, shining across unimaginable distances. This staggering abundance speaks to the vastness and complexity of the cosmos, where every star could host its own planetary system. It's a humbling thought that reminds us how incredibly vast and rich the universe truly is, a magnificent ocean of light and energy stretching beyond imagination. The observable universe stretches 93 billion light-years wide, but there might be much more beyond what we can see. Our cosmic horizon limits what we can observe to roughly 93 billion light-years across. This observable universe contains all the galaxies, stars, and matter whose light has had time to reach us since the Big Bang. Yet, this is only a fraction of what might actually exist. Beyond this visible boundary, space likely continues endlessly, or even infinitely, filled with countless more galaxies and mysteries. Because light from those distant realms hasn't had time to arrive yet, they remain forever out of reach, hidden in darkness and silence. This boundary of sight is not a physical edge, but a reminder of the limits of human observation and the vast unknown still waiting to be explored. Space itself is expanding, carrying galaxies farther apart every moment. It's not just galaxies moving through space, they're being carried apart by the expansion of space itself. This means the fabric of the universe is stretching, increasing the distances between galaxies over time. Imagine dots on the surface of a balloon inflating as the balloon grows. The dots move farther from each other, not because they are moving on their own, but because the surface itself is expanding. This cosmic expansion affects the entire universe, influencing everything from how light travels to the future fate of the cosmos. It's a slow but relentless growth, shaping the grand architecture of space and time. The Big Bang wasn't actually an explosion. It was the creation and expansion of space-time itself. Often imagined as a gigantic explosion in space, the Big Bang was far more profound. It was the moment space and time themselves came into existence. Before this event, there was no space to move through, and no time to pass. Suddenly, from a state of unimaginable density and heat, space began to expand, and time started ticking, setting in motion the creation of everything we know. This initial expansion wasn't a blast within an existing space, but the rapid growth of all of space itself. It's a concept that stretches our understanding and reminds us how unique and mysterious the universe's origins truly are. The early universe may have been filled with light so dense it behaved like matter. In the very first instance after the Big Bang, the universe was not dark, and it was not empty. Instead, it was radiant. Photons, the particles of light, were packed so closely together that they could not move freely. They scattered constantly, colliding with particles of matter and with each other. This dense ocean of light created pressure, almost as if light itself were a physical substance with weight and texture. Over time, as the cosmos expanded and cooled, photons slipped free, streaming into space as the cosmic microwave background that still surrounds us today. That faint glow is the stretched-out remnant of a universe once so bright it behaved like matter itself. Some regions of the cosmos may still be inflating, forever cut off from us. Cosmic inflation is the idea that, in its first fraction of a second, the universe expanded faster than the speed of light. According to some models, inflation never stopped everywhere at once. Instead, it may continue eternally in distant pockets, creating new regions of spacetime forever. These inflating domains would expand so quickly that no light could ever cross the gulf between them and us. In this picture, our universe is just one bubble among countless others, each sealed off by the runaway expansion of space. We will never see those regions, never touch them, and yet they might exist, endlessly budding into the void. To think that our entire observable cosmos could be just one finite blossom on an infinite tree is both humbling and strangely beautiful. Black holes could carry imprints of the universe's first moments. Black holes are usually thought of as the graves of stars, but some might be older than any star. Cosmologists propose the idea of primordial black holes formed in the chaos of the early universe. If density fluctuations in that fiery first second were strong enough, whole regions of space could have collapsed under their own gravity before atoms, stars, or galaxies ever existed. Such black holes would carry with them clues to conditions right after the Big Bang. They could be as tiny as mountains, or as massive as stars, hidden across the universe like relics of creation itself. If discovered, they would be time capsules, holding secrets of a universe younger than a heartbeat, when physics itself may have followed rules different from those we term our. Know today. Time near the Big Bang may have flowed differently than it does now. Time feels steady to us. Each second ticked off evenly, one after another. But near the Big Bang, things may not have been so simple. General relativity tells us that time and space are woven together, and their behavior depends on energy and gravity. In the seething furnace of the early universe, densities and energies were unimaginably high. Time itself may have stretched, warped, or slowed compared to the flow we experience today. Some theories suggest that what we call the beginning of time may not even have been the true beginning, but a transformation from one state to another. When we look back across billions of years, we may not just be peering through space, but also through changing rivers of time itself. Ancient light from the universe's earliest moments still fills every corner of space. The cosmic microwave background is a faint, nearly uniform glow of microwave radiation that fills the entire universe. This ancient light dates back nearly 14 billion years, to when the universe cooled enough for photons to travel freely without constant scattering. It is essentially the leftover glow of the Big Bang, providing a snapshot of the universe in its infancy. This radiation is a treasure trove for scientists, carrying subtle temperature fluctuations that reveal the seeds of galaxies and the large-scale structure of the cosmos. The cosmic microwave background is a silent messenger from the dawn of time, surrounding us in every direction. Invisible matter forms a hidden framework that holds galaxies together. Though it neither emits nor absorbs light, dark matter makes up about 85% of the universe's total matter. This mysterious substance acts as an unseen scaffold, exerting gravitational pull that holds galaxies and clusters together. Without dark matter, galaxies would not have enough mass to keep their stars from flying apart. We detect dark matter only through its gravitational effects on visible objects and light. Mapping this invisible framework helps astronomers understand the universe's structure and the formation of cosmic webs. Despite being invisible, dark matter plays a fundamental role in shaping everything we observe. A mysterious force is pushing the universe's expansion to speed up. After decades of assuming the universe's expansion was slowing, astronomers were shocked to discover it's actually speeding up. This surprising acceleration is driven by an unknown phenomenon called dark energy, which makes up nearly 70% of the universe's total energy. Content. Dark energy acts like a repulsive force, counteracting gravity and pushing galaxies farther apart, faster over time. Its nature remains one of the greatest mysteries in modern physics, challenging scientists to rethink the fundamental laws governing space and time. Understanding dark energy is crucial to predicting the ultimate fate of the cosmos, whether it will continue expanding forever, slow down, or end in some cosmic event. Galaxies aren't scattered randomly, they're connected by vast webs of dark matter. Galaxies form part of an enormous cosmic web, woven together by filaments of dark matter stretching across hundreds of millions of light-years. This invisible scaffolding guides the formation and placement of galaxies, clustering them along these vast threads. Between these filaments lie enormous voids, vast emptinesses with few galaxies. The cosmic web's structure influences how galaxies grow, interact, and evolve over billions of years. Though we cannot see dark matter directly, its gravitational pull shapes the universe's large-scale architecture, revealing a universe connected in a delicate, sprawling network. The largest known structure in the universe is a billion light-year-long wave of galaxies. The universe is not uniform. Galaxies are not scattered randomly like dust, but instead form vast patterns, threads, walls, and filaments. One of the most extraordinary of these is the Boss Great Wall, discovered in galaxy surveys. It is a sprawling chain of superclusters extending across nearly 1 billion light-years. Within it, galaxies are strung together like glowing beads on invisible strings of dark matter. To put its scale in perspective, if our Milky Way were a single dot on a map, this wall would stretch across entire pages. These structures remind us that the cosmos is not just vast, but also deeply patterned, a kind of architecture on the grandest imaginable stage. Neutrinos from the first second of creation are still streaming through your body. Neutrinos are ghostly particles, almost without mass, that rarely interact with matter. Trillions of them pass through your body every second, unnoticed. Many of these are made in the sun or distant stars, but some are unimaginably older. In the first second after the Big Bang, neutrinos flooded the universe. Unlike photons, they slipped free early because they interact so weakly with matter. They have been flying through space ever since, forming what physicists call the cosmic neutrino background. Though they are nearly impossible to detect, they are everywhere, including inside you right now. Each one is a relic of the universe's very first heartbeat, still whispering through the cosmos, almost 14 billion years later. Entire galaxies may be moving because of hidden masses beyond the observable edge. Astronomers have noticed that some galaxies are not drifting in the directions we'd expect. Instead, they seem to be tugged along by a hidden influence, something lying far beyond the part of the universe we can see. This motion has been nicknamed the dark flow. It may be caused by enormous masses outside our cosmic horizon, invisible but powerful enough to bend the paths of whole clusters of galaxies. We cannot observe these hidden regions directly, but we see their fingerprints in the motions of galaxies closer to us. It is a reminder that the observable universe is just a patch of something larger, and that unseen structures may still shape the cosmos we live in. The vacuum of space may not be empty, but simmering with quantum energy. When we picture empty space, we often imagine nothingness, a true void. But according to quantum theory, even the vacuum is restless. Tiny particles blink in and out of existence, borrowing energy from uncertainty itself before disappearing again. This restless sea is called the quantum vacuum, and it may hold the key to one of cosmology's greatest mysteries, dark energy. The accelerating expansion of the universe could be driven by the energy of this empty space. In that sense, every cubic inch of apparent nothingness is alive with possibility, buzzing invisibly with the physics that shapes the fate of the cosmos. The Milky Way spins at over 500,000 miles per hour, carrying our solar system on a vast cosmic journey. Our home galaxy, the Milky Way, is a sprawling spiral of stars, gas, and dust, rotating at an astonishing speed. It spins at more than 500,000 miles per hour, and our solar system is caught in this grand rotation, orbiting the galactic center roughly once every 250 million years. This immense journey carries us through the galaxy's spiral arms, amid clouds of gas and star clusters. Despite this dizzying speed, the vast distances between stars mean collisions are extremely rare. This cosmic voyage reminds us how dynamic and interconnected our place in the universe truly is. Sometimes galaxies collide and merge in slow, majestic dances, lasting billions of years. Galaxies are not static islands over billions of years. They drift and interact under gravity's influence. When two galaxies come close enough, they begin a slow, graceful dance, eventually merging into a single, larger galaxy. These encounters can trigger intense bursts of star formation, as clouds of gas compress and collapse. While stars rarely collide directly, gravitational forces reshape the galaxy's structures and can feed the growth of supermassive black holes at their centers. Our own Milky Way is on a collision course with the nearby Andromeda galaxy, destined to merge in about 4 billion years, creating a new cosmic city. Quasars shine as some of the brightest beacons from the distant past, powered by supermassive black holes. Quasars are luminous objects found in the centers of young galaxies, shining across billions of light years. Powered by supermassive black holes consuming enormous amounts of gas and dust, quasars emit incredible energy, often outshining their host galaxies. This intense radiation allows astronomers to study the early universe and the growth of black holes. Quasars serve as cosmic lighthouses, illuminating the intergalactic medium and revealing conditions in the universe's youth. Their dazzling brightness and immense distance make them among the most fascinating objects in the cosmos. In the universe's earliest moments, space expanded faster than the speed of light in a burst called inflation. Within a tiny fraction of a second after the Big Bang, the universe experienced an extraordinary event called cosmic inflation. During this brief period, space itself expanded exponentially, growing faster than the speed of light. This rapid expansion smoothed out irregularities, making the universe remarkably uniform on large scales. It also stretched tiny quantum fluctuations into the seeds of galaxies and large-scale structures we observe today. Inflation solves several cosmic puzzles and is a cornerstone of modern cosmology, offering profound insight into the universe's birth and structure. Patterns in the cosmic microwave background hint at ripples from before the Big Bang. The cosmic microwave background is the oldest light we can see, released when the universe was only hundreds of thousands of years old. To the eye, it looks almost uniform, but sensitive maps reveal tiny variations, ripples less than 1 part in 100,000. These patterns seeded the galaxies, stars, and planets we know today. But some of the ripples are stranger, unusually cold or unusually aligned, pointing to possible physics before the Big Bang itself. They may be scars left from collisions with other universes or echoes of exotic fields that shaped inflation. The faint patterns in this ancient light are not just random noise. They may be the fingerprints of realities far older and larger than our own. The fate of the universe might depend on particles we haven't discovered yet. The destiny of the cosmos, whether it expands forever, collapses back, or drifts into heat death, depends on the nature of its most mysterious ingredients. Dark energy drives expansion, dark matter shapes galaxies, and both may be tied to particles we have never seen. Physicists search for these unseen particles in underground detectors and high-energy colliders, hoping to glimpse the missing pieces of the puzzle. If they exist, they will tell us whether the universe is stable, whether it may someday decay, or whether it might even cycle through endless rebirths. In the smallest particles may lie the largest answers, hidden keys to the story of everything. Gravity may be weaker than it should be, because it leaks into other dimensions. We think of gravity as universal, binding planets to stars and stars to galaxies. But compared to the other forces of nature, it is astonishingly weak. A small magnet can lift a paperclip against the pull of the entire Earth. Some physicists wonder if gravity feels weak because it isn't confined to our familiar universe. Instead, it may spread into hidden dimensions, unseen by us. If true, this would mean the force we experience is only a faint echo of a deeper reality. These extra dimensions could be curled up, too small for us to perceive, yet large enough to siphon away gravity's strength. It's a hypothesis that may explain why the cosmos holds together the way it does, and a hint that our universe could be part of something more layered than we can imagine. The cosmic horizon hides regions of the universe we can never reach. When we look out into the sky, we are really looking back in time. But there is a limit, a boundary called the cosmic horizon. Beyond this line, light has not had enough time to reach us since the Big Bang. Those regions of space are real, filled with galaxies, but they are forever hidden. The horizon is not a wall, but a limit of perspective, like standing on a shore and seeing only as far as the curve of the Earth. Every year, the horizon grows as light from farther reaches finally arrives. Yet space itself expands too, pushing other regions beyond our view. The cosmic horizon is a quiet reminder. No matter how far our telescopes stretch, there will always be more universe beyond, forever out of sight. The first stars ended the universe's long, dark silence, lighting up the cosmos for the first time. For hundreds of millions of years after the Big Bang, the universe was a vast, dark expanse with no stars to light the way. Then, the first stars, massive and brilliant, ignited, piercing this cosmic darkness. These ancient stars burned hotter and faster than most stars today, forging the first heavier elements in their cores. Their intense radiation began to reionize the surrounding hydrogen gas, clearing the fog and making space transparent to ultraviolet light. This era, called cosmic dawn, transformed the universe from a cold, dark void into a vibrant, light-filled cosmos, setting the stage for galaxies, planets, and ultimately, life to emerge. High-energy particles race through space at nearly the speed of light, born from violent cosmic events. Cosmic rays are charged particles, mostly protons and atomic nuclei, accelerated to incredible speeds by some of the universe's most violent phenomena. Exploding stars, supernova, and energetic black holes fling these particles across the cosmos at nearly the speed of light. When cosmic rays reach Earth, they collide with atoms in our atmosphere, creating showers of secondary particles. These energetic visitors can influence atmospheric chemistry and possibly impact cloud formation and climate. Though invisible and mysterious, cosmic rays link us directly to the universe's most powerful events. Our galaxy belongs to a massive supercluster containing thousands of neighboring galaxies. The Milky Way is part of a colossal structure called the Laniakea supercluster, home to thousands of galaxies bound together by gravity. Stretching over hundreds of millions of light-years, this cosmic metropolis is a sprawling network of galaxies moving together through space. Within Laniakea, galaxies interact, collide, and grow, influenced by the immense gravitational pull of this supercluster. Understanding our galaxy's place within this vast cosmic community helps astronomers comprehend the large-scale structure of the universe and forces shaping it. Vast empty spaces, known as voids, stretch across millions of light-years between galaxy clusters. Between the dense clusters and filaments of galaxies lie enormous cosmic voids, immense regions with very few galaxies and low matter density. These voids can span tens of millions of light-years and influence how galaxies move and cluster around them. Though nearly empty, voids contain some sparse gas and dark matter. Their existence shapes the large-scale structure of the universe, carving out the cosmic web and affecting the dynamics of cosmic expansion. Studying voids sheds light on fundamental cosmic mysteries like dark energy and matter distribution. Primordial black holes could be as small as atoms or as heavy as mountains. Most black holes form when stars collapse, but there may be older, stranger ones, primordial black holes. Born in the first moments after the Big Bang, they could be wildly different from the black holes we know today. Some may be tiny, with event horizons smaller than an atom, while others could weigh as much as mountains. Over billions of years, the smallest would have evaporated through Hawking radiation, but others might still drift invisibly through the cosmos. If they exist, they could even make up some or all of the mysterious dark matter. These hidden relics would be scattered everywhere, silent fossils of creation itself, so subtle that a primordial black hole could pass through Earth unnoticed, and so powerful that collectively they may shape the destiny of galaxies. The early universe may have birthed cosmic strings stretching across space. Theories of high-energy physics predict that as the universe cooled from its hot beginning, strange defects in spacetime could have formed, infinitely thin, immensely powerful. These are called cosmic strings. Unlike ordinary strings, they are not matter at all, but cracks in space-time itself, stretching potentially for billions of light-years. If two cosmic strings were to cross, they could snap and release bursts of gravitational waves, ringing through the universe like struck chords. Though none have yet been found, their existence would reveal physics far beyond what we know. The idea that the early universe might still hold hidden filaments, invisible to our eyes but etched into the fabric of space, is both haunting and beautiful, like scars from the cosmos's own birth. Ripples in spacetime could be fossils from the very first instant. Gravitational waves are ripples in spacetime, stirred up by events like colliding black holes. But there may also be far older waves, born in the very first instant of the universe. During cosmic inflation, spacetime itself may have shivered with quantum fluctuations, stretching those ripples across the entire cosmos. These primordial gravitational waves would be unimaginably faint, but if we could detect them, they would be direct fossils of the universe's birth. Unlike light, which only became free hundreds of thousands of years later, these ripples would carry us back almost to time zero. Scientists search for them in delicate patterns of polarization in the cosmic microwave background, hoping to hear the faintest whispers of creation's first breath. Some galaxies may be racing toward a mysterious great attractor hidden in space. Our galaxy, along with many others, is not just drifting aimlessly. It is being pulled toward a region of space called the Great Attractor. This hidden mass lies hundreds of millions of light-years away, shrouded behind the dust of the Milky Way, making it difficult to study. Galaxies across vast distances show a shared motion, as though they are sliding down the slope of some invisible gravitational hill. The true nature of the Great Attractor is still uncertain. It may be a concentration of galaxy clusters, or something even larger. Whatever it is, it exerts a pull strong enough to guide the paths of entire galaxies, including our own. We are moving toward it even now, carried along on the slow current of cosmic gravity. Nearly invisible neutrinos pass through everything, including your own body, all the time. Neutrinos are tiny, nearly massless particles created in vast numbers by the sun, exploding stars, and other cosmic events. These ghostly particles barely interact with matter, passing through entire planets and your body without notice. Trillions of neutrinos fly through you every second, silently connecting us to the energetic processes of the universe. Detecting them requires massive, sensitive instruments buried deep underground or under ice. Though elusive, neutrinos offer unique insights into stellar explosions, the sun's inner workings, and fundamental physics. On the largest scales, the universe looks remarkably uniform in every direction. When viewed across vast distances, the universe appears surprisingly uniform. No matter where we look, the distribution of galaxies and matter shows no chasse, preferred direction. This cosmic isotropy, paired with homogeneity, means the universe looks much the same everywhere on the largest scales. This principle underlies much of modern cosmology, simplifying our models of the universe's evolution. Observations of the cosmic microwave background radiation strongly support this remarkable large-scale uniformity, hinting at fundamental symmetries in nature. A sea of ancient neutrinos fills space, relics from the earliest seconds after the Big Bang. Nearly instantly after the Big Bang, the universe was flooded with neutrinos, tiny, nearly massless particles that barely interact with anything. These neutrinos decoupled from other matter within the first second and have been streaming through space ever since, forming a cosmic neutrino background. Unlike light, these particles pass through almost everything unimpeded, making them incredibly difficult to detect. Despite this, their existence influences the evolution of the cosmos and the formation of large-scale structures. Detecting and understanding these relic neutrinos would open a window into the universe's earliest moments, offering insights into fundamental physics and the ETS, conditions prevailing fractions of a second after the Big Bang. Scientists measure the universe's expansion rate today with something called the Hubble constant. The universe has been expanding ever since its fiery birth, and the current rate of this expansion is captured by the Hubble constant. This value links how fast galaxies are moving away to their distance from us, providing a cosmic speedometer of sorts. However, measuring the Hubble constant precisely has proven challenging, with different methods yielding slightly different results. This tension in measurements fuels ongoing research, as knowing the exact rate helps us understand the universe's age, size, and ultimate fate. The Hubble constant is a fundamental parameter in cosmology, anchoring our understanding of cosmic history and expansion. Dark energy might grow stronger with time, changing the universe's destiny. Dark energy is the mysterious force driving the accelerated expansion of the universe. For now, it seems steady, but what if it changes? Some models suggest that dark energy could grow stronger over billions of years. If that happens, the expansion would accelerate more and more, tearing galaxies apart, then stars, then even atoms, in a catastrophic Big Rip. In other scenarios, dark energy could fade, allowing gravity to slow expansion or even reverse it. Because dark energy makes up most of the cosmos, its behavior determines everything about the future. And yet, for now, we do not know if it is constant or evolving. The entire fate of the universe may rest on the hidden nature of this invisible force. Cosmic voids, vast expanses with almost no galaxies, are still expanding. Between the luminous filaments of the cosmic web lie immense empty regions called voids. These can span hundreds of millions of light years and contain only a handful of galaxies. Voids are not static emptiness, though. They are expanding faster than the rest of the universe as matter flows outward toward denser regions. In a way, they are the growing hollows of the cosmos, ballooning as galaxies drift away. By studying these voids, scientists can test the nature of dark energy and cosmic expansion. For now, they remain among the quietest and loneliest regions of the universe, vast oceans of near nothing, still stretching wider as time moves on. The universe's geometry may be ever so slightly curved. When we think of the universe, we often picture it as flat, stretching endlessly in all directions. But geometry in cosmology is subtle. Depending on its total energy, the universe could be positively curved, like a sphere, or negatively curved, like a saddle. Observations suggest it is astonishingly close to flat, so close that if there is curvature, it is too small to detect with certainty. A universe with even the tiniest curvature would, over unimaginable distances, bend light in ways that reveal its shape. For now, we live in a cosmos that feels flat, but cosmologists keep searching for that faint, hidden curve that could tell us more about its ultimate size: fate. The cosmic microwave background is dotted with strange cold spots. The cosmic microwave background, the afterglow of the Big Bang, is mostly smooth and uniform. Yet here and there, it contains unusual features, patches colder than expected. One of the largest is known simply as the cold spot, a region of the sky where the temperature of this ancient light dips strangely low. Some suggest it may be caused by a massive void in that direction, sapping energy from photons as they pass through. Others speculate it could be a fingerprint of physics beyond the known universe, perhaps even the scar of a collision with another cosmos. Whatever its cause, the cold spot remains one of the most puzzling anomalies written in the universe's oldest light. The first stars may have been hundreds of times heavier than the Sun. In the quiet after the Big Bang, the universe was dark. Then, hydrogen and helium gathered into the very first stars. These were nothing like the stars we see today. With no heavier elements to cool the gas, they grew enormous, hundreds of times the mass of our Sun. Their light was intense, blazing white-blue, and they lived fast, burning through their fuel in only a few million years. These population 3 stars forged the very first heavier elements, carbon, oxygen, and iron, in their cores. When they died, They scattered those elements across space, seeding the raw material for later generations of stars, planets, and eventually, life. Though none remain today, every atom of carbon in your body may once have been born in one of these long-vanished giants. As galaxies move away, their light stretches to longer, redder wavelengths, a phenomenon called redshift. As the universe expands, galaxies drift away from us, and the light they emit gets stretched into longer, redder wavelengths, a phenomenon known as redshift. This is similar to the Doppler effect with sound, where a passing siren's pitch lowers as it moves away. Redshift not only tells us that the universe is expanding, but also helps astronomers measure distances to faraway galaxies and look back in time. By analyzing redshift, scientists can piece together the history of cosmic expansion and understand how the universe evolved over billions of years. To measure vast cosmic distances, scientists use a step-by-step method known as the cosmic distance ladder. Measuring distances in the universe requires clever techniques because objects are too far away to gauge with simple tools. Astronomers rely on the cosmic distance ladder, a series of interconnected methods, each building on the last. They start by measuring distances to nearby stars using parallax, then use standard candles like Cepheid variables and supernovae, whose true brightness is known, to estimate farther distances. This layered approach allows scientists to map the universe's vastness accurately, helping us understand the scale of cosmic structures and the timeline of the universe's evolution. The cosmic horizon marks the farthest edge of the universe we can observe, beyond which lies the unknown. Because the universe is about 13.8 billion years old, light from beyond a certain distance hasn't had time to reach us. This boundary, known as the cosmic horizon, defines the observable universe, the sphere around us containing everything visible. Beyond this horizon may lie countless more galaxies and mysteries, but they remain forever out of reach. As time passes, the horizon expands slightly, gradually unveiling more of the cosmos. Yet, the cosmic horizon reminds us of the limits to our knowledge, urging humility and wonder as we explore the universe. Tiny grains of cosmic dust drift through space, playing a vital role in forming stars and planets. Cosmic dust consists of microscopic particles made from elements like carbon, silicon, and metals. Although these grains are incredibly small, they play an outsized role in the universe's life cycle. Within dense clouds of gas and dust, gravity pulls matter together, and dust helps cool these clouds by radiating heat, allowing them to collapse further. This process leads to the birth of new stars. Around young stars, dust grains collide and stick, gradually forming planets, moons, and other celestial bodies. Dust also provides surfaces for complex molecules to form, fostering the chemistry essential for life. The universe's first stars were nearly pure hydrogen and helium, without heavier elements. The earliest stars, known as population the third stars, formed from primordial clouds composed almost entirely of hydrogen and helium, simplest elements created in the Big Bang. These stars were massive and burned hotter than most stars today, producing intense radiation. They lived brief, brilliant lives before exploding as supernova, dispersing the first heavier elements like carbon, oxygen, and iron into space. These heavier elements became the building blocks for subsequent generations of stars, planets, and eventually life. While none of these first stars remain today, their explosive deaths shaped the chemical complexity of the universe and set the stage for everything we observe now. Hidden behind cosmic dust, distant galaxies glow brightly in infrared light. Many distant galaxies are cloaked in thick clouds of cosmic dust that block visible light, rendering them invisible to optical telescopes. However, this dust absorbs energy from intense star formation and re-emits it as infrared radiation. Observing these galaxies in infrared allows astronomers to peer through the dust and uncover regions of vigorous star birth. These dusty, star-forming galaxies provide crucial insights into galaxy evolution and the early universe's growth. By studying them, scientists gain a fuller picture of how stars and galaxies have evolved over billions of years. Cosmic rays, high-energy particles from space, might subtly influence Earth's weather. Cosmic rays are fast-moving particles, mostly protons, accelerated by powerful cosmic events like supernovae and active galactic nuclei. When they strike Earth's atmosphere, they ionize atoms and molecules, creating showers of secondary particles. Some scientists propose that this ionization influences cloud formation, potentially affecting weather and climate patterns. Though the exact impact remains debated, cosmic rays represent a link between distant energetic processes in the universe and Earth's atmospheric behavior. This connection reminds us how intertwined our planet is with the cosmos. The universe is dominated by matter, but why antimatter disappeared remains a great mystery. The Big Bang should have produced equal amounts of matter and antimatter, which annihilate each other upon contact. Yet, our universe is overwhelmingly made of matter, with antimatter nearly absent. This imbalance, known as the baryon asymmetry, puzzles scientists deeply. It suggests that some unknown processes in the early universe favored matter's survival. Understanding this mystery is crucial for explaining why anything exists at all, from galaxies and stars to planets and life. It remains one of the most profound unanswered questions in physics and cosmology. Gravity leaves its subtle marks on the ancient light we observe today. As light travels through the universe, it passes near massive objects like galaxies and clusters, whose gravity bends and distorts its path, a phenomenon called gravitational lensing. These subtle shifts imprint tiny distortions on the cosmic microwave background radiation, the oldest light we can detect. By studying these distortions, astronomers can map the distribution of both visible and dark matter. Gravitational lensing thus offers a powerful tool to understand the universe's structure and the invisible forces shaping it. Light traveling through space is gently warped and stretched by the gravity of massive objects. Massive celestial bodies such as galaxy clusters and black holes create strong gravitational fields that bend the path of light passing nearby. This bending gravitational lensing can magnify and distort images of distant galaxies, sometimes creating arcs, rings, or multiple images. This natural magnification acts like a cosmic telescope, enabling astronomers to observe galaxies otherwise too faint or distant. Gravitational lensing also provides a unique method to study dark matter, which exerts gravitational pull but emits no light, revealing the hidden structure of the universe. The universe's first light began when stars and galaxies formed. After hundreds of millions of years of darkness following the Big Bang, the universe's first stars ignited, ushering in the era of cosmic dawn. These pioneering stars grouped into early galaxies, their collective glow piercing the darkness and filling the cosmos with light for the very first time. This ancient light marked a fundamental transformation, the end of the cosmic dark ages, and set in motion processes that led to the complex cosmic structures we see today. This first illumination laid the foundation for the growth of galaxies, star clusters, and eventually planets, offering the universe its first glimpse of brilliance. The universe became transparent when ultraviolet light ionized hydrogen gas. In its early years, the universe was a foggy expanse filled with neutral hydrogen gas that absorbed much of the light trying to travel through it. The formation of the first stars and galaxies changed this, as their ultraviolet radiation ionized the surrounding hydrogen atoms, stripping electrons away and turning the gas into plasma. This reionization phase cleared the cosmic fog, allowing light to stream freely across space. This transformation from opaque to transparent space opened a window for the universe to shine clearly, enabling the vast cosmic web of galaxies to emerge, be observed billions of years later. Star formation peaked billions of years ago during a cosmic high noon. Billions of years ago, the universe experienced a period of intense star formation, often called cosmic high noon. During this epoch, galaxies were rapidly creating stars at rates much higher than we see today. This surge in star birth enriched the universe with heavier elements essential for planets and life. After this peak, star formation gradually declined, leading to the more peaceful cosmos we observe now. This golden age shaped the universe's evolution, weaving the fabric of matter that supports galaxies, solar systems, and ultimately, life itself. Elements heavier than helium grew more abundant as stars lived and died. The universe's earliest elements were mostly hydrogen and helium, products of the Big Bang. However, as stars formed and aged, they fused these light elements into heavier ones like carbon, oxygen, and iron within their cores. When massive stars exploded as supernova, they scattered these heavier elements into space, enriching the interstellar medium. This cosmic recycling allowed subsequent generations of stars and planets to form from richer material, eventually creating the building blocks necessary for complex chemistry and life. Over billions of years, the universe transformed from a simple primordial soup into a chemically diverse environment. Giant filaments of matter connect clusters of galaxies like a cosmic web. The large-scale structure of the universe resembles a vast web, with clusters of galaxies linked by enormous filaments of matter stretching millions of light-years. These filaments, composed mainly of dark matter and gas, form the backbone of the cosmos, guiding the movement and growth of galaxies. Between these threads lie vast voids, immense regions of empty space. This cosmic web shapes how galaxies cluster and evolve, revealing the universe's intricate architecture. Mapping these filaments helps scientists understand the distribution of matter and the forces sculpting the cosmos. Powerful jets of particles shoot out from supermassive black holes. At the centers of many galaxies lie supermassive black holes, some of which unleash jets of charged particles traveling at nearly the speed of light. These jets can extend for millions of light-years, affecting the gas and dust in their host galaxies. By heating and pushing away material, they regulate star formation and influence the galaxy's evolution. Observing these energetic jets reveals the dynamic relationship between black holes and their cosmic environments, showcasing some of the universe's most powerful phenomena. Massive galaxy clusters form the densest nodes of the cosmic web. Galaxy clusters are the universe's largest gravitationally bound structures, containing hundreds or even thousands of galaxies packed into regions millions of light-years across. These clusters act as the densest nodes within the vast cosmic web, a sprawling network of filaments made of dark matter and gas, connecting galaxies across unimaginable distances. The immense gravity in clusters pulls galaxies together, influencing their motions, interactions, and evolution. These regions are also filled with hot, X-ray emitting gas, adding to their dynamic complexity. Studying galaxy clusters reveals how matter is distributed on the largest scales and offers clues about dark matter, dark energy, and the universe's history. The universe's shape is incredibly close to flat. not curved like a sphere. Cosmological measurements show the universe's geometry is astonishingly flat, meaning it doesn't curve inward like a sphere or outward like a saddle. This flatness implies a precise balance between the universe's total energy and its expansion rate. A flat universe means parallel lines stay parallel even over cosmic distances, shaping the paths of light and matter. This discovery supports inflationary models that predict such geometry and helps determine the universe's ultimate fate, suggesting it will expand forever, rather than collapse. Understanding the universe's shape is key to unraveling cosmic evolution. Tiny temperature differences in ancient light seeded all cosmic structures. The cosmic microwave background radiation appears nearly uniform, but contains minute temperature fluctuations, variations of just a few Cray, millionths of a degree. These tiny ripples represent slight differences in density in the early universe. Over billions of years, gravity amplified these small variations, causing matter to clump and form galaxies, clusters, and the large-scale cosmic web. These ancient fluctuations are essentially the universe's original blueprint, dictating how cosmic structures grew and evolved. Mapping them provides a window into the universe's infancy and the fundamental physics at play. Some uncertainty in measurements arises because we observe only one universe. Cosmic variance is a fundamental limitation in cosmology, resulting from having access to just one universe. Since we can only observe our unique cosmic environment, statistical studies of galaxy distributions or cosmic background fluctuations carry inherent uncertainties. Without multiple universes to compare, we cannot be certain whether observed patterns are universal or just chance occurrences. This uncertainty challenges astronomers to develop sophisticated models and careful analyses to ensure robust conclusions. Cosmic variance reminds us of the unique vantage point and limits of our cosmic knowledge. Scientists estimate cosmic history by measuring the ages of distant galaxies. Astronomers use the light from distant galaxies to estimate their ages, effectively looking back in time. By analyzing stellar populations and spectra, scientists determine how long ago these galaxies formed stars. Since light takes billions of years to reach us, observing distant galaxies reveals the universe's history across epochs. These age estimates help build a timeline of cosmic events, tracking galaxy formation, star formation rates, and chemical evolution. Together with other observations, measuring galaxy ages paints a detailed picture of how the cosmos grew from its earliest moments to the rich structures we see today. Hypothetical cosmic strings might be relics from the universe's earliest moments. Cosmic strings are theoretical one-dimensional defects in spacetime, predicted by some early universe physics models. Imagine ultra-thin, immensely dense filaments stretching across the cosmos, formed during phase transitions fractions of a second after the Big Bang. These strings, if they exist, could produce gravitational waves or cause distortions in the cosmic microwave background. Detecting cosmic strings would offer profound insights into fundamental physics and the conditions of the infant universe. Though no direct evidence has yet been found, cosmic strings remain a fascinating possibility in cosmology, linking quantum physics to cosmic structure. High-energy X-rays glow from distant black holes devouring matter. Deep within many galaxies lurk supermassive black holes, often millions or billions of times the mass of our Sun. When these cosmic giants actively consume surrounding gas and dust, the material forms a swirling accretion disk, heated to millions of degrees by friction and pressure. Gravity. This extreme environment emits powerful X-rays that shine across billions of light-years, detectable by space telescopes. These X-rays reveal violent processes occurring near the black hole's event horizon, and help astronomers understand black hole growth, their energetic sepia, feedback on galaxies, and the role they play in shaping cosmic evolution. Observing these glowing beacons provides a window into some of the universe's most extreme and mysterious regions. Turbulent gas clouds within galaxies shape star formation. Within galaxies, vast clouds of gas churn turbulently, stirred by gravity, shock waves from supernova, and magnetic forces. This turbulence compresses parts of the clouds, triggering the collapse of dense pockets that ignite as new stars. The balance between turbulence and gravity controls how many stars form and how massive they become. This intricate dance of chaotic motions and gentle collapses governs the life cycle of galaxies. Understanding this turbulence is key to unraveling how galaxies evolve and sustain star formation over billions of years, painting a vivid picture of cosmic candidae, birthplaces. Pulsars and distant galaxies send radio waves filling the universe. Pulsars, which are rapidly spinning neutron stars left behind after massive star explosions, emit beams of radio waves sweeping through space like cosmic lighthouses. Alongside pulsars, many galaxies emit diffuse radio waves from energetic processes like star formation and black hole jets. Radio astronomy captures these signals, revealing hidden aspects of the universe in invisible light. These radio waves allow scientists to study exotic objects, map magnetic fields, and explore the large-scale structure of the cosmos. Listening to this invisible radio symphony offers insights into the universe's energetic and dynamic nature. Exploding stars launch particles speeding through space as cosmic rays. When massive stars end their lives in supernova explosions, they unleash shock waves that accelerate particles, mostly protons and atomic nuclei, to near light speed, creating cosmic rays. These energetic particles traverse the galaxy, occasionally colliding with Earth's atmosphere and producing cascades of secondary particles detectable by air. Instruments. Cosmic rays influence the chemistry and dynamics of the interstellar medium and possibly Earth's atmosphere. Their origins and properties connect Earth to distant, violent cosmic events, serving as messengers from some of the universe's most energetic phenomena. Patterns in ancient light's polarization reveal early cosmic events. The cosmic microwave background radiation, the afterglow of the Big Bang, not only shines faintly, but also exhibits polarization, where light waves oscillate preferentially in certain directions. This subtle polarization encodes information about gravitational waves and density fluctuations from the universe's earliest moments. By studying these patterns, scientists test theories of cosmic inflation and understand how tiny quantum ripples evolved into the large-scale structures of galaxies and clusters. These delicate signals offer a unique glimpse into the physics of the universe's birth and the forces shaping its evolution. Ultraviolet radiation cleared foggy gas, making the universe transparent. After the first stars formed, their intense ultraviolet light ionized the surrounding hydrogen gas that had made the early universe opaque. This process, called re-ionization, stripped electrons from hydrogen atoms, transforming the cosmos from a foggy, light-absorbing haze into a transparent expanse where photons could travel freely. This fundamental change allowed light to journey vast distances, revealing galaxies and structures billions of years later. Reionization marks a key transition in cosmic history, opening the universe's windows and shaping its evolution toward the star-filled sky we observe today. The first galaxies ionized hydrogen, transforming the early universe. As the universe emerged from darkness, the first galaxies ignited intense ultraviolet light, that ionized surrounding hydrogen gas. This ionization stripped electrons from hydrogen atoms, changing the universe from a neutral, foggy state into a transparent one. This process, known as reionization, allowed light to travel freely across space for the first time, illuminating the cosmos and revealing the large-scale structure of galaxies. The ionizing power of these early galaxies transformed the universe's appearance and marked a major milestone in cosmic evolution. Studying this transition helps scientists understand how the first luminous objects shaped the universe and paved the way for the complex structures we can observe today. Dark energy's mysterious push is speeding up the universe's growth. Though gravity pulls matter together, a surprising discovery revealed that the universe's expansion is accelerating, driven by an enigmatic force called dark energy. This dark energy acts like a repulsive pressure, pushing galaxies apart faster over time. Accounting for about 70% of the universe's total energy, dark energy remains one of science's greatest mysteries. Its nature, origin, and ultimate effects on cosmic fate challenge our understanding of physics. Whether dark energy will cause endless expansion or lead to a cosmic end remains unknown. Unraveling its secrets is a central quest in modern cosmology. The scale factor describes how distances in the universe expand over time. Cosmologists use the scale factor to track how space itself stretches as the universe grows. This dimensionless number changes with time, describing the relative expansion since the Big Bang. When the scale factor doubles, distances between galaxies also roughly double, illustrating cosmic growth. Measuring its changes helps scientists understand the universe's expansion history, the influence of dark energy, and the dynamics of cosmic acceleration. The scale factor provides a simple yet powerful way to chart the vast unfolding of the cosmos over billions of years. The universe's curvature affects its overall shape and destiny. The universe's geometry, whether flat, open, or closed, depends on its total density of matter and energy. A flat universe means parallel lines stay parallel at cosmic scales, implying a balance between gravity and expansion. If the universe were curved like a sphere closed, it might eventually collapse, while an open, saddle-shaped universe would expand forever. Current observations show the universe is astonishingly close to flat, shaping our understanding of cosmic evolution. This curvature influences the universe's fate and the paths of light and matter, guiding the grand cosmic journey. Matter is distributed evenly on the largest cosmic scales. When viewed on scales spanning hundreds of millions of light-years, matter, including galaxies and dark matter, is remarkably uniform. This homogeneity means that, statistically, no region is significantly denser or emptier than another on the largest scales. This even distribution simplifies cosmological models and supports the cosmological principle, which assumes the universe is isotropic, homogeneous. Though locally galaxies cluster and voids exist, the overall cosmic balance reveals fundamental symmetries and structures that govern the universe's evolution. The universe looks nearly the same in every direction. Cosmic isotropy means that the universe appears almost identical no matter where we look. Observations, including those of the cosmic microwave background, show uniform temperature and matter distribution across the sky. This isotropy, together with homogeneity, forms the foundation for modern cosmology's understanding of the universe's large-scale structure. It suggests that the laws of physics and cosmic conditions are consistent throughout space, allowing scientists to develop universal models describing cosmic schema, history, expansion, and evolution. The discovery of cosmic background radiation confirmed the Big Bang. In 1965, Scientists Arno Penzias and Robert Wilson accidentally discovered a faint, uniform microwave glow permeating the universe, now known as the cosmic microwave background radiation. This ancient light is the afterglow of the Big Bang, dating back nearly 14 billion years to when the universe first became transparent. Its discovery provided powerful evidence supporting the Big Bang theory, transforming cosmology from speculation to science. Detailed measurements of this radiation revealed tiny temperature fluctuations that seeded the formation of galaxies and large-scale structures. The cosmic microwave background remains a cornerstone of our understanding, acting as a time capsule from the universe's infancy and a guide to its evolution. Cosmic history spans from fractions of a second to billions of years. The universe's story began in an unimaginably brief instant, the Planck epoch, just a fraction of a second after the Big Bang. From this fiery birth, cosmic history unfolded through epochs: inflation, recombination, cosmic dawn, and galaxy formation. Each stage brought profound changes: space expanding, matter cooling, light emerging, and structures forming. Billions of years passed as galaxies evolved, stars ignited, and planets took shape. This vast timeline reveals a universe in constant transformation, where every moment connects past, present, and future in an ongoing cosmic dance. Understanding this timeline helps us grasp our place in the grand scheme. The observable universe grows as the cosmic light horizon expands. The observable universe is bounded by the cosmic light horizon, the farthest distance from which light has reached us since the Big Bang. As time passes, this horizon slowly expands, allowing us to see more distant galaxies and structures. However, due to cosmic expansion, some regions may remain forever beyond our reach. This expanding horizon represents the limits of human observation and knowledge. It's a reminder that, while we've seen incredible cosmic depths, much of the universe still lies hidden in darkness, waiting patiently for future discoveries, expanding our sense of wonder. Brief, powerful bursts of energy light up space for moments at a time. Gamma-ray bursts are intense flashes of high-energy radiation that briefly outshine entire galaxies. These bursts, lasting from milliseconds to minutes, often result from massive star collapses or merging neutron stars. Despite their fleeting nature, gamma-ray bursts release tremendous energy, illuminating distant corners of the universe. They serve as cosmic beacons, providing clues about stellar death, black hole formation, and the universe's evolution. Observing these brief, powerful events allows scientists to probe extreme physics under conditions impossible to replicate on Earth. Expanding space stretches the light traveling through it. As the universe expands, light waves traveling through space are stretched, increasing their wavelength, a phenomenon known as cosmological redshift. This stretching shifts light toward the red end of the spectrum, making distant galaxies appear redder than they emit. Redshift serves as a cosmic clock, allowing astronomers to measure how fast galaxies recede and to estimate their distances. This effect provides direct evidence for the universe's expansion and enables us to look back in time, observing galaxies as they were billions of years ago. The stretching of light is a subtle but profound signature of cosmic growth. Relic neutrinos have filled space since the universe was only 1 second old. Almost immediately after the Big Bang, the universe was filled with relic neutrinos, tiny, nearly massless particles that rarely interact with matter. These neutrinos decoupled from the hot plasma within 1 second, streaming through space ever since. Though incredibly difficult to detect due to their weak interactions, relic neutrinos influence cosmic evolution and the formation of large-scale bow structures. They represent a cosmic fossil, carrying information about conditions in the universe's earliest moments. Detecting and studying these neutrinos remains a major goal in physics, promising insights into the universe's fundamental nature. Cosmic voids are giant, empty spaces between galaxy clusters. Cosmic voids are vast, sparsely populated regions stretching millions of light-years across, where few galaxies or matter exist. These immense voids are like cosmic deserts, contrasting sharply with dense galaxy clusters and filaments. Though nearly empty, voids play a crucial role in shaping the universe's large-scale structure by influencing the gravitational pull and motion of surrounding galaxies. Studying voids helps scientists understand the distribution of dark matter, the effects of dark energy, and the overall evolution of cosmic architecture. These silent expanses remind us of the universe's vastness and the intricate balance between matter and emptiness. Galaxies grow bigger through slow mergers over billions of years. Galaxies are dynamic entities that grow and evolve by merging with neighbors. These galactic mergers are slow, majestic processes unfolding over billions of years, during which stars, gas, and dark matter combine. Mergers can trigger bursts of star formation, reshape galactic structures, and fuel central black holes. Our own Milky Way is expected to collide and merge with the nearby Andromeda galaxy in several billion years. Understanding galaxy mergers reveals how cosmic structures build up complexity over time, painting a picture of a universe in constant transformation. Invisible magnetic fields thread through galaxies, guiding charged particles. Magnetic fields, though invisible, permeate galaxies and influence cosmic processes. These fields guide the motion of charged particles, affect star formation, and shape the behavior of interstellar gas. Though weak compared to Earth's magnetic field, galactic magnetic fields stretch over thousands of light-years, weaving through spiral arms and galactic halos. Studying these magnetic forces helps astronomers understand the dynamics of galaxies, the propagation of cosmic rays, and the interplay between matter and energy on grand scales. These unseen threads add complexity to the cosmic tapestry. Cosmic rays occasionally cause mutations in DNA here on Earth. Cosmic rays are energetic particles originating from supernova and other cosmic phenomena. When they strike Earth's atmosphere, they create showers of secondary particles that reach the surface. Some of these particles penetrate living organisms, occasionally causing mutations in DNA. While most mutations are harmless or repaired, some contribute to genetic variation and evolution. The constant rain of cosmic rays links Earth's biological history to the broader universe, illustrating how cosmic phenomena subtly influence life on Grade, our planet. Bubble-like structures may have formed during early cosmic phase transitions. In the universe's earliest moments, rapid changes called phase transitions may have created bubble-like structures in spacetime. These bubbles, expanding and colliding, could have left imprints on the cosmic microwave background or produced gravitational waves. Such phase transitions relate to fundamental forces separating and symmetries breaking as the universe cooled. Detecting evidence of these bubbles would provide insight into high-energy physics and the conditions just after the Big Bang, offering a glimpse into the universe's fiery birth. Tiny fluctuations in ancient light reveal our universe's beginnings. The cosmic microwave background radiation carries faint ripples, tiny temperature and density fluctuations that are the seeds of all cosmic structures. These subtle variations represent slight differences in matter concentration in the early universe, which gravity amplified over billions of years into panda, galaxies, clusters, and cosmic filaments. By mapping these fluctuations with exquisite precision, scientists decode the universe's initial conditions and test cosmological models. These delicate imprints offer a profound window into the universe's origins and the forces shaping its evolution. Cosmic rays help create the northern and southern lights near Earth's poles. The dazzling aurora's northern and southern lights are partly sparked by cosmic rays, high-energy particles traveling through space. When these particles collide with Earth's magnetic field and atmosphere near the poles, they excite gases, causing them to glow in vivid colors of green, red, and purple. Cosmic rays, along with solar wind particles, energize the upper atmosphere, creating these mesmerizing light shows. This cosmic connection between distant energetic events and Earth's skies reminds us that our planet is part of a vast, dynamic universe with subtle cosmic influences shaping natural wonders. Galaxies flow along gravitational currents shaped by matter's distribution. Galaxies don't drift randomly but move along vast gravitational currents defined by the universe's distribution of matter, especially dark matter. These invisible flows guide galaxies along filaments of the cosmic web, pulling them toward dense clusters and voids. This cosmic dance shapes galaxy formation, interactions, and evolution over billions of years. Understanding these gravitational streams helps astronomers map the large-scale structure of the universe and uncover the forces driving cosmic endowment. Evolution, revealing the interconnectedness of matter on the grandest scales. Photons last scattered about 380,000 years after the Big Bang. Approximately 380,000 years after the Big Bang, the universe cooled enough for photons, particles of light, to decouple from matter and travel freely. This event, called recombination, marks the release of the cosmic microwave background radiation, the oldest light visible today. Before this, the universe was opaque, with photons constantly interacting with charged particles. The moment of last scattering transformed the universe into a transparent expanse, allowing light to journey across space and time. Studying this light reveals the universe's early conditions and its evolving structure. Small temperature variations in ancient light seeded galaxies and clusters. The cosmic microwave background radiation is nearly uniform but contains tiny temperature differences, mere millionths of a degree. These small fluctuations correspond to density variations in the early universe. Over billions of years, gravity amplified these differences, leading matter to clump and form galaxies, clusters, and the cosmic web. These primordial seeds set the stage for the universe's large-scale structure. By precisely mapping these temperature variations, scientists gain insight into the universe's infancy and the processes that shaped its evolution. Gravitational tides stretch and shape galaxies over time. Just as the Moon's gravity influences Earth's tides, gravitational forces from nearby galaxies and dark matter create tidal effects in galaxies themselves. These gravitational tides stretch, distort, and reshape galaxies, affecting their spiral arms and star formation patterns. Over millions of years, tidal interactions can trigger bursts of star birth or even lead to galactic mergers. Understanding these tidal forces reveals how galaxies evolve within their cosmic neighborhoods and highlights the dynamic, interconnected nature of the universe. Quantum fluctuations during inflation grew into galaxies and clusters. During the brief period of cosmic inflation just after the Big Bang, tiny quantum fluctuations, minute variations in energy, were rapidly stretched to cosmic scales. These fluctuations became the seeds from which all galaxies and clusters grew. Inflation magnified these tiny ripples, imprinting them onto the fabric of spacetime. Over billions of years, gravity amplified these variations, forming the rich cosmic structures observed today. This remarkable process links the quantum realm to the vastness of the universe, revealing the profound interconnectedness of nature's smallest and largest scales. Cosmic dust grains are the seeds from which stars and planets form. Tiny grains of cosmic dust, composed of elements like carbon, silicon, and metals, drift through interstellar space, playing a vital role in the universe's life cycle. These dust particles gather in vast clouds, cooling the gas and enabling it to collapse under gravity. This collapse sparks the birth of new stars, while the surrounding dust coalesces into disks that can form planets, moons, and other celestial bodies. Dust also facilitates complex chemical reactions, creating molecules essential for life. Though minuscule, these cosmic grains are the building blocks of stars, planets, and ultimately, the rich tapestry of the cosmos. Light years measure distances too vast for ordinary units. A light year is the distance light travels in 1 year, about 6 trillion miles or 10 trillion kilometers, offering a convenient way to measure cosmic distances. Using light years, astronomers can describe how far away stars, galaxies, and other celestial objects are, helping us grasp the immense scale of the universe. For example, the nearest star beyond our Sun is over 4 light years away, meaning its light takes more than 4 years to reach us. Light years provide a sense of cosmic time and distance, linking the vastness of space to the speed of light's journey. The universe's oldest light has a temperature just a few degrees above absolute zero. The cosmic microwave background radiation, the universe's oldest light, permeates all space with a chilling temperature of about 2.7 degrees above absolute zero. This faint glow is the cooled remnant of the hot, dense early universe, stretched and cooled as space expanded over billions of years. Its near-uniform temperature carries tiny fluctuations that seeded cosmic structures. The cold temperature highlights how the universe has evolved from a fiery beginning to its current vast, cool state, embodying the passage of cosmic time in a rare, silent, pervasive glow. Cosmic ray showers cascade through Earth's atmosphere constantly. When high-energy cosmic rays, particles traveling near light speed, strike Earth's atmosphere, they collide with atoms, creating cascades of secondary particles called air showers. These showers spread through the atmosphere, sometimes reaching Earth's surface and detected by instruments worldwide. Cosmic ray showers provide insights into the universe's most energetic processes, like supernova and black hole jets. They also interact with atmospheric chemistry and possibly influence climate patterns. Constantly raining down, cosmic rays remind us of Earth's connection to the broader cosmic environment. Voids influence the movement and growth of galaxies around them. Cosmic voids, vast regions with few galaxies, impact the dynamics of nearby galaxies and clusters. Their low density creates gravitational effects that push surrounding matter outward, influencing the flow and clustering of galaxies. Voids shape the cosmic web's evolution, guiding matter along filaments and affecting galaxy formation and interaction. Studying voids helps astronomers understand dark energy's role and the universe's large-scale structure. These empty expanses, though seemingly barren, play a subtle but crucial role in cosmic evolution. Jets from black holes sculpt their host galaxies. Supermassive black holes at galaxy centers often emit powerful jets of charged particles traveling near light speed. These jets can extend millions of light years, influencing their surroundings by heating and dispersing gas. By regulating star formation and reshaping the interstellar medium, black hole jets act as cosmic sculptors, affecting the growth and evolution of their host galaxies. Observing these jets offers insight into the interplay between black holes and galaxies, revealing dynamic processes shaping the universe's grand design. The first galaxies formed during a time known as cosmic dawn. Cosmic dawn represents one of the most transformative epochs in the universe's history, the moment when the first galaxies ignited after hundreds of AND, millions of years of darkness. During this period, primordial clouds of gas collapsed under gravity, giving birth to the earliest groups of stars and galaxies. These fledgling galaxies flooded the universe with ultraviolet light, initiating processes like reionization that transformed the cosmic landscape. This dawn marked the end of the cosmic dark ages and began the universe's luminous chapter. Studying this era reveals how the simplest building blocks evolved into the complex cosmic structures that fill the sky today, offering a glimpse into the universe's awakening from its initial silence. The universe's oldest light fills space almost uniformly. The cosmic microwave background radiation bathes the entire cosmos in a faint, nearly uniform glow. This ancient light dates back nearly 14 billion years, a relic from when the universe first became transparent. Its uniformity is remarkable. The temperature varies by only tiny fractions of a degree across vast distances. This near-uniform glow reflects the early universe's smoothness after the Big Bang, before gravity amplified subtle fluctuations into galaxies, clusters, and filaments. This pervasive light envelops us all, a silent witness to the universe's infancy and the foundation upon which cosmic structure was built. It is a cosmic backdrop that connects us to the universe's origins. Measuring galaxy ages helps scientists chart the universe's history. By analyzing the light from galaxies billions of light-years away, scientists effectively look back in time, estimating how old these distant systems are. Spectral signatures reveal the ages of stars within these galaxies, offering insights into when star formation began and how galaxies evolved. This cosmic archaeology helps piece together the timeline of galaxy growth, chemical enrichment, and star birth rates. Combined with other observations, measuring galaxy ages paints a detailed portrait of cosmic history, showing how matter evolved from a hot, dense beginning to Bra, the richly structured universe we see today. This method reveals the ongoing story of cosmic transformation and maturation. Cosmic evolution describes how everything changes over billions of years. Cosmic evolution is the grand narrative of transformation from the universe's fiery inception to its present state. It encompasses the formation and growth of stars, galaxies, planets, and the emergence of chemical complexity. Over billions of years, fundamental forces shaped matter and energy, sculpting the cosmos into intricate structures. This continual change is reflected in the evolving galaxies, star populations, and cosmic environments. Understanding cosmic evolution offers perspective on our place within this vast, dynamic universe, a universe that is constantly growing, changing, and unfolding its secrets through time. Cosmic variance reminds us we observe only one universe. Cosmic variance is a fundamental limit in cosmology, arising because we can observe only a single universe. Unlike experiments where multiple trials are possible, astronomers must interpret data from one cosmic realization. This means statistical measurements, like fluctuations in the cosmic microwave background or galaxy distributions, carry inherent uncertainties. Some observed features may be random variations rather than universal truths. Cosmic variance challenges scientists to carefully separate signal from noise and highlights the unique vantage point humanity holds in exploring the cosmos. It is a humbling reminder of our observational limitations. Cosmic rays interact with the solar wind flowing from the sun. The solar wind, a continuous flow of charged particles from the sun, interacts with incoming cosmic rays, shaping how many reach Earth's atmosphere. This interaction modulates cosmic ray intensity, affecting ionization levels in the upper atmosphere and contributing to space weather phenomena. Variations in solar activity influence this modulation, leading to changes in cosmic ray flux over solar cycles. Understanding this complex relationship is important for protecting satellites, astronauts, and Earth's technology from radiation damage. It also connects solar behavior with cosmic influences, illustrating how our star interacts with the broader universe in subtle but significant ways. Magnetic fields stretch across entire galaxies, shaping their evolution. Invisible, yet influential, magnetic fields thread through galaxies, shaping the movement of charged particles and the behavior of interstellar gas. These fields help regulate star formation by guiding gas flows and influencing the collapse of clouds where stars are born. Spanning thousands of light years, galactic magnetic fields intertwine with cosmic rays and plasma, adding complexity to galactic dynamics. Though weak compared to Earth's magnetic field, their vast scale means they have a profound impact on the evolution of galaxies. Understanding these magnetic forces helps astronomers unravel how galaxies grow, maintain structure, and interact with their environment over billions of years. Reionization made the universe transparent to ultraviolet light. In the universe's infancy, neutral hydrogen gas absorbed ultraviolet light, rendering space opaque and dark. The first stars and galaxies emitted intense ultraviolet radiation that ionized this hydrogen, stripping electrons and transforming the gas into a Burr, transparent plasma. This epoch of reionization lifted the cosmic fog, allowing light to travel freely across the universe for the first time. This transition fundamentally changed the universe's appearance and enabled the formation of complex structures visible today. Studying reionization sheds light on the earliest luminous objects and the processes that cleared the cosmic haze. Cosmic dawn ended the universe's dark and opaque childhood. The era known as cosmic dawn marks the universe's emergence from darkness and opacity. Before this time, the cosmos was filled with neutral hydrogen gas that absorbed light, keeping it dark and foggy. With the birth of the first stars and galaxies, intense radiation began ionizing hydrogen, clearing the fog and allowing light to permeate space. This dawn of cosmic illumination transformed the universe into the transparent expanse we observe today. Exploring cosmic dawn helps astronomers understand the timing, mechanisms, and consequences of the universe's first illumination. Cosmic strings, if they exist, could reveal fundamental physics secrets. Cosmic strings are hypothetical, ultra-thin defects in spacetime, predicted by some theories about the universe's earliest moments. If real, these incredibly dense filaments could stretch across vast cosmic distances, affecting gravitational fields and possibly producing detectable gravitational waves. Detecting cosmic strings would offer profound insights into fundamental physics, including the unification of forces and the fabric of space-time itself. Though no direct evidence exists, cosmic strings remain a fascinating concept that could bridge the gap between quantum mechanics and cosmology. Inflation explains why the universe appears smooth and uniform on large scales. The theory of cosmic inflation proposes a brief period of exponential expansion moments after the Big Bang. This rapid stretching smoothed out irregularities and distributed tiny quantum fluctuations across vast distances. Inflation explains why the universe looks so uniform in every direction, despite its enormous size. These tiny fluctuations became the seeds of galaxies and large-scale structures. Inflation solves several cosmic puzzles and remains a cornerstone of modern cosmology, linking the smallest scales of quantum physics with the grandest cosmic structures. Photons from the Big Bang carry messages from the universe's birth. Photons, particles of light, released during the Big Bang have traveled through space for nearly 14 billion years. These ancient photons make up the cosmic microwave background radiation, a faint glow filling the universe. Their properties encode information about the universe's earliest moments, its composition, and its evolution. By studying these primordial photons, scientists unlock secrets of cosmic origin, inflation, and structure formation. They are messengers from the dawn of time, connecting us to the universe's fiery beginning. Cosmic rays were first discovered over a century ago. In the early 1900s, scientists noticed mysterious radiation penetrating Earth's atmosphere, eventually identifying it as cosmic rays, high AS, energy particles originating from outer space. These energetic particles, mostly protons and atomic nuclei, travel at near-light speeds and bombard Earth constantly. Early experiments by Victor Hess and others revealed that cosmic rays increased in intensity at higher altitudes, confirming their extraterrestrial origin. Today, cosmic rays continue to intrigue scientists, offering clues about violent cosmic events like supernova and black hole jets. Their discovery marked the beginning of cosmic ray physics, linking Earth to energetic processes unfolding across the universe. Cosmic horizons limit how far we can see into space and time. The universe has a finite age, about 13.8 billion years, meaning light from beyond a certain distance hasn't had time to reach us. This boundary, called the cosmic horizon, defines the observable universe's edge. Beyond this horizon lies an unseen expanse of space and time, possibly containing countless more galaxies and mysteries. As the universe ages, the horizon slowly expands, allowing us to observe more distant objects. However, due to the universe's expansion, some regions may remain forever unreachable. The cosmic horizon sets fundamental limits on our knowledge, reminding us that the cosmos is vaster than what we can observe. The cosmic microwave background captures a snapshot of the young universe. The cosmic microwave background radiation is a faint, uniform glow filling space, a relic from when the universe was just about 380,000 years old. At this time, the universe cooled enough for photons to travel freely, creating a snapshot of the cosmos's infancy. This radiation carries subtle temperature fluctuations that reflect the density variations seeding galaxies and large-scale structures. Detailed observations of the cosmic microwave background provide invaluable insights into the universe's composition, age, and evolution, serving as a cornerstone for modern cosmology. Polarization in ancient light helps reveal the universe's earliest moments. Beyond its temperature, the cosmic microwave background radiation also exhibits polarization, a pattern in the orientation of light waves. This polarization encodes information about gravitational waves and density fluctuations from the universe's earliest moments. Studying these patterns helps scientists test inflationary models and understand how primordial fluctuations grew into galaxies and clusters. Polarization measurements offer a unique window into the physics of the Big Bang, providing clues about the universe's origin and the forces that shaped its evolution. Cosmic filaments contain much of the universe's ordinary matter. Galaxies cluster along vast filaments composed of dark matter and ordinary or baryonic matter, gas, and dust. These cosmic filaments stretch across millions of light years, forming the universe's large-scale structure. While dark matter dominates the mass, filaments hold much of the ordinary matter that forms stars, planets, and life. This matter exists as hot, diffuse gas between galaxies, often challenging to detect. Understanding filaments helps scientists trace how matter flows through the cosmos and how galaxies grow within this vast network. Jets from black holes can stretch for millions of light years. Supermassive black holes at galactic centers often launch jets of charged particles moving at nearly the speed of light. These jets can extend for millions of light-years, sculpting the intergalactic medium and influencing star formation in their host galaxies. By heating and displacing gas, jets regulate galaxy evolution, preventing runaway star formation or triggering new bursts. Observing these colossal jets provides insights into the powerful interplay between black holes and their cosmic environments, revealing some of the universe's most energetic and dynamic processes. Inflation left subtle imprints on ancient light we detect today. During the brief moment of cosmic inflation, the universe expanded exponentially, stretching tiny quantum fluctuations to macroscopic scales. These fluctuations became the seeds of all cosmic structures, galaxies, clusters, and filaments. The imprint of inflation remains encoded in the cosmic microwave background radiation as delicate patterns of temperature and polarization variations. By studying these subtle imprints, scientists gain insight into the universe's earliest instance and the physics governing its rapid birth. Inflation's legacy links the quantum world with the vast cosmos, revealing the profound unity of nature's smallest and largest scales. Cosmic rays may play a role in Earth's cloud formation. Some scientists propose that cosmic rays influence Earth's climate by affecting cloud formation. When cosmic rays enter Earth's atmosphere, they ionize molecules, creating charged particles that can act as seeds for cloud droplets. Clouds, in turn, affect Earth's temperature by reflecting sunlight and trapping heat. Although the extent of this effect is still debated, cosmic rays provide a subtle connection between distant cosmic events and our planet's climate system. This intriguing possibility highlights the delicate interplay between space and Earth's environment. Galactic movements follow the paths set by cosmic filaments. Galaxies don't drift aimlessly but move along gravitational currents defined by the cosmic web's filaments. These vast strands of dark matter and gas guide galaxies toward dense clusters and voids, shaping their trajectories over billions of years. This flow influences galaxy interactions, mergers, and evolution, forming the large-scale structure of the universe. Mapping these cosmic highways helps astronomers understand the forces shaping the universe's architecture and the dynamic motion of its constituents. Neutrinos offer clues about the universe's very beginnings. Neutrinos are tiny, nearly massless particles produced in vast numbers during the universe's earliest moments. These elusive particles decoupled from matter mere seconds after the Big Bang, streaming through space almost unimpeded ever since. While difficult to detect, relic neutrinos carry invaluable information about the universe's infancy, fundamental physics, and particle interactions at extreme energies. Studying neutrinos helps scientists probe conditions inaccessible by other means, providing a unique window into the cosmos's origin and the laws governing it. Some of those stars may have collapsed into the first black holes. The most massive of the first stars ended their short lives in collapse. Their gravity was so strong that when their fuel ran out, no force could stop them from imploding. Some exploded as supernova, leaving behind neutron stars, while others fell directly into black holes. These black holes were unique, not the corpses of ordinary stars, but the direct descendants of the first cosmic fire. They may have acted as seeds, growing over billions of years into the supermassive black holes that anchor galaxies today. If so, the brilliant quasars we see at the edge of the observable universe, powered by black holes a billion times the Sun's mass, may trace their lineage all the way back to those first collapsing stars born in the dawn of time. The Milky Way moves through space at over 1 million miles per hour. Though the night sky looks still, our galaxy is on a ceaseless journey. The Milky Way, along with its stars, planets, and nebulae, drifts through the cosmic web at more than 1 million miles per hour. This motion is partly the result of local gravitational pulls from nearby galaxies, from clusters, even from vast unseen structures. To us, it feels invisible, since everything around us moves together. But when astronomers measure the cosmic microwave background, they can see a faint dipole pattern, a subtle distortion caused by our galactic motion. It's a reminder that there is no absolute rest in the universe. Everything drifts, everything flows, carried along in the great cosmic tide. Superclusters of galaxies weave a cosmic web across the universe. Galaxies do not sit alone in space. They gather into clusters, and those clusters gather into larger structures, superclusters. These superclusters stretch for hundreds of millions of light-years, linked by filaments of galaxies and separated by vast cosmic voids. Together, they form the cosmic web, a pattern that resembles strands of a spider's web or the filaments of neurons in a brain. Our own galaxy lives within the Laniakea supercluster, a sprawling region that contains hundreds of thousands of galaxies. When we map these structures, we see not chaos, but elegance. Gravity sculpting luminous threads across the universe, revealing a hidden order that spans billions of light-years. Ancient quasars shine from less than 1 billion years after the Big Bang. Quasars are the beacons of the early universe, galaxies whose central black holes feed so voraciously that they blaze brighter than all their stars combined. Some quasars we see today come from less than 1 billion years after the Big Bang, when the cosmos was still young. To shine so brightly so soon, their black holes must have grown with astonishing speed, reaching masses of 1 billion suns in a fraction of cosmic history. These quasars act like lighthouses, illuminating the fog of intergalactic gas and helping us peer back into the reionization era, when galaxies first éclairent, carved light into the darkness. Their existence poses deep questions. How did black holes grow so fast, and what seeds gave rise to them? We may live in a local bubble of unusually empty space. Astronomers mapping the interstellar medium have discovered that our sun lies within a vast cavity, a bubble carved into the galaxy's gas. This local bubble stretches hundreds of light-years across and is unusually empty compared to its surroundings. It was likely created by a chain of supernova explosions millions of years ago, which blew away the surrounding material. Today, our sun and its neighbors drift quietly within this rarefied zone, bathed in a faint glow of hot plasma. The edges of the bubble form denser walls of gas and dust where new stars are born. To think that our solar system resides inside the lingering footprint of ancient stellar deaths adds a strange intimacy to our place in the cosmos. Dark matter may clump into invisible filaments that shape galaxies. When astronomers simulate the growth of the universe, they find that ordinary matter alone cannot form the patterns we see. Something unseen, dark matter, must weave invisible scaffolding beneath it all. In these simulations, dark matter clumps into filaments stretching across space, guiding the flow of galaxies into strands and knots. Our own Milky Way sits within one of these invisible filaments, like a dewdrop caught on a spider's thread. We cannot see the dark matter directly, but we see its gravity sculpting the grand architecture of the universe. Without it, galaxies would fly apart, and the cosmic web would unravel into scattered fragments. Actions, if they exist, could make up all dark matter. Dark matter's true identity is still unknown, but one candidate is the action, a hypothetical particle predicted by certain theories of quantum physics. Unlike heavy particles once imagined to explain dark matter, actions would be incredibly light, lighter even than neutrinos, that produced in such enormous cath. Numbers that together they could outweigh all the visible matter in the universe. Actions would interact so weakly that they slip through stars, planets, and even detectors unnoticed. Scientists have built experiments with ultra-sensitive magnetic fields and resonant cavities, hoping to catch even a whisper of these elusive particles. If found, actions would not only solve the dark matter mystery, but also connect cosmology with deep questions of particle physics. The laws of physics may be slightly different in other universes. Some versions of inflation predict that our universe is only one bubble in an endless multiverse. If so, the laws of physics may vary from bubble to bubble. In one, stars might never form because gravity is weaker. In another, atoms may not exist at all. Our own universe appears finely tuned, its constants balanced in a way that allows galaxies, chemistry, and life. It raises a haunting possibility. Perhaps we live in one universe among countless others, most sterile, some chaotic, but ours balanced just enough for complexity to bloom. Though we cannot see beyond our cosmic horizon, the idea that reality may be broader than our laws allows us to wonder at the fragile conditions that make existence possible here. Cosmic inflation could have spawned an infinite multiverse. In the theory of eternal inflation, the universe expands not as a single bubble, but as an endless froth. Regions of space stop inflating and form universes like ours, while other regions keep expanding, forever spawning new bubbles. Each bubble could be infinite in size, and together they form a multiverse without end. In this picture, the Big Bang was not the beginning of everything, but simply the birth of our local region. Other universes may lie forever beyond our reach, with their own physics, their own galaxies, and perhaps their own forms of life. It is a vision of reality so vast that even our observable cosmos, with its 2 trillion galaxies, would be just one small ripple on an endless cosmic sea. The universe once transitioned from opaque to transparent. For its first few 100,000 years, the universe was a fog of particles. Electrons and protons drifted free, scattering photons so completely that light could not travel. It was a glowing plasma, opaque to vision, with no way for radiation to move freely. Then, as the cosmos cooled, electrons settled into orbits around protons, forming the first atoms. Suddenly, photons were released, able to fly unhindered across space. In that instant, the universe became transparent, and the light we call the cosmic microwave background began its journey. Every time we measure that ancient glow, we are seeing the moment the universe first let light go free, a timeless afterimage of a cosmos lifting its summer, primordial veil. The reionization era lit up space with the first galaxies. After recombination, the universe was transparent but dark, filled only with neutral hydrogen gas. For hundreds of millions of years, there were no stars to shine. Then, slowly, the first galaxies ignited. Their newborn stars and quasars flooded space with ultraviolet light, energetic enough to break hydrogen back into ions. This period is called the reionization era, when the fog lifted once more, not by cooling this time, but by being pierced with light. Reionization carved great bubbles of transparency around the first galaxies until the whole universe was lit. When we observe distant galaxies and quasars today, we are catching sight of that moment when darkness gave way to cosmic dawn, and the universe became illuminated from within. The cosmic neutrino background has never been directly seen. We know of the cosmic microwave background, the light from when the universe became transparent. But before that, another background formed, a sea of neutrinos, released only seconds after the Big Bang. These ghostly particles still stream through space today, forming the cosmic neutrino background. Unlike photons, which were trapped for hundreds of thousands of years, neutrinos escaped almost instantly, carrying information from the universe's earliest heartbeat. Yet because they interact so weakly, we have never directly detected them. They flow through planets, stars, and our bodies, almost without trace. Instruments capable of catching even a faint echo are still being dreamed of. If one day detected, this neutrino background would be like opening a hidden window into the first second of existence itself. The most energetic particles in the universe may come from beyond our galaxy. Cosmic rays are high-energy particles that rain down on Earth, striking our atmosphere with invisible sparks. Most come from sources within our galaxy, like exploding stars. But some cosmic rays carry energies so extreme that no known event in the Milky Way could have launched them. These ultra-high energy cosmic rays may come from far beyond, perhaps the jets of distant quasars or collisions between galaxy clusters. Each particle travels for millions or billions of years, until by chance, it meets birth. When it strikes, it unleashes a cascade of secondary particles, momentary fireworks of invisible origin. Even now, we don't fully know what launches the most powerful particles in the universe, only that they come from somewhere far beyond our home galaxy. Black holes might merge often enough to reshape galaxies. Black holes are not always solitary. In galaxies where stars collide and clusters interact, black holes can be drawn into pairs. Over time, they spiral closer, radiating energy in gravitational waves until they finally merge. Each collision creates a single, larger black hole and a burst of space-time ripples. Over billions of years, these mergers may grow black holes at the centers of galaxies to enormous sizes. When they do, the energy released can alter the flow of gas, shaping star formation and influencing the structure of the galaxy itself. In this way, black hole mergers are not just rare fireworks, they are part of the quiet, ongoing architecture of the cosmos, chiseling galaxies into the shapes we see today. Gravitational waves carry whispers of ancient collisions. Einstein predicted them, and a century later, we finally heard them. Gravitational waves are ripples in spacetime created when massive objects like black holes or neutron stars collide. They stretch and squeeze space as they pass, though only by less than the width of a proton. With detectors like LIGO and Virgo, scientists have recorded dozens of these events, distant cataclysms billions of light years away, their whispers reaching us. Across cosmic time, each wave carries a signature, telling us about the size, mass, and dance of the objects that created it. And someday, if we can hear even fainter ones, we may catch the background hum of gravitational waves from the earliest universe, echoes of creation still rolling. Through space-time, the speed of cosmic expansion has changed more than once. The universe does not expand at a constant pace. In its first fractions of a second, inflation drove an almost unimaginable expansion, faster than light. After that, gravity slowed things down, as matter pulled against the outward flow. For billions of years, galaxies drifted apart at a gentle rate. But in the last few billion years, the expansion has sped up again, pushed by dark energy. This shifting pace tells us that the cosmos has gone through phases, each governed by the balance of forces and energies within it. From rapid inflation to slow deceleration to the present acceleration, the rhythm of expansion is like a cosmic heartbeat, changing with time, and still unfolding into an unknown future. Some stars may have formed directly from collapsing dark matter. Ordinary stars form from collapsing clouds of gas, but some theories suggest a stranger origin story: dark stars. In the early universe, dark matter may have clumped densely enough that its annihilation released bursts of energy. Instead of collapsing fully, these clumps could inflate into giant dark stars, powered not by fusion, but by dark matter itself. They may have been massive, glowing faintly with heat from within, but unlike ordinary stars, their light would have been almost invisible to us. If such stars existed, they could have been the first beacons of the cosmos, later collapsing into black holes that seeded galaxies. Though still hypothetical, the idea of stars born from the invisible matter of the universe gives a haunting glimpse of what might once have been. The cosmic microwave background is slightly lopsided. When we map the cosmic microwave background, the afterglow of the Big Bang, we find it is almost perfectly uniform. Almost, but not entirely. There is a slight asymmetry, a lopsidedness, with one side of the sky showing slightly stronger fluctuations than the other. This imbalance is puzzling, because the early universe should have been nearly the same in every direction. Some explanations suggest it is simply a statistical quirk. Others propose deeper causes, like hidden physics from inflation or even interactions with regions beyond our observable universe. Though subtle, this lopsidedness challenges our assumption that the cosmos is perfectly isotropic, and it keeps cosmologists searching for the hidden story behind this ancient light. A mysterious axis of evil aligns structures across the universe. Among the patterns of the cosmic microwave background, scientists have noticed something unusual: large-scale features that seem to align along a common axis in the sky. This alignment, strangely nicknamed the axis of evil, shouldn't exist if the universe is truly random and uniform at the largest scales. Even more puzzling, some of the largest cosmic structures, like galaxy distributions, seem to follow this same orientation. Whether it is a coincidence, a statistical fluke, or a sign of unknown physics, no one knows. The name may be playful, but the mystery is serious. Why should the universe, so vast and ancient, show a preference for any particular direction at all? The finer tuning of cosmic constants allows galaxies to exist at all. The universe is balanced on a razor's edge. The strength of gravity, the charge of the electron, the mass of fundamental particles. If any of these values were even slightly different, the cosmos would look nothing like it does today. Stars might never ignite, atoms might never form, or galaxies might collapse too quickly to allow life. This delicate balance is known as fine-tuning, and it fascinates cosmologists because it seems improbably precise. Some see it as a mystery to be explained by deeper laws of physics. Others suggest the multiverse, where countless universes exist with different values, and we live in the one where conditions happen to allow observers. Whatever the explanation, it is humbling to know that the entire visible universe, from the largest galaxy to the breath in your lungs, depends on the delicate tuning of timbre. Invisible constants written into the fabric of reality. Some physicists believe the universe is a hologram. It sounds like science fiction, but the holographic principle is a serious idea in theoretical physics. It suggests that everything in the universe, stars, galaxies, even ourselves, might be described not in 3 dimensions, but by information encoded on a distant 2-dimensional surface. Just as a flat hologram contains the illusion of depth, the cosmos we live in may emerge from data written on a cosmic boundary. This strange idea comes from studying black holes, where information appears to be stored on the event horizon rather than inside. If true for black holes, it could be true for the whole universe. The holographic principle doesn't mean reality is an illusion, but that space and time themselves may be emergent, shadows of a deeper, more fundamental layer of physics. Quantum fluctuations may have seeded every star and planet. In the smallest scales of reality, quantum physics rules. Particles flicker in and out of existence, and uncertainty is the law. During cosmic inflation, these tiny quantum fluctuations were stretched to cosmic scales, becoming slight ripples in the density of the universe. Over billions of years, gravity amplified those ripples, drawing matter into some regions more than others. From those seeds grew galaxies, stars, planets, and eventually, life itself. It is astonishing to realize that everything we see in the night sky, from the Milky Way to the most distant galaxy cluster, may have been born from microscopic bikar, quantum jitter amplified by the vast machinery of cosmic expansion. The entire universe, in a sense, rests on the chance tremors of the quantum world. Cosmic inflation could have created baby universes we'll never see. Inflation is the idea that the universe expanded faster than light in its first instant. But some versions of the theory suggest it didn't happen uniformly. Instead, while our region slowed down and became a universe, other regions may have continued inflating, forming their own universes. This process may happen endlessly, with baby universes budding off like bubbles in boiling water. Each one would be cut off from the others by expansion faster than any signal could cross. Some might follow laws of physics very different from ours. Others might look much the same, with galaxies and stars like our own. If true, our observable universe is just one blossom on an infinite cosmic tree, its countless branches forever hidden from one another, each carrying its own version of reality. There may be more galaxies in the observable universe than grains of sand on Earth. The number of galaxies is almost beyond imagination. Early estimates suggested hundreds of billions. But deep field images from telescopes like Hubble revealed far more. Counting carefully, cosmologists now think there may be 2 trillion galaxies in the observable universe. To give perspective, if you scooped up all the sand from every beach and desert on Earth, the grains would still fall short of the number of galaxies above. Each of those galaxies contains billions or trillions of stars. And each of those stars could host planets, moons, and perhaps life. The scale is so immense that even the word infinite feels close at hand. When we gaze at the night sky, we see only the faintest sprinkling of the cosmic ocean, a handful of nearby sparks among an overwhelming abundance. Some regions of space may have negative energy density. In most of the universe, energy is positive, tied to matter, radiation, and motion. But in quantum field theory, there are scenarios where the energy of space itself could dip below zero, creating regions of negative energy density. These exotic states are not like ordinary emptiness. They could warp spacetime in unusual ways, potentially allowing shortcuts like wormholes or even stable warp bubbles. Though still theoretical, negative energy has been glimpsed in tiny effects, such as the Casimir force between closely spaced plates in a vacuum. If it can exist in small ways, perhaps it can exist in larger cosmic contexts. Negative energy density could be one of the strangest hidden features of the universe, rare, fleeting, but profound enough to reshape our understanding of what nothing really means. Primordial black holes could explain dark matter. Dark matter remains one of the great mysteries of cosmology, invisible, undetectable except by its gravity. One possibility is that dark matter isn't made of particles at all, but of black holes formed in the first moments after the Big Bang. These primordial black holes could range in size from asteroids to stars scattered throughout the cosmos. Unlike ordinary black holes, they would not be the end state of dying stars, but fossils of the universe's earliest fluctuations. If enough of them exist, they could account for all the dark matter we see shaping galaxies and clusters. Detecting them would not be easy. They could drift unseen through space, giving themselves away only through rare gravitational effects. If confirmed, primordial black holes would tie two of the universe's greatest mysteries together in a single explanation. A single photon could, in theory, stretch across the whole universe. Photons, the particles of light, are described by waves. And in principle, a single photon's wave can extend indefinitely, stretching across vast distances. In the expanding universe, light from the earliest times has been redshifted to longer and longer wavelengths. Some of the photons from the cosmic microwave background now have wavelengths measured in millimeters, small, but not infinitely so. In theory, though, a photon could be spread so thin that its wave function spans the entire observable universe. This is not something we can observe directly, but it shows how strange quantum mechanics becomes on cosmic scales. Even a single particle of light might not be local, but universal, rippling silently across billions of light years. Entropy ensures the cosmos will one day reach heat death. Entropy is the tendency for systems to move from order to disorder. On Earth, it's why energy disperses and why things break down over time. On the scale of the cosmos, entropy ensures that stars will eventually burn out, galaxies will drift apart, and usable energy will vanish. In the far future, trillions upon trillions of years from now, the universe may reach heat death, a state where all is cold and uniform, with no gradients. Left to drive change. It is not a fiery ending, but a fading, a slow dissolution into silence. Though it sounds bleak, it is also deeply peaceful, a universe that once blazed with energy, gently settling into perfect stillness. Vacuum decay could, in principle, erase the universe instantly. According to some interpretations of particle physics, the vacuum state of our universe may not be perfectly stable. If it is metastable, then one day, perhaps in billions of years, perhaps tomorrow, a tiny bubble of true vacuum could fall. Expanding at nearly the speed of light, it would erase everything it touched, rewriting the laws of physics as it spread. We would never see it coming. The change would arrive faster than light could warn us. Though the idea sounds terrifying, it is largely hypothetical, and even if possible, the timescales are so vast as to be irrelevant to human existence. For now, it remains one of cosmology's most haunting possibilities, that reality itself may not be permanent, but a delicate balance that could, in principle, collapse. Cosmic rays constantly shower Earth with particles from distant space. Every moment, invisible particles from space rain down on Earth. These are cosmic rays, high-energy fragments of atoms launched by distant supernova, pulsars, or even galaxies far away. Most pass through unnoticed, striking our atmosphere and scattering into showers of smaller particles. Some are so energetic that they challenge our understanding of physics, carrying more power than any particle accelerator on Earth can produce. You are touched by them constantly. They slip through your body, through oceans, even through mountains. In fact, a tiny fraction of the noise in old film photography comes from cosmic rays striking the film. They are a reminder that Earth is not isolated, but bathed in a steady drizzle of particles born in the most violent corners of the universe, still reaching us, across immense spans of time and space. The observable universe is only a fraction of the whole. When we look out into the cosmos, the most distant light we can see comes from around 13.8 billion years ago. Yet because space has been expanding, the observable universe stretches much farther, about 93 billion light-years across. But this is not the full universe, only the patch we can see. Beyond it lies more space, perhaps infinitely more, hidden behind the cosmic horizon. Entire galaxies, clusters, even colossal structures may lie forever outside our reach. Some theories suggest our observable universe is like a bubble in a vast inflating ocean of space. Others imagine countless bubbles, each sealed from the rest. Whatever lies beyond, we may never know. And yet, just knowing the universe is larger than what we see fills the night sky with mystery. Galaxy clusters collide in slow-motion cosmic crashes. Clusters of galaxies are the largest bound structures in the universe, containing hundreds or thousands of galaxies, plus immense clouds of hot gas. When they collide, the process is slow, lasting billions of years. Galaxies usually pass through without colliding because space between stars is vast. But their hot gas clouds slam together, heating up and glowing in X-rays, while dark matter halos glide past almost undisturbed. These collisions reshape the clusters, mixing their contents and altering their structures. Some galaxies may be stripped of gas, leaving them to fade into silence. Seen across cosmic time, cluster mergers are like continental drift on Earth, but on unimaginable scales, slow, inexorable, and transformative, sculpting the architecture of the universe. The bullet cluster provides direct evidence for dark matter. One of the strongest clues for dark matter comes from an extraordinary collision called the bullet cluster. Two galaxy clusters passed through each other, and astronomers studied the aftermath. The visible gas, which carries most of the normal matter, slowed down and piled up, glowing brightly in X-rays. But the galaxies themselves, and more importantly, the gravitational mass revealed by lensing, kept moving ahead. This showed that most of the mass was not in the hot gas, but in something invisible, dark matter. The bullet cluster has become a cosmic laboratory, a snapshot proving that unseen matter outweighs the stars and gas we can see. It is one of the clearest, most compelling windows into the existence of the invisible scaffolding that holds the universe together. Some galaxies are so faint they're almost invisible. Not every galaxy glitters brightly in the night sky. Some, called ultra-diffuse galaxies, spread their stars so thinly that they look more like faint smudges than luminous cities of stars. These galaxies may be as large as the Milky Way, but with only a fraction of the stars. They are ghostly, difficult to detect, and often discovered only through sensitive surveys. Some appear to be rich in dark matter, while others strangely seem to lack it almost entirely. Their faintness makes them fragile, easily disrupted by interactions with larger galaxies. Yet their existence reveals that galaxies come in more varieties than we once imagined, from blazing spirals to nearly invisible shadows drifting quietly through the cosmic web. Giant elliptical galaxies may be the fossils of countless mergers. While spiral galaxies like the Milky Way are graceful and structured, elliptical galaxies are huge, rounded, and often dull in appearance. Yet their simplicity hides a dramatic past. Astronomers believe giant ellipticals are the products of countless mergers. Over billions of years, galaxies collide and combine, their orderly spirals shredded into amorphous shapes. Star formation slows as gas is consumed or stripped away, leaving behind old, red stars glowing faintly. These galaxies can grow to incredible sizes, containing trillions of stars. In galaxy clusters, they often dominate the center, like massive fossils of an ancient and violent history. To gaze at one is to see not a quiet giant, but the faded memory of countless galactic collisions, written into its smooth, rounded glow. The universe may be shaped by physics we haven't discovered yet. Our best models explain much of what we see, but cosmology still leans on mysteries. Dark matter and dark energy, which together make up 95% of the universe, remain unidentified. Inflation, the theory that explains the cosmos's early rapid expansion, still needs a mechanism. And quantum gravity, The unification of general relativity and quantum mechanics has yet to be found. It may be that new physics, undiscovered laws, underpin the entire structure of the universe. Each telescope, each experiment, pushes closer to the edge, hinting that reality may rest on foundations we have not yet glimpsed. For now, cosmology stands as a bridge between the known and the unknown, a map sketched partly in discovery and partly in mystery. Wormholes are allowed by relativity, but may never form naturally. Einstein's equations admit strange solutions, tunnels through spacetime, connecting distant regions or even different universes. These wormholes are a staple of science fiction, but they are also legitimate possibilities in general relativity. However, for a wormhole to remain open, it would require exotic matter with negative energy, something we have never seen in large amounts. Without it, wormholes collapse instantly, becoming impassable. Still, they remain a tantalizing thought experiment. A cosmos where shortcuts exist, hidden corridors through the deep fabric of spacetime. Even if nature never built one, wormholes remain a reminder that relativity does not just describe the universe we see, but also strangers. Possibilities that stretch imagination itself. The cosmic web resembles the neural structure of a brain. When scientists map the large-scale structure of the universe, they find galaxies arranged in filaments, knots, and voids, a pattern known as the cosmic web. Strikingly, this structure resembles the network of neurons in a brain. Both systems balance nodes and connections in a way that maximizes efficiency of flow. In the brain, it is electrical signals; in the cosmos, it is matter and gravity. The resemblance is not just visual, mathematically. The two networks share similar properties. To think that the universe, on its largest scales, echoes the same architecture as the mind that contemplates it, is a poetic coincidence, a reminder that patterns repeat, from the smallest sparks of thought to the vast sweep of galaxies. Supervoids may cause subtle distortions in cosmic light. A supervoid is an immense, underdense region of space, larger and emptier than ordinary voids, spanning hundreds of millions of light years. Though nearly empty, they still influence the light passing through them. Photons traveling across a supervoid lose a little energy, slightly cooling by the time they reach us. This subtle effect, known as the integrated Sachs-Wolf effect, leaves faint imprints on the cosmic microwave background. One possible explanation for the mysterious cold spot is that light passed through such a supervoid on its journey to Earth. Though invisible themselves, supervoids may shape the universe's faintest signals, reminders that even emptiness can leave fingerprints on the oldest light. Some galaxy clusters contain hot gas that outweighs their stars. When astronomers study galaxy clusters, they find that the stars we see make up only a fraction of their mass. Much of the visible matter is locked not in stars, but in immense clouds of superheated gas. This gas glows in X-rays, reaching temperatures of tens of millions of degrees, and it outweighs all the stars in the cluster combined. The gas is held in place by the cluster's gravity, filling the space between galaxies like an invisible ocean. Without X-ray telescopes, we would never know it was there. Its sheer mass reveals that galaxies are not isolated islands, but members of vast ecosystems, immersed in hot, glowing atmospheres. In a sense, the stars are just the brightest sparks within an even greater sea of matter. Black holes may influence the fate of entire galaxies. Though tiny compared to galaxies, black holes at their centers wield enormous power. When they feed, matter spirals inward, heating up until it releases torrents of radiation and powerful jets. These outbursts can blow gas out of the galaxy, shutting down star formation, or stir it, triggering new stars to form. Over billions of years, the activity of a single supermassive black hole can regulate the growth of its host galaxy. Observations suggest that the mass of central black holes and the properties of galaxies are tightly linked, as if they grew together, shaping one another's destiny. Black holes, once thought to be destructive outliers, are now seen as key architects of the cosmic landscape. Time may pass at different rates in different cosmic regions. Einstein's theory of relativity showed that time is not absolute. It bends and flexes with gravity and motion. In regions near massive objects, time passes more slowly. In emptier, weaker gravity regions, it passes faster. On cosmic scales, this means the flow of time may differ slightly from place to place. Even the expansion of the universe itself stretches time, altering the pace at which distant galaxies evolve compared to our local frame. When we look at the cosmos, we are not just peering across space, but across different rivers of time, each flowing at its own tempo. The night sky is therefore not a single snapshot, but a patchwork quilt of timescales woven together into the cosmic story. The speed of light sets a limit on what we can know. Light is fast, nearly 300,000 kilometers per second, but it is not infinite. Because of this, we see distant galaxies not as they are today, but as they were billions of years ago. The farther we look, the further back in time we reach. The speed of light creates a natural boundary to our knowledge, the cosmic horizon. Beyond it, light has not yet had time to arrive. This limit is not just technological, but fundamental. No future telescope can reveal what lies past it. We live within this light-bound bubble, able to peer into the past, but never beyond a certain edge. The speed of light, so constant and universal, becomes not just a property of physics, but a cosmic boundary on human understanding. The Planck era, the universe's first fraction of a second, remains a mystery. Cosmologists can describe the universe from a fraction of a second onward, but the very first instant, known as the Planck era, remains hidden. In this unimaginably brief sliver of time, less than 1/10 million trillion trillionth of a second after the Big Bang, the universe was so hot and dense that our current physics breaks down. Gravity, quantum mechanics, and energy were entwined in ways we cannot yet model. To understand this era would require a complete theory of quantum gravity, uniting relativity with the quantum world. For now, the Planck era is a blank space on our cosmic timeline, the hidden prologue of the universe's story. Whatever happened then determined everything that followed, yet it remains one of the deepest mysteries in all of science. Hawking radiation could one day evaporate black holes. Black holes seem like eternal prisons, swallowing everything that comes too close. But Stephen Hawking showed that they are not perfectly black. Quantum effects near the event horizon allow them to emit tiny amounts of radiation. Over unimaginable timescales, this Hawking radiation slowly saps their mass. For stellar black holes, the process is far too slow to matter now. But given trillions upon trillions of years, they will eventually evaporate entirely, leaving behind nothing but faint radiation. Even the supermassive black holes at the hearts of galaxies will one day fade away. In the far future, when the stars have burned out, Hawking radiation will be the last whisper of the cosmos. Black holes gently dissolving into silence. White holes are a possible mirror image of black holes. If black holes are regions where nothing can escape, then white holes are the opposite, regions where nothing can enter. They are mathematical solutions to Einstein's equations, mirror twins of black holes. A white hole would spew matter and light, but resist anything trying to cross its horizon. None have ever been observed, and most physicists doubt they exist in nature. Still, they are fascinating hypotheticals. Some theories even suggest black holes could transform into white holes at the end of their lives, releasing information back into the universe. Though purely speculative, white holes are reminders of how strange and flexible relativity can be, allowing possibilities that stretch the imagination far beyond the familiar. Some theories predict a cyclic universe that dies and is reborn. Not all cosmologists believe the universe began once and for all with the Big Bang. Some models suggest a cycle: expansion, collapse, and rebirth. In this view, the universe grows for billions of years, then slows and reverses, collapsing back into a big crunch. From that collapse, a new Big Bang might arise, beginning another cycle. This idea is ancient, echoed in myths of eternal return, but it also has modern scientific versions. Though evidence for a cyclic universe is uncertain, the possibility is haunting. That the cosmos is not a singular story, but an endless loop of deaths and rebirths, each universe following another, perhaps forever. A big crunch could one day reverse cosmic expansion. If the pull of gravity is strong enough, it could eventually halt the expansion of the universe and reverse it. Galaxies would slow, then begin to collapse inward, the cosmos shrinking back on itself. Stars would crowd closer, galaxies would merge, and temperatures would rise. Eventually, everything would converge in a final collapse, a big crunch, undoing the Big Bang. For now, evidence suggests the opposite, that expansion is accelerating under dark energy. But the Big Crunch remains one possible fate, a cosmic implosion that would erase the universe we know, perhaps setting the stage for something new. The Big Bounce could mean our universe is not the first. Some cosmologists combine the ideas of the Big Bang and the Big Crunch into a larger cycle, the Big Bounce. In this model, each universe collapses, then rebounds into expansion again, like a heartbeat of creation. If true, ours is not the first universe, but just the latest in an endless chain. Each bounce may leave traces, imprinted in the cosmic microwave background as subtle patterns or asymmetries. The Big Bounce offers a comforting symmetry, creation and destruction as part of an eternal rhythm, with no true beginning or end. It is speculative, but beautiful, the cosmos breathing in and out forever, with our universe as just one breath among infinite others. Cosmic background radiation once glowed bright orange in the sky. The cosmic microwave background is faint today, just a whisper of cold light at 3 degrees above absolute zero. But in the early universe, it would have looked very different. Billions of years ago, this radiation was still warm enough to glow in visible light. Had we been there, the entire sky would have shone with a fiery orange glow, a uniform radiance stretching in every direction. Over time, as the cosmos expanded, the light stretched to longer wavelengths, cooling into the invisible microwaves we see today. That ancient orange glow was the universe itself shining before stars, before galaxies, a cosmic dawn painted not by suns, but by spacetime itself. The universe cooled as it expanded, allowing atoms to form. At first, the cosmos was too hot for atoms to exist. Electrons and protons roamed freely, unable to bind together. But as the universe expanded, its temperature dropped. Around 380,000 years after the Big Bang, conditions became cool enough for electrons to join with protons, creating gwath, hydrogen atoms. With atoms stable, light could travel freely, releasing the cosmic microwave background. This cooling marked the end of the universe's childhood chaos, the moment matter began to take form. Every atom of hydrogen in your body today, every atom in water, in air, in stars, is a direct descendant of that cooling, when the cosmos first settled into Set. Structure. Matter barely won over antimatter in the beginning. In the earliest moments of creation, particles of matter and their antimatter twins were produced in nearly equal amounts. When they meet, matter and antimatter annihilate, leaving behind only energy. Had the amounts been perfectly equal, the universe today would contain no galaxies, no stars, and no people, only light. But somehow, matter held the slightest advantage, outnumbering antimatter by just one particle in a billion. That tiny imbalance became everything: the stars, the planets, the oceans, and even us. The mystery of why matter triumphed is still unsolved, but the fact that it did is why anything exists at all. Without that imbalance, no galaxies would exist. It is hard to imagine how fragile reality is. If matter and antimatter had been perfectly symmetrical, their mutual destruction would have erased all substance. The universe would be a thin haze of radiation, glowing forever without form. No stars would ignite, no galaxies would assemble, no planets would form, and no life could arise. Every structure in existence rests on that 1/1000th advantage of matter. We owe our very being to a cosmic imperfection, a tiny skew in the balance that gave atoms, and thus worlds, a chance to exist. The universe as we know it is built not on symmetry, but on the smallest possible break from it. Inflation predicts the universe is nearly perfectly flat. Inflation, the theory that the universe expanded faster than light in its first instant, has another surprising consequence. It smooths and flattens spacetime. Just as blowing up a balloon makes its surface appear flatter from up close, inflation stretched the fabric of the cosmos so greatly that today it appears nearly ET, perfectly flat on observable scales. Measurements of the cosmic microwave background confirm this with exquisite precision. To within fractions of a percent, the universe shows no detectable curvature. Whether this flatness extends beyond our horizon or whether the larger universe curves gently like a hidden sphere remains unknown. But in our cosmic neighborhood, inflation left behind a universe astonishingly straight and balanced. Dark flow hints at influences beyond our cosmic horizon. Astronomers studying the motion of galaxy clusters discovered something strange. Many seem to be drifting in the same direction, faster than expected, as though pulled by something beyond the observable universe. This large-scale motion has been nicknamed dark flow. One explanation is that massive structures exist outside our horizon, their gravity tugging on galaxies across billions of light years. If true, dark flow is not just motion, but evidence that our observable bubble is part of a larger reality, with hidden giants shaping what we see. Though still debated, the idea that unseen structures beyond our cosmic edge are influencing us adds a haunting depth to the night sky. The integrated Sachs-Wolf effect reveals dark energy's fingerprints. Light from the cosmic microwave background does not travel through empty space. It weaves past galaxies, clusters, and vast structures, gaining and losing energy as it moves through gravitational wells. In a universe without dark energy, the balance of gains and losses would cancel perfectly. But observations reveal a small leftover signal, the integrated Sachs-Wolf effect. This tells us that gravitational wells are changing as the universe expands, stretched by dark energy. In this faint way, the invisible hand of dark energy leaves fingerprints on the oldest light. By studying these subtle imprints, scientists confirm not only that dark energy exists, but that it has been shaping the universe for billions of years. The cosmic microwave background once fit inside your hand. Today, the cosmic microwave background fills the entire observable universe, spanning 93 billion light-years. But when that light was first released, the universe itself was only about 1 million light-years across, small enough, in cosmic terms, to fit within your hand. Imagine cradling the whole universe, glowing hot and dense, a sphere of plasma ready to expand into everything we know. That light has traveled ever since, stretched and cooled by expansion, but still present, still whispering its story across the sky. To think that the cosmos we inhabit was once so small is almost impossible, and yet, in its earliest moments, everything really did fit into a graspable whole. Some ancient stars may still burn from the dawn of time. Most of the first stars were massive and short-lived, but a few may have been small, faint, and long-lasting. Stars with very low mass can burn for trillions of years, far longer than the current age of the universe. If any such stars formed in the early cosmos, they could still be shining today. They would be dim, red, and difficult to spot, hidden among the countless younger stars around them. But if found, they would be living fossils of the cosmic dawn, stars that witnessed the birth of galaxies, the rise of black holes, and the long unfolding of cosmic history. Somewhere in the night sky, a faint red ember may still glow, older than any other star we have ever seen. The universe may still echo with the first gravitational waves. Gravitational waves are ripples in spacetime, and some of the first may have been produced during cosmic inflation. These primordial waves would have been stretched across the universe, leaving faint imprints in the polarization of the cosmic microwave background. Detecting them would be like hearing the faint sound of creation itself, vibrations from the universe's earliest instant, still ringing today. Though they remain elusive, experiments continue to search for this background hum. If discovered, these waves would confirm inflation and give us direct evidence of physics at energies we can never reproduce on Earth. The cosmos itself would become the laboratory, still echoing with its birth. The scale of cosmic expansion stretches light into red. As the universe expands, it stretches not only space, but the very light that travels through it. Photons moving across billions of years are pulled to longer, redder wavelengths. This cosmological redshift is how we measure distance to galaxies. The farther they are, the more their light has been stretched. It means that the night sky is a time machine, its colors stretched by the breathing of the cosmos itself. A galaxy that once shone blue may now arrive at our telescopes in shades of red, its energy diluted by expansion. Each photon in your eye tonight is an ancient traveler, drawn out like a musical note played slower and lower, carrying the story of distance, time, and the Tao. Universe's restless growth. Olber's paradox asks why the night sky is dark. If the universe were infinite, filled uniformly with stars, the night sky should blaze with light in every direction. This simple thought experiment, known as Olber's paradox, puzzled thinkers for centuries. Why then is the sky dark at night? The answer lies in two facts. The universe has a finite age, and it is expanding. Because stars have not existed forever, their light has not had time to fill the sky. And because expansion stretches light into faint, invisible wavelengths, much of it fades beyond our sight. The darkness between the stars is therefore not emptiness, but a canvas painted by time and distance. The night sky glows only with what has had time to reach us. The answer lies in cosmic expansion and finite age. The darkness of the night is not a flaw, but a clue. Expansion means that galaxies recede faster the farther away they are, their light redshifted into invisibility. Finite age means that light from the most distant regions has not yet arrived. Together, these two principles resolve Olber's paradox. The universe is not static nor eternal, but dynamic and young compared to infinity. Each patch of blackness above you is a veil, hiding regions too far or too early for their light to reach. The starless dark is not empty, but alive with light still on its way, destined to arrive only after billions more years have passed. The universe may have begun as a quantum fluctuation. In the strangeness of quantum physics, empty space is never truly empty. Tiny fluctuations in energy constantly arise and vanish. Some theories suggest that the entire universe may have sprung from one such fluctuation, a quantum tremor magnified by inflation into a cosmos. If so, our universe is not an exception, but a natural outcome of physics itself, a possibility realized among infinite quantum rolls of the dice. The idea that everything we see, galaxies, stars, and life, grew from a microscopic flicker of energy is both humbling and awe-inspiring. It means the grandest scales of existence may be rooted in the smallest whispers of quantum chance. Vacuum energy could drive inflation and dark energy alike. Vacuum energy is the background energy of empty space. Though invisible, it may be one of the most important forces in the cosmos. In the earliest fraction of a second, vacuum energy could have driven inflation, stretching the universe unimaginably fast. Today, it may appear again in another guise, as dark energy, the mysterious pressure accelerating cosmic expansion. If these two are truly connected, then the same energy that sparked the birth of the universe still drives its future, linking the dawn of time to the deep tomorrow. What we call nothing may be the most powerful something of all. Black holes may encode information on their surfaces. A paradox arises with black holes. When matter falls in, does its information vanish? Physics insists that information can never be lost, but black holes seem to swallow it beyond recall. One possible resolution is that black holes store information not inside, but on their event horizons, encoded in subtle patterns of quantum states. This idea reframes black holes not as bottomless voids, but as cosmic hard drives, their surfaces shimmering with hidden codes. If true, black holes preserve the record of everything they consume, woven into their horizons like runes on the fabric of spacetime. The holographic principle suggests reality is two-dimensional at heart. Building on the idea of black hole information, some physicists propose the holographic principle that the three-dimensional universe we experience may be a projection of data encoded on a two-dimensional surface. Just as a hologram carries 3D depth in a flat image, the cosmos itself could emerge from information written on its boundaries. If true, everything we see, stars, galaxies, even ourselves, might be a kind of holographic unfolding. This radical idea ties together gravity, quantum mechanics, and information theory, hinting that the deepest layer of reality may be less like substance and more like code. The cosmic web keeps growing as galaxies drift apart. The universe's large-scale structure resembles a web, strands of galaxies linked by filaments of dark matter with vast voids between them. Over billions of years, this web has stretched and expanded, but it continues to evolve. Gravity draws galaxies along the filaments, while dark energy pushes the web outward, thinning it. As time goes on, clusters grow denser, voids grow emptier, and the contrast sharpens. The cosmic web is not fixed, but alive, slowly sculpting the fate of galaxies within it. Even now, our own Milky Way drifts along its strand, part of a larger, growing pattern. Galaxy filaments can stretch for 500 million light-years. Among the most breathtaking structures in the universe, are galaxy filaments, rivers of galaxies flowing together across unimaginable distances. Some of these filaments extend for 500 million light-years, binding thousands of galaxies in a single chain. Within them, galaxies cluster like pearls on a string, their motions guided by the invisible scaffolding of dark matter. To see them mapped is to glimpse the universe's skeleton, the architecture on which all else is built. These filaments reveal that galaxies are not scattered randomly, but woven into vast structures that span the cosmos like threads of an infinite tapestry. Some of the most distant quasars are powered by billion solar-mass black holes. Quasars are among the brightest objects in the universe, outshining entire galaxies. They are powered by black holes feeding voraciously at their centers, converting matter into light with extraordinary efficiency. What amazes astronomers is that we see quasars from the universe's earliest billion years already powered by black holes with masses of 1 billion suns. How such giants formed so quickly remains one of cosmology's greatest puzzles. Did they grow from smaller seeds far faster than expected? Or were they born massive, collapsing directly from primordial gas? Each distant quasar is a beacon from the dawn of time, its brilliance powered by a monster that defies our understanding. The universe once glowed with plasma hotter than stars. In its earliest era, the universe was not cold and dark, but dazzling. It burned with plasma, a roiling soup of charged particles far hotter than the core of any star. Atoms could not exist, yet protons and electrons flew free, colliding in a constant storm. Light itself was trapped, scattering endlessly, unable to travel in straight lines. Imagine space filled with brilliance, but no clear view, just a glowing fog that stretched in every direction. This state lasted for hundreds of thousands of years, defining the young cosmos. It was a time of blinding heat and pressure, before structure, before galaxies, before even atoms could take shape. Only when expansion cooled this plasma did the universe settle into a gentler form, letting light finally roam free. Every star we see today is just a faint echo of that first all-encompassing brilliance. Recombination ended that plasma age, making space transparent. Around 380,000 years after the Big Bang, the temperature of the cosmos had dropped enough for a profound change. Electrons and protons could finally come together, forming neutral hydrogen atoms. This transition, called recombination, was like a clearing of fog. With no free electrons left to scatter photons, light suddenly had a clear path. For the first time in cosmic history, space became transparent. Photons that had been endlessly bouncing could stream outward, beginning their long journey across the cosmos. That ancient radiation is what we detect today as the cosmic microwave background, the oldest light in the universe. It is as though the cosmos took its first deep breath, opening a window to the future. To look at the microwave background is to see the moment when the universe's blazing fog parted, and the first beams of light were finally free to travel forever. The cosmic microwave background is nearly uniform to 1 part in 100,000. When scientists map the microwave background, they see a glow so astonishingly smooth, it almost defies belief. Its temperature varies by only 1 part in 100,000, a level of uniformity unmatched anywhere else in nature. This nearly perfect evenness tells us that the young universe was mixed and blended to an extraordinary degree, as if every corner had been stirred together in chow. Harmony. And yet, hidden in that perfection are the tiniest ripples, faint differences of density and heat. Those almost invisible variations would one day grow into galaxies, clusters, and the great cosmic web. The microwave background shows us two truths at once: a universe astonishingly balanced, and a universe seeded with just enough difference to allow creation. Without that delicate balance between sameness and variation, the cosmos might have remained forever featureless. Those tiny differences seeded galaxies. The early universe was nearly uniform, but not perfectly so. In some places, the density was ever so slightly higher. Gravity amplified those tiny differences, pulling matter inward, allowing clumps to form. Over millions of years, those clumps grew into clouds, then stars, then entire galaxies. It is extraordinary to think that the vast spiral arms of the Milky Way and the clusters of galaxies we see in the night sky began as faint ripples in the fabric of the sapphire young cosmos. Without them, there would have been no structure at all, no stars to shine, no planets to orbit them, no life to wonder about it all. The richness of the universe, its galaxies, nebulae, and everything we see was written in the faintest whisper of unevenness at the dawn of time. Creation itself began with imperfection. Inflation could explain why distant parts of the universe look alike. One of the strangest mysteries in cosmology is why the universe looks so uniform across regions that are impossibly far apart. Opposite ends of the sky are billions of light years away, yet their conditions match almost exactly. How could they have ever communicated to become so similar? Inflation offers an answer. In the first fraction of a second after the Big Bang, space itself expanded faster than the speed of light, stretching tiny, connected regions into the vast universe we see today. Those regions once shared heat and information, and inflation carried that sameness across unimaginable distances. In a blink, the cosmos grew from smaller than an atom to larger than a galaxy. The fingerprints of that incredible expansion remain imprinted in the microwave background, a silent memory of the universe's wildest instant. The cosmic horizon keeps expanding, but light speed keeps us bounded. Every day, light from galaxies that were once hidden finally reaches us, slowly extending the boundaries of the observable universe. The cosmic horizon grows, revealing more of the story. And yet, there is a limit written into the laws of physics. Light has a finite speed, and space itself is expanding ever faster. Galaxies beyond a certain distance recede from us more quickly than their light can travel, slipping forever out of reach. That boundary, the cosmic horizon, is not made of walls or edges. It is simply the limit of what light has had time to show us. The universe beyond may be infinite, but we will never see it. The horizon keeps expanding, but so too does what lies beyond it. We are forever inside a bubble of knowledge, peering outward, while the vast majority of the cosmos lies beyond our sight. Entanglement may link particles across cosmic distances. Quantum entanglement defies ordinary intuition. When two particles are entangled, their states remain connected no matter how far apart they drift. A change in one is reflected instantly in the other, as though they share a hidden bond beyond space and time. Some scientists suggest this phenomenon may not be confined to small scales. It could be woven into the very structure of the universe, connecting regions of space across unimaginable distances. Entanglement may even provide a bridge between quantum mechanics and gravity, helping to explain how space-time itself emerges. If this is true, then the cosmos is threaded with invisible links, binding stars, particles, and perhaps even galaxies in a subtle quantum fabric. To live in such a universe is to exist in a web of connections deeper than distance, a cosmos where separation may only be an illusion. Space-time itself may be emergent from quantum information. We tend to think of space and time as the foundation of reality, the backdrop against which everything unfolds. But some physicists suggest they may not be fundamental at all. Instead, space-time might emerge from patterns of quantum entanglement and information, as though the universe were woven from invisible threads of data. In this view, geometry, distance, and even gravity are large-scale effects born from countless microscopic exchanges of information. The cosmos would not be a stage, but a story written in code, with space-time as its unfolding plot. If true, then our universe is more like a hologram than a solid object, a grand projection of hidden relationships. The deepest layer of reality might not be matter or energy, but information itself, endlessly recombining to give rise to the world we know. The universe is still ringing faintly with primordial vibrations. Long ago, the young universe was filled with sound, pressure waves moving through the hot plasma like ripples in a vast ocean. Those waves left their imprint, freezing into the structure of matter as the cosmos cooled. Today, we still see their faint signature in what are called baryon acoustic oscillations, enormous ripples in the clustering of galaxies. They stretch across hundreds of millions of light years, like the frozen echoes of creation. To measure them is to hear the aftersound of the universe's first moments, a cosmic hum that continues to shape structure even now. Though no ear can hear it, the cosmos is still ringing with vibrations from its birth, faint yet enduring, carrying across billions of years. We may never know whether our cosmos is the only one. The multiverse is one of the most tantalizing ideas in science. Inflation, they have created not just one universe, but countless bubbles, each with its own laws of physics. Quantum theory hints at branching realities, while black hole models suggest new universes might bloom on the far side of collapse. Yet by definition, these other universes may lie forever beyond our reach, cut off by horizons we cannot cross. Perhaps our cosmos is one of many, or perhaps it is truly unique. We may never know, and that uncertainty is part of its beauty. The fact that the universe inspires such questions, that it invites us to wonder about realities beyond our own, is itself a profound gift. To live in a cosmos that holds mystery is to live in a place where imagination and science meet, stretching toward infinity together. The universe might contain regions forever hidden from us. Beyond the limits of what we can see, the universe expands into regions whose light will never reach us. Those distant regions are not just far away, they are cut off by the finite speed of light and the way space itself expands. Even if we built perfect instruments and waited longer than any human lifetime, some parts of reality would still remain out of reach. In those unseen domains, matter could arrange itself into galaxies and structures that never send a single photon in our direction. Physics might follow the same rules we know, or twist them in subtle ways we cannot check. When we look at the night sky, we are staring at a small patch of a much larger whole, knowing that there are events happening right now that no one here will ever witness. The universe may be full of stories that will forever remain untold. There could be entire realms of space with different laws of physics. Many modern theories suggest that what we call the laws of nature may not be uniquely fixed. Certain ideas in cosmology and fundamental physics allow constants like particle masses and interaction strengths to take different values in different kami, regions of a larger reality. In one cosmic domain, stars might never ignite. In another, atoms might be unstable, or entirely different kinds of matter might form. We only know the behavior of our own patch, where the numbers happen to support long-lived stars and complex chemistry. It is possible that beyond any horizon, there are expanses where even the idea of a stable atom would be impossible. Our familiar physics could be a local dialect spoken in a much larger landscape of possibilities. If that is true, then what we call fundamental might be more like a regional custom, one example among many, with no way for us to visit the others and compare. We still do not know what happened before the first moment of time. Our best cosmological models describe how the universe evolved from an early hot and dense state, but they do not fully explain what, if anything, came before. At very early times, gravity and quantum physics must both matter, yet we do not yet have a single theory that combines them consistently. When we run the equations backward, they eventually stop giving meaningful answers, as if the mathematical surface of time itself ends. Some proposals suggest a prior contracting phase, others imagine a bounce, and some describe time as emerging from something more primitive that does not resemble prey. Ordinary before and after. Observations of the sky give us clues about the early fireball, but they cannot directly pierce whatever lies beyond that veil. The question of a beginning may even be the wrong way to think about it, yet our minds are drawn to it. What does it mean for time to start? And can there ever be a reason for the first instant? Space might be infinite, or it might loop back on itself. When we look out into the cosmos, we can measure how space is curved on vast scales, but those measurements do not yet tell us the global shape of everything. One possibility is that space extends without limit, stretching on forever with no boundary and never returning to where it started. Another is that space has a finite volume but no edge, like the surface of a sphere generalized into more dimensions, so that if you could travel far enough in one direction, you might eventually return to your starting point. Different shapes of space would subtly change the pattern of structures we see in the sky, but those differences are extremely delicate and hard to detect. Our observations so far are consistent with many possibilities. The true shape of all that exists could be simpler or stranger than we imagine, and we may never travel far enough to find out for certain. There could be invisible dimensions interwoven with the ones we see. We experience reality as having three directions of space and one of time. But some theories that try to unify the forces of nature work only if additional paying. Spatial directions exist. These extra directions could be curled up to sizes unimaginably small, so that we do not notice them in daily life. Their presence could gently affect how particles move and how gravity behaves, leaving only subtle traces in experiments and cosmic observations. In such a picture, every point in familiar space would really be a tiny multidimensional structure, with paths that loop through directions our senses cannot follow. If these hidden dimensions exist, they might allow new kinds of particles, or even connect distant regions of space in ways we have barely begun to picture. Looking for them requires creative experiments and careful study of how the universe evolved. The idea that our world might be only part of a larger dimensional tapestry remains an open and profound possibility. We do not know what space itself is made of. We talk about space as if it were an empty stage, a smooth backdrop where matter moves and light travels. Yet we do not truly understand whether that stage is fundamental or built from something deeper. Some approaches to quantum gravity picture space as emerging from discrete building blocks, perhaps a network of relations or tiny units of area and volume that only look continuous from far away. Others imagine space arising from patterns of quantum information, like a vast web of entanglement that gives rise to distance and geometry as collective effects. Even in ordinary physics, vacuum is not truly empty, but filled with fluctuating fields that can give rise to real particles. These hints suggest that the notion of a simple void may be an illusion. If space has an underlying structure, then at extremely small scales, our familiar concepts of location and distance might dissolve, replaced by something that does not fit our usual intuition. Time may flow differently in parts of the universe we cannot reach. Relativity tells us that the passage of time is not absolute. It depends on motion and on gravity. Clocks deep in gravitational wells tick more slowly compared to clocks far away, and objects moving at high speeds experience less elapsed time than those at tight rest. Across the universe, matter is arranged in complex ways, from dense clusters to vast empty regions, so the rate of time can vary from place to place. In distant galaxies, the rhythm of processes could be slightly offset from our own, even if no one there would notice the difference locally. In extreme environments near very compact objects, the difference becomes even more dramatic, with outside observers watching events unfold in slow motion. Because we cannot synchronize clocks across unreachable distances, we are left with a patchwork of local times woven together by theory. The idea that there is a single universal now becomes difficult to sustain once we take the cosmos into account. The universe might be one bubble among countless others. Certain theories of cosmic inflation suggest that the rapid expansion in the early universe might not have stopped everywhere at once. In some regions, expansion could have ended and cooled, forming bubbles where conditions stabilized enough for galaxies and stars to appear. In other regions, the accelerated growth could have continued, spawning further bubbles with potentially different properties. Our observable universe would then be one such bubble, occupying a finite domain in a much larger inflating background. Other bubbles might never collide with ours, remaining forever separated by growing distances and by regions where space still stretches at an enormous rate. Within those distant domains, physics might take different forms, or perhaps echo our own in ways we will never confirm. This picture turns what we call the universe into one example inside a greater multiverse. It offers explanations for certain cosmic puzzles, yet raises even deeper questions about what counts as reality. There could be structures larger than anything we can observe. Astronomers have discovered clusters, filaments, and sheets of galaxies that span astonishing distances, weaving a cosmic web through space. Yet our surveys are limited by how far light has traveled since the early universe and by the parts of the sky we have been able to study in detail. It is entirely possible that beyond the boundaries of current data, there are arrangements of matter even grander than the largest known formations. Perhaps superstructures that bend our assumptions about how uniform the cosmos should be. Some hints already challenge expectations, such as huge alignments that appear more coherent than standard models predict. Whether these are statistical flukes or glimpses of something deeper remains uncertain. If truly colossal structures exist beyond our horizon, their gravity could influence the motion of galaxies we do see, leaving only indirect signs of their demanda, presence. In that sense, unseen architecture might be quietly shaping the cosmos we can measure. We do not know whether the universe has an edge or no boundary at all. When we talk about the universe, it is natural to picture a region with some kind of border, beyond which there is nothing. Yet in physics, the idea of an edge to space is problematic, because edges usually imply something outside. One alternative is that the universe is finite, but curved in such a way that it has no boundary, like the surface of a sphere that ends nowhere even though it has limited area. Another possibility is that space extends indefinitely, with no edge and no outside, only more and more of the same fabric. Our observations of the cosmic background and the distribution of galaxies tell us about geometry within the part we can see, but they do not conclusively answer the global question. Even our language struggles because we are trying to describe the totality of everything from within. Whether there is a true edge, a closed shape, or infinite extent remains one of the deepest open puzzles. The universe might be expanding into something we cannot perceive. When we measure the motion of distant galaxies, we find that space itself is stretching. carrying them farther from us. Yet the question of what this expansion is happening into remains unresolved. In standard cosmology, space does not need an outside. It can grow the way a pattern on a balloon grows, even if you focus only on the two-dimensional surface, without considering the air around it. Still, it is difficult not to wonder whether the fabric of the cosmos is embedded in something larger. If such an external realm exists, it would not necessarily follow the rules of our own space or time. It might not contain matter, energy, or geometry as we understand them. Our instruments are designed to measure what happens within the universe, not beyond it. As a result, any wider container would remain hidden from view, leaving us to infer possibilities only through mathematics and the behavior of distant galaxies. The true nature of expansion remains one of the most puzzling questions in modern science. We still do not understand why space is so smooth on vast scales. Across billions of light years, the universe looks remarkably uniform. The temperature of ancient radiation varies only by tiny fractions, and matter spreads out in a pattern far more even than one might expect. This smoothness is surprising because regions separated by extreme distances could never have interacted in the early universe. There was simply not enough time for light or any other signal to travel between them. To explain this, theories propose a brief phase of extremely rapid growth that allowed regions now far apart to originate from a small connected area. Although this idea fits the data well, we still do not know what triggered that growth, how it ended, or whether alternative explanations might work. The uniformity we observe could carry information about processes that occurred before the earliest moments we can probe. Space may hold silent clues about a deeper mechanism that shaped the entire cosmos, long before galaxies began to form. The universe could carry subtle imprints from events before its birth. The oldest light in the universe is a faint glow that has traveled across space for almost the entire cosmic history. Although it has been studied with great precision, it might contain traces of processes that happened even earlier than the hot, dense state usually described as the beginning. Certain models of cosmic evolution predict that ripples, patterns, or slight distortions might survive from an earlier phase, carried forward as the universe expanded and cooled. These features would be extremely delicate, hidden within the noise of cosmic data and difficult to distinguish from ordinary fluctuations. If they exist, they could reveal information about conditions that no current experiment can recreate. They might hint at a prior contraction or a more complex transition that preceded the familiar expansion. The possibility that our universe retains the fingerprints of an earlier era invites the idea that the cosmos has a longer and richer story than we can presently observe. There may be hidden patterns in the cosmic web we have not recognized. When astronomers map the distribution of galaxies, they discover a sprawling network of clusters, filaments, and great empty voids. This intricate web resembles the structure of living tissue or neural pathways, showing how gravity shaped matter on the largest scales. Yet we may only be seeing the most obvious layer. Deeper mathematical relationships might link the positions and motions of galaxies in ways we have not yet noticed. Subtle symmetries could be present in the alignment of structures, or long-range correlations might exist that require new tools to detect. Even the way galaxies rotate or cluster might follow hidden rules that have gone unrecognized. As surveys grow more detailed, they may reveal unexpected organization buried within the apparent randomness. Patterns like these could hint at undiscovered physics or at early cosmic processes that left long-lasting effects throughout the web of matter that stretches across the ball. Universe. The universe might end in ways we cannot yet imagine. Cosmology offers several possible futures, yet none are certain. If dark energy remains steady, space will continue expanding at an ever-increasing rate, gradually isolating galaxies from one another until the night sky grows empty and cold. If dark energy strengthens, the expansion could accelerate so dramatically that even atoms might eventually be pulled apart. If dark energy weakens or reverses, the universe could slow, halt, and collapse into a dense state, possibly leading to a new expansion. Other possibilities involve transitions in the underlying vacuum of space, changes in physical laws, or processes we have not yet formulated. Because we cannot measure the future behavior of dark energy or the stability of the vacuum, we face fundamental uncertainty about how the story of the our universe concludes. Each scenario shapes matter and time in profoundly different ways. The vast future remains an open landscape of possibilities, each hinting that our cosmic era is only one chapter in a much longer narrative. There could be cycles of cosmic creation beyond our horizon. Some theoretical frameworks imagine that the universe did not begin with a single event, but instead passes through repeating phases of contraction and expansion. In such a picture, our own cosmic history would be part of a larger sequence, with previous cycles imprinting subtle hints on the structure we observe today. Although these ideas are difficult to test, they offer explanations for certain puzzles about uniformity and fine structure. If the universe has experienced multiple cycles, then each era might inherit conditions shaped by those that came before. Entire sequences of galaxies, stars, and cosmic evolution could have risen and faded long before our own epoch, leaving few traces except possibly in the earliest moments of the current expansion. These cycles might continue far into the future, forming a grand rhythm of creation and transformation that lies beyond our observable domain. Whether such patterns truly exist remains unknown, yet they provide a striking alternative to a single beginning. We do not know what started the rapid expansion of the early universe. Observations strongly support the idea that the universe underwent a brief period of extremely fast growth, shortly after its earliest moments. This expansion smoothed out irregularities and set the stage for the formation of galaxies. However, the cause of this rapid growth remains mysterious. Proposed explanations include new fields of energy, transitions between physical states, or deeper mechanisms that might involve the fabric of space itself. Each proposal attempts to account for the characteristics we see today in ancient radiation and the arrangement of matter. Yet none has been confirmed, and several predict effects that are very subtle. Without a way to directly examine the conditions of that early time, we must rely on indirect clues and careful analysis of cosmic patterns. The true trigger of this expansion remains an open question, and understanding it may require insights that unify ideas about gravity, quantum physics, the origin of space. The universe might have dimensions curled too small to detect. Some theories that aim to unify the forces of nature suggest that in addition to the familiar three dimensions of space, there may be extra directions folded into power, extremely tiny shapes. These compact dimensions would be far smaller than any current experiment can probe, hidden within the structure of each point in space. Their geometry could influence particle behavior, alter gravitational interactions, or allow new types of motion that cannot occur in ordinary space. Although these dimensions would not be directly visible, their presence might produce small deviations in measurements of particle collisions, or leave faint signatures in the early universe. Searching for these effects requires precise instruments and creative experimental designs. If such curled dimensions exist, they would imply that our everyday experience captures only a small part of a much richer spatial environment. The universe might be built on a multidimensional foundation that remains almost entirely concealed. We do not know whether space emerges from something deeper. Modern research has raised the possibility that space is not a fundamental entity, but instead arises from more basic components. In some models, geometry is produced by patterns of quantum information or by networks of relationships between microscopic elements that do not resemble locations in any ordinary sense. Distances, directions, and even the flow of time could be large-scale consequences of these underlying structures. Evidence for such ideas comes from studies of black holes and quantum physics, where traditional concepts break down and new principles appear to link geometry with information. Although these ideas are still speculative, they offer a route toward unifying gravity with the world of particles. If space is emergent, then familiar reality might be analogous to a surface formed from countless unseen interactions. Understanding the deeper layer could change the way we think about the fabric of the universe and the nature of existence itself. The universe could be a projection of a more fundamental reality. Certain approaches to quantum gravity suggest that the three-dimensional world we experience may be encoded on a lower dimensional structure, somewhat like a pre-hologram. In these proposals, the full richness of space and matter arises from information stored on a surface that has fewer dimensions than the space it describes. This concept emerged from the study of black holes, where the amount of information needed to describe them seems to scale with their surface area rather than their volume. Extending this idea to the entire cosmos suggests that reality might have an unexpected architectural design. Although this does not mean the universe is an illusion, it implies that our usual understanding of location and depth might be secondary to deeper principles. Experiments and observations are beginning to test aspects of these ideas, but the question remains far from settled. The possibility that the cosmos is a projection challenges many intuitive notions and opens the door to new ways of describing the foundations of physics. Dark energy may be changing over time in ways we cannot measure yet. Astronomers discovered that the expansion of the universe is speeding up, a result often attributed to an unknown influence called dark energy. Yet we do not know whether this mysterious force is constant or shifting over cosmic time. Our measurements cover only a narrow slice of the universe's history, and any slow variation would be extremely difficult to detect. If dark energy changes, it could alter the ultimate fate of the cosmos, either strengthening to drive galaxies apart ever faster or weakening enough for gravity to slow the expansion in the distant future. It might even undergo transitions, behaving differently in past eras than it does today. The difficulty lies in the fact that dark energy does not interact directly with matter or light. We infer its presence only through the motion of galaxies and the geometry of space. Subtle changes could hide beneath current uncertainties, waiting for more precise observations or new ways of mapping cosmic history. The nature of dark energy remains one of the most profound mysteries in physics. Dark matter could be something entirely outside known physics. We observe the influence of an unseen mass that surrounds galaxies and shapes the large-scale structure of the universe. This invisible matter does not emit light or interact strongly with normal atoms, although many theories attempt to explain it using new particles. Another possibility is that dark matter does not belong to the familiar family of forces, interactions at all. It could arise from a sector of physics that barely touches the one we experience. In such a scenario, dark matter might have its own kinds of particles, motions, and internal processes, operating in a shadow-like framework that rarely influences ordinary matter except through gravity. This idea opens the door to entire worlds of behavior that remain hidden from every detector on Earth. If dark matter truly lies outside known physics, then solving its nature will require ideas beyond the standard approaches. Its presence could be a clue that our view of reality captures only a fraction of what exists. There might be particles passing through us that we cannot yet detect. Even within the known laws of physics, countless particles move through space constantly. Some are familiar, such as neutrinos, which pass through matter with little interaction. Others may exist beyond our current understanding. These hypothetical particles could permeate the cosmos, drifting through planets, stars, and living beings without leaving detectable traces. Their interactions might be so weak or so unusual that they escape every current instrument. Some theories predict particles that rarely collide with normal atoms, while others propose entities that do not fit the usual categories of matter and energy. The Earth might be immersed in a sea of undetected particles that influence cosmic evolution, yet remain invisible to us. Each new generation of detectors reaches further into this landscape, searching for signs in faint flashes of light, subtle vibrations, or rare collisions. The possibility that unknown particles are quietly passing through us every moment suggests that much of reality may be hidden just beyond our reach. Dark matter could form structures as complex as the visible universe. Although dark matter is invisible, its gravity affects everything around it. Models of cosmic evolution often show dark matter gathering into halos that guide the formation of galaxies. Yet these halos might not be simple clouds. They could contain layers, clumps, waves, or patterns shaped by interactions within the dark sector. If dark matter has its own forces or particle families, it might be capable of forming structures as varied as those made of atoms. These structures would not emit light, but they could influence the motions of stars and gas, shaping galaxies in ways we have not yet recognized. Some simulations suggest that dark matter might form filaments within halos or support long-lived patterns that affect how galaxies rotate. Discovering such structures would require incredibly detailed observations and new theoretical tools. The idea that an unseen architecture coexists alongside the visible cosmos highlights how limited our perspective may be. Dark energy might interact with matter in ways we have not observed. Most interpretations treat dark energy as something that influences only the expansion of space, not the behavior of matter. However, some theoretical models allow for a faint connection between dark energy and the particles that make up stars and galaxies. If such an interaction exists, it could cause subtle shifts in the masses of particles or the strength of forces over vast periods of time. These tiny changes might accumulate across cosmic history, leaving patterns in the distribution of galaxies or affecting the rate at which structures formed. So far, no clear evidence for such interactions has appeared, yet the possibility remains open because the required effects could be extremely small. Future surveys that examine distant galaxies more precisely may reveal signs of a hidden dialogue between dark energy and matter. If this connection exists, it would reshape our understanding of how the universe evolves and reveal a bridge between two of its most mysterious components. There could be multiple types of dark matter hidden in plain sight. Most discussions of dark matter assume that it is composed of a single kind of particle. Yet nature often prefers variety. Ordinary matter includes atoms, molecules, plasma, dust, and countless other forms. Dark matter might be just as diverse. Some types could be cold and slow-moving, others warm and faster, and still others could bind into composite objects through interactions within the dark sector. Each type would influence galaxy formation differently, creating a much richer landscape than most simple models predict. Because dark matter does not emit light, this diversity would not be visible directly. Instead, the mixture might reveal itself through subtle features in the motion of stars or the shapes of galaxies. Understanding such complexity would require new methods of analyzing cosmic data and new theories that allow dark matter to have internal structure. The idea of multiple unseen components hints that the dark side of the universe could be far more intricate than we imagine. Dark energy could hint at a deeper layer of reality we do not see. The discovery of accelerated expansion forced physicists to consider that the vacuum of space contains energy with unusual properties. This energy does not behave like matter or radiation. Its effects suggest that space itself has an underlying structure that influences how it stretches. Some proposals link dark energy to quantum fields that fill all of space, while others connect it to geometric features that emerge from deeper principles. If dark energy reflects a hidden layer of reality, then our familiar understanding of space might be only a surface-level description. The behavior of dark energy could reveal information about this deeper framework, yet we currently lack the tools to probe it directly. Observations of distant supernova, galaxy clustering, and the cosmic background provide clues, but the full picture remains obscure. Dark energy may be the most accessible sign that reality contains levels we have not uncovered. Dark matter might be a shadow of processes in higher dimensions. Some theoretical models propose that our universe contains more spatial directions than we can perceive. If higher dimensions exist, dark matter might be an echo of processes occurring within them. In this view, particles we detect only through gravity might be objects moving or interacting in directions unseen by ordinary senses. Their apparent invisibility could be a natural consequence of their higher dimensional nature. They would interact weakly with familiar matter because they occupy different slices of reality, yet their mass would still tug on stars and galaxies. This idea offers possible explanations for why dark matter behaves differently from ordinary particles and why it forms large halos around galaxies. Detecting such effects would require looking for small deviations in gravitational behavior or searching for signs of extra-dimensional motion. If dark matter is truly linked to higher dimensions, discovering its nature would change our understanding of what space itself can be. There could be entire stars made mostly of dark matter. If dark matter can clump under gravity, it might gather in high enough concentrations to form compact objects. In some cosmological scenarios, dark matter could collapse into dense regions that behave like stars, yet without nuclear reactions or visible light. These dark stars would be practically invisible to telescopes that rely on electromagnetic radiation. Instead, their presence might be revealed through gravitational influence alone. Some theories imagine dark matter particles that can release energy through exotic interactions, allowing dark stars to shine faintly in ways we have not yet identified. Others picture them as cold, quiet bodies drifting through galaxies, leaving only subtle gravitational footprints. Finding such objects would require precise mapping of stellar motions or gravitational lensing. The existence of dark stars would add an entirely new category to the cosmic inventory, showing that the universe contains kinds of stellar bodies fundamentally different from anything we have ever seen. Dark matter might carry information about ancient cosmic eras. Because dark matter interacts so little with ordinary particles, it has preserved its original properties across almost the entire history of the universe. While atoms were broken apart, fused and reshaped in stars, dark matter remained largely unchanged. Its distribution today still reflects the conditions that existed long before galaxies formed. If we could decode its structure, we might learn about epochs that no radiation can directly reveal. For example, slight variations in dark matter density might reflect events in the very early universe, or transitions that occurred before familiar particles emerged. Mapping these patterns requires detailed observations of how galaxies move within their halos and how matter clusters on different scales. Each measurement provides a hint of the ancient landscape that shaped the cosmos. Dark matter serves as a quiet record keeper of IRAs beyond direct observation, storing information in the way it is arranged across space. Black holes may contain regions where the fabric of reality breaks down. When matter collapses under its own gravity and forms a black hole, the equations of general relativity predict that space-time curves more and more sharply toward the center. At some point, these equations indicate that curvature becomes infinite. This is a sign not of a literal infinity, but of the failure of our current theories. Near such extreme conditions, the familiar rules of space, time, and physics may dissolve. Quantum effects should become important, yet we do not have a complete theory that unites quantum mechanics with gravity. As a result, the interior of a black hole remains an unsolved frontier. Physical quantities that behave smoothly elsewhere may no longer make sense. Even the concept of location could break down. This mysterious region is hidden from the outside world by the event horizon, so no signal can carry direct information outward. The unknown interior remains one of the most dramatic reminders that our understanding of reality is incomplete. A black hole's center could be something other than a singularity. Although classical theory predicts a point of infinite density at the core of a black hole, many researchers believe that nature avoids true infinities. Alternative models propose that quantum effects could replace the singularity with something more complex. Some ideas picture a region of extremely high but finite density. Others describe a tiny sphere where quantum pressure counteracts gravity. Still others imagine a surface where space-time undergoes a phase transition. These possibilities depend on how quantum gravity operates, and since that field remains under development, no single answer has emerged. Observations of black holes do not reveal their centers, so indirect evidence must be used. The behavior of gravitational waves, the motion of matter near the event horizon, and the stability of black holes over long periods may offer clues. Each scenario implies a different internal structure, suggesting that black holes might contain exotic states of matter or geometry unlike anything we have studied in laboratories. There might be paths through black holes that lead elsewhere. The mathematics of general relativity allows solutions where black holes connect to distant locations or even other universes through hypothetical bridges. These structures are often unstable and may collapse too quickly for anything to pass through, yet they remain intriguing possibilities. If quantum effects modify the interior, such pathways might become more stable in certain models. A traveler attempting to cross would face enormous tidal forces and unpredictable physical conditions, making any journey purely theoretical for now. Some theories propose that what appears to be a black hole from the outside could be connected to a different region that looks like a white hole from within, ejecting matter instead of absorbing it. These concepts arise naturally in the equations of gravity, yet we lack evidence to determine whether any of them correspond to real physical objects. Even so, the idea that black holes might serve as gateways hints at a universe more interconnected than our senses suggest. Black holes could store information in ways we do not understand. A long-standing puzzle in physics concerns what happens to information carried by matter that falls into a black hole. Quantum theory insists that information cannot be destroyed, yet classical black holes appear to erase the details of anything that enters. Efforts to resolve this contradiction have led to the idea that information might be encoded in subtle patterns on the event horizon or stored in quantum states of the hour. Gravitational field. Some proposals suggest that the horizon behaves like a physical surface with an enormous number of microscopic degrees of freedom. Others propose that information is released slowly through radiation during the black hole's lifetime. None of these ideas are fully proven, and each raises new questions about how information is represented in spacetime. The resolution of this puzzle could reveal a deeper connection between quantum theory and gravity, showing how the universe preserves its history even in the most extreme environments. There might be tiny primordial black holes scattered through the cosmos. In the very early universe, density fluctuations could have been large enough in some regions to collapse directly into small black holes. These primordial objects would not have formed from stars, so their masses could range from extremely small to quite large. If they exist, they might contribute to dark matter or influence cosmic evolution in subtle ways. Some might have evaporated completely, while others could still drift through galaxies invisibly. Their presence might be revealed through gravitational lensing of distant stars, through disruptions in the motions of objects, or through faint radiation produced during their final stages of evaporation. Despite careful searches, no confirmed detection has yet been made. The possibility of primordial black holes remains open, offering a link between the physics of the early universe and the dark matter puzzle. If they are real, they would provide a direct window into conditions that existed long before the first stars formed. We do not know what happens at the very edge of a black hole. The boundary that separates the interior of a black hole from the outside universe is called the event horizon. It is not a solid surface, but a region where escape becomes impossible. Although general relativity predicts how the horizon behaves, quantum effects complicate the picture. According to theory, the horizon emits radiation due to quantum processes, yet the detailed mechanism remains unclear. Some research suggests that the horizon might have a complex structure influenced by quantum information. Others picture it as a smooth boundary with no special features. Because we cannot observe the horizon up close, our understanding relies heavily on theory. The behavior of particles, light, and information near this boundary may hold clues about the unification of physics. The edge of a black hole is a frontier where known laws reach their limits, making it a key area of study for anyone seeking a deeper understanding of gravity and quantum mechanics. Black holes could evaporate in ways we have never observed. Quantum theory predicts that black holes emit radiation, slowly losing mass over extremely long timescales. This process, while theoretically robust, has never been directly observed because even small black holes evaporate far too slowly for current detectors. Some models suggest that evaporation might include bursts of energy or changes in the spectrum of the emitted radiation at late stages. Others propose that the final moments could reveal new physics involving exotic particles or transitions in the nature of spacetime. If evaporation proceeds differently from the standard picture, it could alter our understanding of energy conservation, information preservation, and the life cycle of black holes. Detecting these signals would require either an unexpectedly small black hole near Earth or a new method for observing extremely faint radiation across the cosmos. The final fate of black holes remains an open question, one with profound implications for the nature of the universe. Some black holes might have formed before the first stars existed. Most black holes arise from massive stars collapsing at the end of their lives. However, conditions in the early universe may have allowed black holes to form directly from dense regions of primordial gas. These black holes would predate the first stars and galaxies, acting as seeds that influenced early cosmic structure. Their growth could help explain how some supermassive black holes became so large so quickly, an ongoing puzzle in astronomy. Early black holes might have interacted with the surrounding gas, altering the rate at which the first stars formed. Observations of ancient quasars reveal extremely massive black holes, at times when the universe was still very young. Understanding how these giants arose may require the existence of an earlier generation of black holes formed through mechanisms unrelated to stellar beating. Evolution. These ancient objects would provide insight into the earliest chapters of cosmic history. Black holes could shape the universe more than we realize. Although black holes are often pictured as isolated objects, their influence extends far beyond their immediate surroundings. The largest galaxies appear to have enormous black holes at their centers, and the energy released by matter falling into these giants can shape the growth of the entire galaxy. Jets of high-energy particles can heat or disperse gas, regulating star formation across vast regions. Even smaller black holes can influence their environments by triggering bursts of radiation or stirring the motion of nearby matter. On cosmic scales, the collective activity of black holes may affect how structures evolve, how galaxies cluster, and how gas circulates between regions. These effects, although indirect, can reshape entire regions of space over immense periods of time. The role of black holes in cosmic evolution is still being uncovered, hinting that they are not merely endpoints of stellar life, but engines that drive large-scale transformations. There may be hidden black holes that emit almost no light at all. Most known black holes are discovered through the radiation produced by hot gas spiraling into them. However, many black holes may exist in quiet environments where little matter falls inward. These objects would be almost completely dark, detectable only through their gravitational pull. Some may drift through space alone. Others may reside in the outskirts of galaxies or within star clusters. Finding them requires careful analysis of stellar motions, gravitational lensing, or rare interactions with surrounding objects. The universe could contain far more black holes than current observations suggest, with many remaining invisible. These silent black holes hold clues about stellar evolution, galactic dynamics, and the unseen population of remnants scattered throughout the cosmos. Their existence reminds us that much of the universe may be made of objects that reveal themselves only through subtle gravitational effects. Gravity might behave differently on scales larger than galaxies. Astronomers have measured gravity with great precision within our solar system and inside galaxies, yet on the vastest scales, it becomes far more difficult to determine whether the familiar equations still apply. The motion of galaxies within clusters, the rate at which large structures grow, and the pattern of ancient cosmic light all depend on gravity acting across immense distances. Some observations hint at slight mismatches between predictions and reality, suggesting that gravity might change its behavior very subtly when stretched over enormous scales. These variations could be tiny, yet influential enough to affect the expansion of the universe or the formation of cosmic structures. Several ideas propose that gravity may weaken, strengthen, or shift its form when dealing with the emptiest regions of space. Others suggest that modifications might occur because the universe is not perfectly uniform. Untangling these possibilities requires deeper surveys, more refined models, and new ways of testing gravity across cosmic landscapes far larger than anything accessible in laboratories. There could be hidden forces acting across cosmic distances. In addition to gravity, the universe may host long-range forces that barely affect everyday matter, but shape the cosmos in subtle ways. These hypothetical forces could influence how galaxies move or how clusters evolve. They might act extremely weakly, making them difficult to detect within the solar system, yet influential across billions of light-years. Some theories predict that these forces emerge from new fields that fill all of space, guiding the behavior of dark matter or interacting with matter only through delicate channels. Such forces could help explain unusual motions within galaxies or unexpected patterns in cosmic structure. Detecting them would require precise observations of distant objects, careful comparison with theoretical predictions, and a willingness to consider that the universe might include influences far beyond the familiar four fundamental interactions. If hidden forces exist, they would reveal an enriched and more intricate picture of cosmic behavior. Gravity might be linked to quantum information in a way we do not yet see. Ideas from quantum theory and general relativity increasingly suggest that spacetime might be connected to the flow of information. In some approaches, the curvature of space could emerge from the structure of microscopic quantum states, with gravity arising as a large-scale consequence of how information is organized. This perspective connects the bending of light, the motion of planets, and the behavior of black holes to deeper patterns involving entanglement and quantum correlations. If this link is real, then classical gravity might be the visible expression of an underlying informational fabric. Evidence for these ideas comes from studies of black hole thermodynamics and from mathematical correspondences between geometry and quantum systems. Yet no direct experiment has confirmed the connection. Understanding it may require entirely new tools that bridge the gap between quantum physics and gravity. This possibility hints that the universe's geometry may not be fundamental, but instead a reflection of hidden informational rules. The universe could contain gravitational phenomena we have not imagined. Most of our understanding of gravity comes from observing planets, stars, black holes, and large-scale structures. Yet the universe is vast enough that phenomena unknown to us may occur under extreme conditions or in regions we have not yet explored. There might be exotic gravitational configurations where spacetime behaves in ways not described by simple curvature. Strange objects could exist that bend space in asymmetrical or unpredictable patterns. Regions with unusual forms of matter might produce entirely new gravitational effects that have left only faint or indirect signs in observable data. As our instruments improve, we may uncover hints of these unfamiliar behaviors, perhaps in gravitational wave signals or in anomalies found in the distribution of distant galaxies. The full diversity of gravitational possibilities may extend well beyond our current theories, waiting to be discovered in the deep reaches of the cosmos. There might be regions where gravity temporarily weakens or strengthens. The strength of gravity is usually treated as constant, yet in some theoretical frameworks it could vary slightly in time or space. These variations might arise from fields that evolve slowly across cosmic distances, or from interactions between gravity and unknown components of the universe. If gravity fluctuates gently, these changes would be far too small to notice on Earth, but they could influence cosmic evolution over immense periods. Regions where gravity is slightly stronger might form structures earlier, while weaker regions might delay the growth of galaxies. Observations of distant clusters and the cosmic web may hold subtle signs of such variations. Distinguishing them from ordinary cosmic variability is challenging, requiring careful analysis of large datasets and sophisticated simulations. If gravity does shift in strength, even by tiny margins, it would imply a deeper and more dynamic foundation underlying one of nature's most familiar forces. Gravity could leak into dimensions beyond our own. Some theories propose that gravity might not be confined to the familiar three-dimensional space we inhabit. Instead, it could spread into additional spatial directions that are hidden from ordinary perception. If so, gravity would appear weaker than expected in our three-dimensional world because part of its influence would extend into these unseen directions. This idea could help explain why gravity is so much weaker than other forces. It might also produce distinctive patterns in experiments designed to detect tiny deviations from Newtonian behavior. On cosmic scales, gravity leaking into higher dimensions could influence the rate at which structures grow or contribute to the accelerated expansion of the universe. Although no conclusive evidence has been found, the possibility remains compelling because it integrates naturally with theories that attempt to unify the IAS. Fundamental interactions. Discovering extra-dimensional effects would reshape our understanding of space, matter, and the behavior of the cosmos. The gravitational constant might not be constant everywhere. The constant that sets the strength of gravity plays a central role in every astronomical calculation, yet we do not know whether it is truly fixed across space and time. If it varies even slightly, it could influence the formation of stars, the behavior of galaxies, and the evolution of the universe. Subtle shifts might occur due to interactions with unknown fields or due to processes that began in the early universe. Observations of distant objects offer indirect tests, yet distinguishing true variation from ordinary astrophysical differences is extremely challenging. Some studies have searched for signs in the timing of pulsars, the brightness of supernova, or the distribution of galaxy clusters. So far, results remain inconclusive. If future measurements reveal that the gravitational constant changes, it would indicate that gravity is not a simple universal force, but a dynamic quantity shaped by deeper layers of physics. The way gravity works near the beginning of time is still unknown. As we trace cosmic history backward, conditions become increasingly extreme. Temperatures rise, densities climb, and quantum effects become significant. Under such circumstances, general relativity alone cannot describe gravity. We need a theory that unifies gravity with quantum physics, yet that theory remains incomplete. Without it, we cannot fully understand how space curved or how matter behaved during the earliest moments after the beginning of the universe. Clues may be hidden in the pattern of ancient cosmic light, in the distribution of large-scale structures, or in the behavior of gravitational waves. These hints suggest that gravity may have operated differently at that time, perhaps allowing phenomena that no longer occur. The early universe represents a laboratory with conditions impossible to recreate on Earth. Understanding gravity in that environment remains one of the most pressing challenges in cosmology. There could be particles that mediate gravity in subtle ways. In quantum field theory, forces are often transmitted by particles. If gravity follows a similar pattern, it might be mediated by a hypothetical particle. Such a particle would interact extremely weakly, making it nearly impossible to detect in experiments. Its existence could influence gravitational waves, modify the behavior of black holes, or subtly affect how matter clusters on large scales. Some theories predict families of such particles, each contributing in different ways to the overall behavior of gravity. Detecting them would require methods capable of isolating incredibly faint signals or observing effects that accumulate over cosmic distances. These particles may also interact with unknown fields or dimensions, complicating their behavior. If they exist, they would provide a direct route toward unifying gravity with quantum theory, revealing the microscopic structure behind the force that shapes the cosmos. Gravity might arise from something deeper than spacetime. The familiar picture of gravity as the curvature of spacetime may be an approximation of a more fundamental process. In some models, gravity emerges from the collective behavior of microscopic constituents that do not resemble space at all. These constituents could be quantum bits of information, relational structures, or other entities that operate according to rules unlike any classical theory. Spacetime itself would then be a large-scale phenomenon, much like temperature arises from microscopic motion. If gravity is emergent, then understanding its true nature requires identifying the underlying components and the principles that govern them. Evidence for this idea comes from connections between thermodynamics, information theory, and black hole physics. Although still speculative, the concept offers a unified way to link gravity with quantum mechanics. It suggests that our sense of space, time, and curvature may be secondary effects, shaped by an unseen foundation that determines how the universe behaves at its deepest level. The first stars may have been unlike anything in the modern universe. Astronomers believe the earliest stars formed from pristine gas containing only hydrogen and helium. the simplest elements created in the first minutes of TAF, cosmic history. Without heavier elements to cool the gas efficiently, these stars may have grown far more massive than anything that typically forms today. Some theories suggest that they reached hundreds of times the mass of the Sun, burning at extraordinary temperatures and living for only brief periods before collapsing or exploding. Their interiors may have produced the first heavy elements, seeding later generations of stars and shaping the chemistry of the universe. Because these earliest giants lived fast and died young, they vanished long before any galaxy reached maturity. Detecting traces of them requires studying faint signals imprinted on ancient cosmic light, or observing extremely distant galaxies where their influence remains embedded in the distribution of gas. The nature of these first stars remains unknown, yet they set the stage for everything that followed. We do not know how the first galaxies formed so quickly. When telescopes peer back into very early cosmic times, they reveal galaxies that appear surprisingly mature despite the short interval since the first stars ignited. These early galaxies contained structured regions, vigorous star formation, and sometimes even central black holes. Standard models predict that assembling such complex systems should require longer periods than the universe appears to have given them. This mismatch has prompted renewed study of how gas collapses, fragments, and ignites under primordial conditions. It also raises questions about whether our theories correctly describe how matter behaved during the first few 100 million years. New observations continue to find surprisingly bright and organized early galaxies, deepening the puzzle. These discoveries hint that early cosmic environments may have fostered rapid growth through processes not yet fully captured in simulations. The first galaxies remain key to understanding how the large-scale structure of the universe emerged from initial fluctuations. Some ancient galaxies look far older than they should be. Observations of extremely distant galaxies sometimes reveal systems that appear too massive, too bright, or too chemically enriched for their age. These galaxies formed when the universe was still in its infancy, yet they display properties expected of far later epochs. Their stars can show signs of earlier generations, even though there should not have been enough time for multiple cycles of formation and evolution. This tension challenges models of galaxy growth, prompting scientists to examine whether star formation was more efficient in early conditions or whether unknown mechanisms accelerated their development. Some of these galaxies may have undergone rapid mergers, while others may have collapsed unusually quickly from dense pockets of primordial gas. Each explanation carries implications for cosmology, suggesting that our picture of early cosmic timelines may need refinement. These ancient outliers remain compelling markers of unexplained processes that shaped the earliest structures in the universe. There could be stars made almost entirely from exotic particles. Most stars shine through nuclear fusion of familiar elements, but some theories propose the existence of stars composed partly or entirely of exotic forms of matter. These hypothetical objects might use dark matter interactions as an energy source, or they might consist of particles that do not follow the usual rules of nuclear physics. If such stars exist, they would behave differently from ordinary ones. Their temperatures, lifetimes, and internal structures could diverge dramatically from standard expectations. They might emit unusual spectra or produce neutrino signatures unlike any known stellar process. Detecting them would require careful searches for stars that appeared too dim, too bright, or too stable for their mass and age. These exotic stars would offer direct insights into unfamiliar physics, showing that starlight may not always come from the same kinds of processes that power the LR. Familiar cosmos. We do not know how supermassive black holes grew so fast. Giant black holes, millions or billions of times the mass of the Sun, exist in galaxies throughout the universe. Yet observations show that some of these giants were already enormous when the universe was still very young. Their rapid growth poses a challenge because known processes of accretion and merging do not seem efficient enough to build such massive objects so quickly. Several ideas attempt to resolve this puzzle. Some propose that the first black holes formed from stars far larger than any seen today. Others suggest that entire clouds of gas may have collapsed directly into black holes without forming stars first. Another possibility is that early environments allowed unusually rapid feeding rates. Each explanation requires conditions that differ from those found in the modern universe. Understanding how these giants emerged so early is essential, because they influenced the evolution of the first galaxies and shaped large-scale cosmic development. Some galaxies appear to lack dark matter for reasons we cannot explain. Dark matter is thought to be essential for galaxy formation, providing the gravitational framework that holds stars and gas together. Yet a handful of observed galaxies seem to contain far less dark matter than expected, and in some cases, almost none at all. Their stars move more slowly than predicted, suggesting that dark matter does not dominate their mass. These unusual systems challenge widely accepted ideas about how galaxies form and evolve. Some hypotheses propose that interactions with neighboring galaxies stripped away dark matter, while others suggest that these galaxies may have formed through processes not yet understood. Observing them more closely may reveal whether they truly defy expectations or whether hidden complexities in their structure mask the presence of dark matter. These galaxies remain rare but important, offering unexpected insights into the diversity of cosmic evolution. There could be entire galaxies made mostly of invisible matter. While some galaxies appear to lack dark matter, others might be composed almost entirely of it. Such galaxies would contain very few stars, making them extremely faint and difficult to detect. Their presence could be inferred only through gravitational effects on nearby objects or through subtle lensing of background light. If these dark-dominated galaxies exist, they might account for a portion of the missing matter in the universe and provide clues about how dark matter behaves on galactic scales. They might form in regions where normal matter could not cool efficiently or where star formation was suppressed. Studying them would deepen our understanding of how structure forms in the dark sector and how galaxies assemble under a wide range of initial conditions. Discovering even a few would dramatically expand our view of what counts as a galaxy. There might be stellar objects that do not fit in any known category. Astronomers classify stars into familiar groups based on temperature, mass, and composition. Yet surveys occasionally reveal objects that defy simple categorization. Some appear too cool to be stars, but too warm to be planets. Others show chemical signatures or brightness patterns that do not match standard models. These oddities may represent previously unknown stages of stellar evolution, or entirely new kinds of objects shaped by exotic physical processes. They could be remnants of unusual formation histories or products of environments not seen elsewhere. Understanding them requires detailed observation and creative thinking about how matter behaves under unexpected conditions. Each new anomaly challenges the boundaries of established classifications, reminding us that the universe may host forms of stellar structure that are rare, fragile, or simply unfamiliar. They could be ancient cosmic structures we have not yet seen. The observable universe contains clusters, filaments, and other large-scale formations, but our surveys cover only a limited portion of the cosmos. Beyond the reach of current instruments, there may be structures older, larger, or more complex than any mapped so far. These might include massive collections of galaxies, unusually shaped regions of cosmic voids, or patterns imprinted by early processes that no longer operate. Some features may be so faint or diffuse that they blend into the background, while others may lie beyond our observational horizon. As telescopes and analysis techniques improve, we may uncover hints of these hidden structures through gravitational effects, subtle distortions of ancient light, or unexpected alignments. Their discovery would deepen understanding of how matter arranged itself across cosmic time. Some stars may collapse in ways we do not understand. Most stars follow predictable paths from formation to final collapse, yet some observations reveal stellar deaths that do not match standard explanations. Certain explosions appear too bright or too faint for their expected mass. Others produce unusual remnants or emit energy in ways that challenge known physics. Some stars may collapse directly into black holes without visible explosions, while others may undergo partial collapse that leaves behind exotic cores. These anomalies suggest that the internal processes driving stellar endings may involve complexities not captured in current models. Studying such events requires rapid observations, broad wavelength coverage, and careful comparison with theoretical predictions. The diverse ways in which stars reach their final moments reveal that stellar evolution still contains unsolved mysteries. Neutron stars might hide states of matter unknown on Earth. Inside a neutron star, matter is compressed to densities far beyond anything achievable in laboratories. Under such conditions, atoms no longer exist in familiar forms. Electrons are forced into protons, forming an immense sea of neutrons, packed together with almost no empty space between them. Yet even this description may be too simple. The pressure in the core could become so extreme that neutrons break down into their constituent particles or rearrange into entirely new states of matter. Some models predict a fluid of quarks, while others imagine strange particles that appear only under the most intense compression. These extreme environments may host behaviors not found in any other place in the universe. Because we cannot probe neutron star interiors directly, we rely on clues from vibrations, cooling patterns, and the way these stars react when paired in binary systems. Each observation offers a hint, yet the true nature of matter inside remains an unsolved and profoundly compelling mystery. There could be objects denser than neutron stars, but not black holes. The known universe contains white dwarfs, neutron stars, and black holes. But some theories suggest the existence of objects that fall between the last two categories. These hypothetical bodies could be composed of exotic particles or unusual arrangements of matter that resist collapse, even at extreme densities. They might be smaller and heavier than ordinary neutron stars, yet not compressed enough to form an event horizon. If such objects exist, they would challenge our understanding of the nuclear forces that hold matter together. Their signatures might hide in puzzling mass measurements or unusual behaviors in binary systems. Distinguishing them from known objects requires precise observations of how they bend light and how they interact with companions. These ultra-dense bodies would provide a natural laboratory for physics beyond the familiar, revealing new layers of complexity in how matter behaves under pressures far surpassing anything seen on Earth. Some neutron stars might convert entirely into exotic matter. As certain neutron stars gain mass through accretion or evolve over long timescales, their internal pressure may reach thresholds where neutrons become unstable. In some models, this instability triggers a conversion to strange matter or quark matter, creating an object radically different from its original form. This transformation could occur suddenly or gradually, altering the star's rotation, magnetic field, and thermal properties. If the entire interior converts, the star becomes a new type of compact object with a different density and structure. Detecting such transitions would require careful monitoring of pulsars for abrupt changes in timing or unexpected shifts in emitted radiation. These conversions, if real, would reveal that nature supports forms of matter more exotic than anything observed in laboratories. The idea that a neutron star can transform from one extreme state to another adds a remarkable dimension to the study of compact objects. They could be planets orbiting neutron stars that should not exist. The discovery of planets around neutron stars came as a surprise because the violent events that create these compact remnants should destroy or eject NEK, nearby worlds. Yet several pulsars host planets that orbit steadily, suggesting either remarkable survival or formation from debris after the original star's explosion. These planets experience intense radiation and extreme gravitational conditions, making them unlike typical worlds around ordinary stars. Some may have formed from disks of material shed during the supernova, while others may be remnants of disrupted companion stars. Their unusual origins raise questions about how planets can form or endure in hostile environments. Studying them allows researchers to explore the outer limits of planetary physics and examine worlds shaped by conditions far removed from those that influenced the Dingra solar system. These strange planetary systems highlight the resilience and diversity of planetary formation across the cosmos. Neutron star collisions might produce unknown particles. When two neutron stars spiral together and merge, they create some of the most extreme conditions in the universe. Temperatures soar and densities climb, producing an environment where nuclear reactions and particle interactions reach energies far beyond those achievable in particle accelerators. Such collisions might generate particles that do not appear in ordinary reactions, revealing aspects of physics that remain hidden in normal cosmic hour. Conditions. These events also produce gravitational waves and bursts of radiation that can carry subtle information about the particles involved. If unknown particles are created, they might affect the distribution of energy or alter the signatures observed by telescopes. Each merger offers a rare opportunity to study matter at its most extreme, providing clues about the behavior of fundamental particles under conditions that existed only briefly in the early universe. Some neutron stars spin in ways that defy current physics. Neutron stars are known for their rapid rotation, yet some exhibit spin rates or timing behavior that challenge theoretical expectations. Certain pulsars maintain astonishingly stable periods, while others glitch suddenly, changing rotation speed in unpredictable jumps. A few spin so fast that their survival seems to defy limits imposed by structural integrity. These behaviors may involve complex interactions among the crust, superfluid interior, and magnetic fields. They might also hint at processes not yet understood, such as interactions with exotic matter or instabilities rooted in quantum phenomena. Observing these spin patterns helps researchers test models of how compact objects evolve and how their internal layers interact. The diversity of rotational behaviors suggests that neutron stars may host intricate mechanisms that push the boundaries of known physics. There could be pulses of neutron star activity we have never detected. Neutron stars emit radiation across a wide range of wavelengths, much of it highly directional. If their beams do not sweep across Earth, we never observe their signals. Many neutron stars may therefore remain unknown, hidden simply because their emission does not intersect our line of sight. In addition to regular pulses, neutron stars can produce bursts, flares, or subtle vibrations that may be too faint or too brief for current instruments to capture. Some phenomena may require new detectors or more sensitive surveys to uncover. There might be entire classes of neutron star emissions that lie just outside the capabilities of existing technology. Detecting these would expand our understanding of how neutron stars transfer energy, how their magnetic fields evolve, and how their interiors respond to stress. The unseen behaviors of these compact objects likely form a rich and unexplored domain of astrophysics. Neutron stars might hold clues about the universe's earliest moments. Because neutron stars contain matter compressed to densities similar to those present shortly after the beginning of the universe, studying them offers insights into physical conditions that no laboratory can replicate. Their cores may preserve information about interactions that shaped the early cosmos, including transitions between different states of matter. The behavior of their crusts, magnetic fields, and oscillations reflects fundamental forces that also influenced early cosmic evolution. Observations of neutron stars in binary mergers provide data about how matter behaves at extreme temperatures and densities, echoing conditions from the first fractions of a second of cosmic history. By decoding the signals from these events, scientists hope to learn about forces and particles that operated in the earliest moments. Neutron stars serve as natural time capsules, holding information from epochs otherwise inaccessible. Some neutron stars might be slowly transforming into black holes. As neutron stars age or accumulate matter from companions, they may approach the threshold at which gravity overcomes all internal pressure. When this limit is crossed, the star can collapse into a black hole. This transformation may not occur abruptly. Some models suggest a gradual sequence of internal changes as the star becomes increasingly compact, with phases marked by shifts in rotation, magnetic fields, or emission properties. Observing these signatures might allow astronomers to witness the stages leading to collapse. Such transitions would reveal the fine boundary between the stability of neutron matter and the gravitational pull that forms a black hole. Identifying stars on the brink of this transformation would provide valuable information about the fundamental limits of matter and the complex pathways that lead to the creation of black holes. Neutron star crusts could contain the strongest material in the universe. The outer layers of a neutron star form a crystalline lattice of nuclei packed together under extreme pressure. This material must support enormous magnetic fields and withstand immense stresses caused by rotation and internal motion. Calculations suggest that the crust structure may be hundreds of times stronger than any known substance on Earth. It could deform without breaking, endure intense strain, and store vast amounts of elastic energy. When this crust finally gives way, it may produce sudden changes in rotation or bursts of radiation. Understanding the properties of this remarkable material helps explain how neutron stars behave under stress and why they sometimes experience abrupt shifts. Its strength reflects the unique conditions of these compact objects, where extreme density and pressure create forms of matter that simply cannot exist anywhere else. We still do not know what most comets originate from. Comets carry some of the most ancient material in the solar system, yet their true origins remain elusive. While many are believed to come from a distant reservoir known as the outer cloud, we have never observed this region directly. It lies so far from the Sun that any objects within it reflect almost no light, making them effectively invisible to telescopes. The few comets we see are those that have been nudged inward by gravitational disturbances, but these represent only a tiny sample of what likely exists. Their compositions vary widely, hinting at different birthplaces or histories. Some contain ingredients associated with deep cold environments, while others show signs of processing in warmer regions. This diversity suggests that comets may form in multiple zones or migrate long distances before settling into the far reaches of the solar system. Until we develop ways to detect objects across those extraordinary distances, most of their place of origin will remain a hidden chapter of our solar system story. There could be entire clouds of objects beyond the reach of our telescopes. Astronomers suspect that the outskirts of planetary systems may hold vast collections of icy bodies far larger in number than the comets and asteroids we observe near the Sun. These distant clouds could contain trillions of small objects drifting silently through space. Because they reflect so little light and lie at such great distances, they evade even the most powerful telescopes. Their existence is inferred from the behavior of long-period comets and from models of how planetary systems form. These unseen populations may include bodies with diverse compositions, shapes, and histories, each shaped by conditions in the early solar nebula. They could also influence the motion of nearby stars or record subtle gravitational interactions from ancient encounters. Detecting them will require future missions that can sense faint thermal signatures or gravitational effects across enormous distances. Until then, the outermost regions of planetary systems will remain among the least explored realms in astronomy. The space between stars may hold more than dust and gas. Interstellar space is often described as a thin mixture of dust, gas, and radiation. Yet growing evidence suggests that it may contain far more complexity. Observations of absorption lines and faint emissions reveal unexpected molecules, unusual temperature gradients, and hints of structures that do not fit simple models. Some regions appear to host dense clumps of material that drift independently, while others contain magnetic patterns that extend for great distances. There may also be charged particles and tiny grains, with properties distinct from those found in the solar system. These components influence how light travels through space, how stars gather material, and how shock waves from supernova propagate. The interstellar medium is dynamic, shaped by stellar winds, radiation, and passing clouds. Understanding it requires combining chemistry, plasma physics, and studies of cosmic dust. Far from being empty or simple, the space between stars may be a vibrant and evolving environment. There could be invisible structures moving through interstellar space. As astronomers map the galaxy, they find variations in starlight that hint at objects or patterns passing between us and distant stars. These features do not match the behavior of known clouds or dust. Some appear transient, shifting on timescales too short for ordinary interstellar material. Others produce effects that suggest large but diffuse structures with properties unlike typical gas or dust formations. These invisible shapes might be composed of extremely fine particles, magnetic filaments, or low-density material that interacts with light in unusual ways. They could form naturally through turbulence or arise from processes not yet understood. Detecting them requires repeated observations of the same stars and careful analysis of subtle changes. If such structures are common, they may influence how matter cycles through the galaxy, shaping star formation and the distribution of interstellar material. Their elusive nature highlights how much remains undiscovered in the vast spaces between stars. Some rogue objects traveling through space defy classification. Occasionally, astronomers detect objects moving on trajectories that do not match typical comets, asteroids, or planets. These rogues drift freely through space, unbound to any star. Some may be fragments from disrupted planetary systems, while others might have formed independently in the cold depths between stars. Their properties vary widely. A few show comet-like activity when approaching a star, while others behave more like dense rocky bodies. Some move at speeds that suggest distant or tumultuous origins. Because they do not remain in the solar system for long, studying them requires rapid observation and careful analysis. These visitors offer insights into the diversity of material in the galaxy and the processes that eject objects from planetary systems. Their unusual features challenge existing categories and reveal that the galaxy may hold many forms of wandering bodies we have only begun to identify. Interstellar space may contain reservoirs of frozen ancient material. Cold regions far from stars allow molecules and dust grains to survive unchanged for immense periods. These reservoirs could hold frozen gases, complex organic compounds, and minerals older than many stars in the galaxy. When such material is disturbed by shock waves or passing objects, fragments may drift into denser regions, influencing star and planet formation. Some of the frozen material may carry signatures of chemical processes that occurred in the earliest phases of the galaxy. These reservoirs also affect the temperature and ionization of interstellar clouds, shaping the cycle of matter between stars. Detecting them is difficult because they emit little radiation, yet faint signals in the infrared and radio bands hint at their presence. These silent storehouses of ancient material serve as archives of cosmic history, preserving clues about conditions that shaped the earliest environments in the galaxy. There might be complex magnetic fields spanning vast distances. The galaxy is threaded with magnetic fields that twist, bend, and interact with charged particles. These fields are difficult to map because they do not emit light directly. Instead, they reveal themselves through the behavior of cosmic rays, polarized starlight, and the motion of gas clouds. Some regions show remarkably coherent structures extending through interstellar space, suggesting large-scale organization. Others display tangled patterns shaped by turbulence or shock waves from exploding stars. These magnetic fields influence star formation, guide charged particles, and help regulate the temperature of interstellar gas. They may also shape the boundaries between different regions of the galaxy, creating large but invisible frameworks that affect how matter moves. Understanding these magnetic structures is essential for modeling the behavior of the interstellar medium, yet many details remain unknown. Their complexity points to processes that span enormous distances and long periods of cosmic time. There could be waves through space we have not yet recognized. Beyond gravitational waves, which ripple through spacetime itself, there may be other forms of waves moving through the galaxy. These could arise from oscillations in magnetic fields, fluctuations in charged particle densities, or variations in interstellar pressure. Some may travel slowly through diffuse gas, while others might move rapidly across regions filled with plasma. Because they do not emit strong light, they are difficult to detect with traditional instruments. Their presence could influence the formation of stars, the behavior of cosmic rays, or the distribution of material across the galaxy. Detecting these waves would require sensitive measurements of radio emissions, polarization patterns, or tiny changes in the motion of interstellar gas. Discovering such hidden waves would reveal new channels through which energy flows across cosmic environments, adding depth to our understanding of galactic dynamics. Exotic molecules may form in interstellar regions where chemistry should fail. Some areas of interstellar space are so cold and diffuse that chemical reactions should be extremely slow. Yet observations reveal molecules that seem too complex to form under such barren conditions. These exotic compounds range from simple organics to surprisingly intricate structures. They may arise from reactions on the surfaces of dust grains, triggered by faint starlight or cosmic rays. Alternatively, they might form within transient pockets of denser material that collapse and disperse quickly. The presence of these molecules challenges traditional ideas about where chemistry can occur. Their distribution influences the composition of forming stars and planets, seeding young systems with raw material that may play roles in later chemical evolution. Understanding how these unexpected molecules form requires a combination of laboratory experiments, modeling, and careful astronomical observation. Their existence highlights the creativity of nature in environments once thought chemically inactive. There might be unseen objects passing through our solar system. The solar system is vast, and many regions remain poorly explored. Objects with extremely dark surfaces or unusual compositions could drift through its outer reaches without reflecting enough light to be detected. Some may follow long, looping orbits that keep them far from the sun for most of their journey. Others might pass through only once, moving quickly and silently before returning to interstellar space. Their gravitational influence on known planets or comets might be too subtle to measure. Detecting such unseen bodies would require wide field surveys capable of spotting faint movement against the background of stars. Future missions that map the sky continuously may finally reveal these hidden travelers. Their discovery would expand our understanding of the solar system's population and shed light on the variety of objects that wander through our celestial neighborhood. The nature of quantum vacuum energy remains a deep mystery. Empty space is not truly empty. According to quantum physics, even the quietest vacuum contains a restless sea of energy that cannot be removed. This energy influences how particles behave and how fields interact, yet its true origin remains unclear. Calculations of vacuum energy often produce values far larger than anything observed in the real universe, suggesting that something in our understanding is incomplete. This energy might interact with space in ways that affect cosmic expansion, hinting at a possible connection to dark energy. It could also shape how fields fluctuate across vast distances. Because vacuum energy cannot be switched off or isolated, it can only be inferred indirectly through subtle measurements of particle behavior or delicate shifts in atomic states. Every attempt to explain it opens new questions, suggesting that vacuum energy may hold clues to deeper layers of reality that lie beyond current theories. Particles might pop in and out of reality from hidden realms. Quantum theory allows particles to appear briefly, interact, and vanish again, borrowing energy for a fleeting moment before conserving the total balance. These ephemeral phenomena are usually described as fluctuations, yet some researchers explore the idea that they may be linked to realms outside ordinary space. In these views, particles could momentarily dip into hidden layers of the universe before returning, creating short-lived signatures in measurable quantities. If such realms exist, they could host structures or fields that influence our world only through these brief interactions. Detecting these events directly is nearly impossible because they occur on unimaginably small scales and over extremely short intervals. Instead, scientists search for tiny deviations in particle collisions or unexpected patterns in the behavior of quantum fields. These fleeting appearances hint that the universe may include unseen dimensions that leave only the faintest traces. Quantum processes could influence the entire cosmos. Although quantum physics typically governs the world of the very small, some processes may have effects that ripple through the universe on enormous scales. Fluctuations in quantum fields during the earliest phases of cosmic history might have seeded the large-scale structure of galaxies. Tiny variations could have grown into the clusters and voids visible today. Quantum tunneling might also play roles in processes that affect the lifetime or evolution of the cosmos. Even the stability of space itself could depend on quantum interactions occurring throughout the vacuum. These possibilities suggest that the behavior of particles and fields on minute scales can shape the universe's fate. Understanding these influences requires bridging the gap between quantum theory and cosmology, two domains that operate under vastly different conditions. Their intersection remains one of the richest and most mysterious areas of modern physics. We do not know whether reality is continuous or pixelated. Mathematics often describes space and time as smooth and continuous, yet some theories propose that at the smallest scales they might be composed of discrete units. These tiny building blocks could determine the limits of how finely space and time can be divided. If reality is pixelated, then notions such as position, motion, and energy may behave differently near these fundamental scales. Experiments that probe extremely short distances or high energies are necessary to test this idea. Yet achieving such conditions is far beyond current car technology. Indirect hints may come from the behavior of gravitational waves or from subtle anomalies in the motion of particles. Determining whether the universe is continuous or discrete would reshape our understanding of geometry, physics, and the nature of spacetime. It remains one of the deepest unanswered questions in theoretical science. The universe might be haunted by virtual particles we cannot observe. Virtual particles constantly influence measurable properties, even though they do not appear in ways detectable as ordinary matter. They modify forces, shift energy levels, and alter how particles interact. These unseen contributors arise naturally from quantum fields that fill space, flickering into relevance only during specific processes. Though they vanish almost immediately, their effects accumulate across countless interactions, subtly shaping everything from atomic transitions to the behavior of electromagnetic fields. Virtual particles may also play roles in more mysterious phenomena, such as the vacuum energy problem or the behavior of space under extreme char conditions. Their existence reveals that much of reality operates through hidden processes that can be inferred only through their influence on observable quantities. Understanding them forces physicists to accept that unseen layers of activity underpin the physical world. Quantum fields could be more fundamental than space itself. Some interpretations of physics treat quantum fields as the primary ingredients of reality, with particles emerging as excitations of these fields. In this view, even space may not be a fixed stage, but a phenomenon that arises from deeper interactions among fields. The geometry of the universe, the strength of forces, and the behavior of matter could all be consequences of patterns embedded within these fields. If this perspective is correct, then space might not exist independently, but instead emerge from relationships among more basic components. Evidence for this idea appears in attempts to unify gravity with quantum theory. Some approaches suggest that space-time curvature reflects how information or entanglement is distributed within quantum fields. Uncovering the precise structure of this deeper layer remains an enormous challenge, yet its implications would transform our understanding of the universe. Quantum uncertainty might shape the large-scale structure of the universe. Quantum uncertainty dictates that particles cannot have perfectly defined positions or energies. During the universe's earliest moments, this uncertainty created tiny irregularities in the distribution of matter and energy. Over cosmic time, gravity amplified these irregularities, causing some regions to grow into galaxies while others became vast voids. Thus, the overall structure of the universe may owe its shape to random fluctuations at quantum scales. Even now, quantum uncertainty may guide processes such as the behavior of black holes or the properties of dark energy. The connection between microscopic indeterminacy and macroscopic structure illustrates the profound reach of quantum principles. Understanding this link requires studying both ancient cosmic light and simulations that model how small variations grow into immense formations. The idea that randomness on the smallest scales shaped the architecture of the cosmos remains one of the most remarkable insights of modern science. There could be unknown quantum states filling the entire cosmos. Quantum fields can occupy many possible states, some familiar and others never observed directly. The vacuum itself may represent only one configuration within a much larger landscape of possibilities. If the universe contains regions where fields settle into different states, these variations could influence the strength of forces, the masses of particles, or the behavior of space. Such states might be stable, long-lived, or ephemeral, leaving faint imprints on cosmic history. They could shape how matter formed, how galaxies evolved, or how the universe expands. Detecting them is extremely difficult because their signatures may be subtle or hidden within the background of known phenomena. Nevertheless, their existence is supported by some theoretical models that seek to explain the diversity of physical constants. Unknown quantum states may operate quietly throughout the cosmos, influencing reality in ways we have not yet recognized. Quantum effects might affect gravity in extreme situations. General relativity describes gravity as the curvature of spacetime, yet at very small scales or under extreme conditions, quantum processes may alter this behavior. Near the centers of black holes or in the earliest moments of the universe, the smooth geometry predicted by relativity may break down. Quantum fluctuations could produce irregularities, distortions, or limits on how sharply space can curve. These effects might prevent singularities or change the fate of collapsing matter. They could also influence how gravitational waves propagate or how black holes evaporate. Studying such situations requires combining quantum theory with gravity, a task that continues to challenge physicists. Although indirect hints appear in theoretical models, direct evidence remains elusive. Understanding how quantum processes modify gravity would open a window into the deepest workings of the universe. Reality might depend on information in ways we do not yet understand. Emerging ideas in physics suggest that information could play a central role in shaping reality. In this view, the properties of particles, the behavior of forces, and even the structure of space may reflect patterns of stored or distributed information. Some theories propose that the universe's geometry arises from networks of quantum entanglement. Others argue that physical laws follow from principles of information preservation. These concepts connect areas once thought unrelated, linking thermodynamics, quantum mechanics, and gravity. Evidence appears in the behavior of black holes, which seem to store vast amounts of information in unexpected ways. If reality is indeed governed by informational principles, then matter and space may be secondary expressions of deeper rules. Understanding these rules would revolutionize physics, offering a new framework for exploring the universe. Fast radio bursts might come from processes we have never considered. Fast radio bursts are brief flashes of radio energy that last for only a fraction of a second. Yet in that instant, they release more power than many stars, produce in long stretches of time. Their origins remain deeply mysterious. Some repeat, others fire only once, and many appear from directions with no obvious source nearby. While theories range from magnetars to collisions to strange plasma behaviors, the diversity of signals suggests that at least some may come from mechanisms not cruel, yet imagined. Their extreme brightness hints at compact sources, but their patterns sometimes show irregularities that challenge existing models. Because they travel across vast distances, they carry information about the medium between galaxies. Yet that information is difficult to interpret. Some bursts arrive with structures too complex for current explanations. As new instruments capture more events, the puzzle deepens, pointing to physical processes that may stretch or reshape our understanding of cosmic energy. Some cosmic signals could originate from unknown natural engines. Across the sky, telescopes detect signals that do not fit cleanly into known categories. Some are too sustained to be bursts, yet too irregular to be typical emissions from stars or galaxies. These signals may arise from natural engines that have not yet been identified. Extreme magnetic fields, turbulent environments, and interactions between exotic particles could generate emissions unlike any familiar process. Some signals vary in brightness or frequency in ways that do not correspond to standard astrophysical cycles. Others show sudden changes that hint at hidden mechanisms operating deep within cosmic structures. The galaxy may host dynamic engines that activate under conditions we have not yet observed directly. Understanding these signals requires gathering more data, refining analysis methods, and keeping an open mind about processes that may exist outside established frameworks. Each unexplained pattern offers a clue to unseen behavior in the universe. There might be flashes of energy we have not learned how to detect. The universe produces many kinds of emissions, yet our instruments detect only a narrow range of possible signals. Some energy bursts may be too faint, too brief, or emitted at wavelengths beyond the reach of existing technology. These flashes could occur during rare cosmic events or in environments where matter and radiation behave in unfamiliar ways. They might carry information about extreme physics, exotic particles, or transitions that occur deep within compact objects. If we lack detectors tuned to the right frequencies, these events pass unnoticed. As new observatories expand sensitivity across previously unexplored ranges, astronomers may uncover flashes that reveal unknown processes. Hidden bursts could help explain unexplained cosmic variations or missing energy signatures. The possibility that entire classes of events remain invisible underscores how much of the universe operates beyond our current perception. Some cosmic rays arrive with energies we cannot explain. Cosmic rays are high-energy particles that strike Earth from space. Most originate from known processes such as supernova remnants or active galaxies. Yet a small fraction arrive with energies far too high for these sources. These extreme particles challenge theories of acceleration because no known environment appears capable of imparting such incredible energy. They may arise from rare cosmic phenomena, interactions involving exotic particles, or processes that occur near the boundaries of extreme astrophysics. Their paths through space bend under magnetic fields, making it difficult to trace them back to their origins. This obscures the nature of the mechanisms that launched them. Studying these rare particles may reveal new physics operating at energies far beyond those produced by any human-made accelerator. They represent one of the most direct windows into high-energy processes that the universe keeps largely hidden. There could be signals hidden in the noise of the universe. Astronomical data contains vast amounts of background noise created by natural processes, such as dust emission, cosmic microwave radiation, faint starlight. Within this noise, subtle signals may be buried. These signals could originate from phenomena too weak or too rare to stand out clearly. Some might be patterns that repeat only over long timescales, while others might appear as barely detectable variations. New analysis techniques using advanced modeling and machine learning may help uncover these hidden signs. If such signals exist, they could reveal unknown objects, transitions, or interactions. They might also provide clues about processes that shaped the early universe or influence cosmic structure today. The possibility that important information lies concealed within noise adds depth to the challenge of interpreting astronomical observations. Some gamma-ray bursts might reveal unknown cataclysms. Gamma-ray bursts are among the brightest explosions known, often linked to collapsing massive stars or merging neutron stars. Yet a subset of these bursts do not match established categories. Their durations, intensities, or afterglows differ from expectations. Some appear too short for stellar collapse, yet too long for known merger processes. Others lack expected signatures in lower energy wavelengths. These anomalies suggest that additional kinds of cosmic cataclysms may exist, involving mechanisms not yet understood. They might arise from exotic stars, unusual magnetic events, or interactions involving compact objects in unexpected configurations. Because gamma rays carry enormous energy, even small differences in their emission mechanisms reveal profound variations in underlying physics. These unusual bursts may hold clues to rare or extreme events that occur infrequently, but shape the evolution of energetic regions of the universe. There could be rhythms in cosmic activity we have not yet noticed. Across the cosmos, many processes follow cycles, from stellar pulsations to galactic interactions. Yet some rhythms may be so slow, faint, or irregular that they escape detection. These long-term or subtle cycles might govern changes in magnetic fields, variations in emission from compact objects, or shifts in large-scale cosmic structures. They could also operate on timescales far longer than human history, making them difficult to observe without continuous long-term monitoring. Detecting such rhythms might require observing many objects simultaneously or analyzing historical data for patterns. If these cycles exist, they could reveal coordinated behavior across distant regions or provide insights into processes that evolve gradually. Cosmic rhythms may be hidden background patterns shaping the dynamic behavior of the universe. Some astronomical events might repeat on timescales longer than human history. Certain cosmic phenomena occur so infrequently that no human has witnessed more than a single instance. Ancient star eruptions, rare collisions, and slow changes in stellar interiors may repeat only after long intervals. Some stars may undergo dramatic transformations on cycles lasting thousands or millions of years. These events could influence surrounding environments, trigger waves of star formation, or reshape cosmic structures. Because these timescales extend far beyond recorded observations, it is difficult to confirm whether certain phenomena repeat or are singular occurrences. As data accumulates over generations, astronomers may begin to detect signs of cyclic behavior. Understanding these long-term processes will reveal how objects evolve over deep time and how seemingly stable systems undergo changes on scales that transcend human experience. There might be transient phenomena too brief for current instruments. Many astronomical events occur in the blink of an eye, releasing energy in extremely short bursts. If these flashes last only microseconds or nanoseconds, current detectors may not be fast enough to register them. Such transient events might arise from rapid magnetic reconnection, particle interactions in extreme environments, or collisions involving small bodies. Detecting them requires instruments with very high temporal resolution and continuous monitoring. Because they vanish almost instantly, their properties may differ significantly from longer events. These fleeting phenomena may play important roles in transferring energy, shaping radiation fields, or influencing cosmic environments in ways not yet understood. Their discovery would expand the known spectrum of celestial behavior. The universe could emit glows from processes outside known physics. Some aspects of cosmic radiation may come from mechanisms that do not fit into current models of particle physics or astrophysics. These glows could be diffuse emissions spanning large regions or faint backgrounds produced by unfamiliar interactions. They might emerge from exotic particles, transitions in quantum fields, or processes linked to dark matter. Their spectra would differ from ordinary starlight or thermal emission, making them difficult to identify within existing datasets. Detecting such glows requires careful separation from known backgrounds and creative approaches to interpreting faint signals. If confirmed, they could reveal entirely new categories of energy release that operate quietly across the universe. Life might arise in conditions completely foreign to us. On Earth, life depends on liquid water, moderate temperatures, and a familiar set of chemical reactions. Yet the universe contains environments far outside these boundaries. There are worlds with crushing pressures, extreme cold, violent radiation, or atmospheres filled with chemicals toxic to known organisms. In such places, life could emerge through pathways unlike anything in terrestrial biology. Reactions that fail in Earth-like settings might flourish under different conditions. Energy could come from sources unrelated to sunlight, such as deep chemical gradients, magnetic interactions, or slow geological processes. Structures that resemble cells might form from exotic materials that behave predictably only under extreme conditions. These possibilities force us to consider that life is not a narrow phenomenon, but a process shaped by its environment. If such unfamiliar life exists, detecting it will require methods that do not rely on assumptions drawn from a single example. It expands the search for living systems into realms we once dismissed as barren. The building blocks of life could form in places we would not expect. Complex organic molecules appear in interstellar clouds, on icy comets, and within the atmospheres of giant planets. These environments seem inhospitable, yet they host chemical reactions that produce ingredients essential for life. Radiation, cold temperatures, and dust grains provide surfaces and energy sources that drive unusual chemistry. Some clouds contain long carbon chains, while cometary ice traps molecules that may have formed in ancient cosmic regions. Even gas giant atmospheres show hints of compounds that could serve as precursors to biological structures. These materials may later seed young planets or accumulate on surfaces where conditions eventually allow life to develop. The universe seems to be a factory for organic components, producing them across environments with no resemblance to Earth. Understanding these processes helps explain how life's essential ingredients may arise long before planets are ready to host living systems. The universe might host life based on chemistry we do not yet understand. Life on Earth uses a narrow set of molecules built around carbon, hydrogen, oxygen, and nitrogen. Alternative forms could rely on entirely different chemistries. Some environments may support molecules that remain stable only under extreme pressures or temperatures. Solvents other than water could permit reactions that assemble structures unfamiliar to terrestrial biology. Elements such as silicon, sulfur, or phosphorus might form the basis for self-sustaining systems that process energy and replicate. These hypothetical life forms would not resemble microbes, plants, or animals. Their metabolic pathways, structural components, and modes of growth could be unrecognizable. Detecting such life requires moving beyond Earth-centered assumptions and considering signatures based on unexpected patterns in heat, chemistry, or energy flow. The variety of possible chemistries suggests that life may exist in forms that challenge every definition currently used in science. Life elsewhere could evolve in environments we cannot imagine. Planets and moons throughout the universe experience conditions far different from those found on Earth. Some are locked in perpetual darkness, while others endure long cycles of intense heat and extreme cold. Certain worlds have thick atmospheres, boiling oceans, or surfaces coated in exotic materials. Life, if present, would adapt to these conditions using strategies shaped by unique evolutionary pressures. Organisms might rely on energy from tidal forces, deep interior heat, or chemical gradients created by unusual minerals. They might develop structures suited for dense atmospheres or low gravity. Evolution could produce behaviors and sensory systems unlike anything on Earth. Considering such diversity widens the scope of what living worlds may look like and prepares us to recognize life even when it emerges under extraordinary terror. Conditions. They could be biological processes happening in extreme cosmic settings. Beyond planets, biological activity might occur in environments that seem completely unsuitable. Certain asteroids contain materials that could support simple chemical cycles. Subsurface oceans on icy moons may host thermal vents where living systems take root. Free floating objects in interstellar space could contain internal heat sources, maintaining pockets of liquid beneath icy crusts. Even dust-laden clouds may shelter molecules capable of developing into primitive systems. These possibilities show that biology might not require stable surfaces or traditional planetary conditions. Instead, it could arise wherever chemical complexity and energy sources align. Studying these environments expands the search for life into regions previously considered irrelevant for biology. Life might leave traces we do not yet know how to recognize. Most searches for life rely on signatures familiar from Earth, such as oxygen, methane, or chlorophyll-related pigments. Yet alien life may produce byproducts unlike anything found in terrestrial ecosystems. It might release gases that appear inert or unimportant, create patterns in heat emissions, or alter minerals in subtle ways. Such signatures may blend into background noise or be dismissed as ordinary geological effects. Recognizing them requires new frameworks that consider a wide range of possible biosignatures. These may include unusual chemical ratios, unexpected atmospheric cycles, or repeating patterns not caused by natural processes. Understanding how life alters its environment in unfamiliar ways will be crucial for identifying living systems across the universe. The universe could host civilizations with unknown technological signatures. If intelligent life exists elsewhere, its technologies may not resemble radio transmissions, satellites, or optical signals. Advanced civilizations might use energy sources invisible to current detectors or construct structures that blend into natural backgrounds. They could manipulate magnetic fields, reshape planetary atmospheres, or leave imprints in radiation fields that appear natural to us. Their communication methods may not rely on electromagnetic waves at all. Technologies based on principles we have not yet discovered might operate across scales or frequencies outside human detection capabilities. Searching for such civilizations requires expanding our expectations beyond familiar ideas. Unknown signatures may be hiding in existing data, waiting for new perspectives to reveal them. Some worlds might hold ecosystems entirely unrelated to our own. On distant planets, ecosystems could develop with species that do not share Earth's genetic or biochemical foundations. Their interactions might follow rules shaped by alien environments, such as constant storms, dim starlight, or abundant minerals unknown on Earth. Food webs might rely on chemical energy rather than sunlight. Organisms could use materials that are unstable in terrestrial conditions, forming tissues and structures that behave unpredictably when compared to Earth-based life. Such ecosystems would rewrite our assumptions about how living communities form, interact, and evolve. Their discovery would offer insight into the adaptability of life and the range of ecological possibilities available across the universe. Life could exist in forms that do not rely on planets. Floating habitats in interstellar space, suspended environments within giant planet atmospheres, or stable structures around stars could all support life. Some systems may provide heat and chemical gradients without needing a solid surface. Life might arise in clouds of organic particles or within long-lived vortices in thick atmospheres. It could occupy magnetic structures or exist within networks of complex molecules drifting through space. These possibilities challenge the idea that planets are the primary homes for biology. Instead, life may thrive wherever conditions allow complexity and energy flow, even if no planet is present. The universe may reveal forms of life that change our idea of what life is. As we explore more worlds and detect more signals, we may encounter systems that blur the line between life and non-life. These forms could challenge the definitions used in biology, forcing scientists to rethink concepts such as metabolism, growth, and reproduction. Some systems might rely on processes unfamiliar to Earth's chemistry, while others might operate at scales too small or too large for traditional categories. Discovering such life would expand the boundaries of science, offering new perspectives on how matter organizes itself into living patterns. The universe may hold examples that redefine the very meaning of being alive. Some asteroids are packed with precious metals. While most asteroids are made of rock or carbon-rich material, a rare class called M-type asteroids are composed largely of metals such as iron, nickel, and even platinum. One famous example, 16 Psyche, is thought to be the exposed core of a failed protoplanet, stripped of its outer layers. Its estimated metal content is so great that, in theory, it could be worth more than all the money on Earth. Though, of course, mining and transporting it would be extraordinary challenge. Studying these metallic asteroids can reveal how planetary cores form and how the early solar system evolved. They may also be future targets for space mining missions, offering resources for building in space rather than hauling materials from Earth. A day on Venus lasts longer than its year. Venus rotates so slowly on its axis that one full rotation takes about 243 Earth days. However, it orbits the Sun in just 225 Earth days, meaning a day on Venus is longer than its year. Even stranger, Venus rotates in the opposite direction to most planets, so the Sun appears to rise in the west and set in the east. This slow spin may be the result of ancient collisions or tidal interactions with the Sun. Combined with its thick carbon dioxide-rich atmosphere and extreme surface temperatures, Venus's rotation creates one of the most inhospitable environments in the solar system. Yet beneath its clouds, volcanic landscapes and towering mountains hint at a complex geological history we are only beginning to understand. The coldest place in the universe is colder than empty space. In the Boomerang Nebula, located about 5,000 light-years away, temperatures plunge to just 1 degree above absolute zero, colder than the fainter core. Heat, left over from the Big Bang. This deep freeze occurs because gas from a dying star is expanding so rapidly that it cools beyond the background temperature of space itself. The Boomerang Nebula's eerie hourglass-shaped cloud glows faintly in visible light, but shines brightly in radio wavelengths. It is a natural cosmic freezer, preserving its gas and dust in conditions almost unimaginable on Earth. Eventually, the star at its center will heat up again, dispersing the nebula, but for now, it remains the chilliest known place in the universe. Entire stars can be eaten by black holes. When a star drifts too close to a supermassive black hole, tidal forces can tear it apart in a process called a tidal disruption event. The star's material is stretched into a long, glowing stream, with much of it spiraling into the black hole's accretion disk. As the gas falls inward, it heats to millions of degrees, emitting powerful bursts of light that can outshine the galaxy for months. The rest of the star's remains may be flung back into space at incredible speeds. These cosmic meals are rare for any given galaxy, but when they happen, they offer astronomers a chance to study black holes in action. The event is both beautiful and violent, a reminder that even massive luminous stars are fragile when faced with the gravitational hunger of a black hole. Saturn could float in a large enough ocean. Saturn's average density is less than that of water, about 0, 69 grams per cubic centimeter, making it the only planet in the solar system that would float if there were an ocean large enough to hold it. This low density comes from its composition, mostly hydrogen and helium, with only a small core of heavier elements. Of course, no real ocean could contain a planet, but the thought experiment shows how different Saturn is from rocky worlds like Earth. Its gaseous nature also means it has no solid surface. If you descended into its atmosphere, you would pass through layers of cloud and increasing pressure until you were crushed by its deep interior. The planet's lightness contrasts with the immense beauty of its rings, making Saturn one of the most striking worlds in the night sky. The hottest planet in the solar system isn't the closest to the Sun. Mercury may be nearest to the Sun, but Venus holds the record for the highest average surface temperature, about 465 degrees Celsius. This is due to its thick atmosphere of carbon dioxide, which traps heat through a runaway greenhouse effect. Clouds of sulfuric acid reflect sunlight, but they also lock in the heat already on the surface, preventing it from escaping into space. The result is a world where metal melts, and any spacecraft lasts only hours before succumbing to the heat. Venus's extreme conditions make it a cautionary example of how greenhouse gases can transform a planet. Yet beneath its hostile skies lies a landscape of vast plains, volcanoes, and mountains, hinting at a geologic complexity that continues to intrigue our scientists. Some moons are geologically active. Of all moons are frozen, dead worlds. Jupiter's moon Io is the most volcanically active body in the solar system, with hundreds of active volcanoes powered by tidal heating from Jupiter's immense gravity. Saturn's moon Enceladus has geysers that spray water vapor and ice particles into space, feeding Saturn's ring. Even Neptune's moon Triton shows signs of past cryovolcanism, where water, ammonia, or methane erupt instead of molten rock. Geological activity suggests that some moons may have internal heat sources capable of supporting subsurface oceans and potentially life. These active moons are windows into processes that occur far from the warmth of the sun, proving that the solar system is far more dynamic than it might appear at first glance. You could fit all the planets between Earth and the Moon. The average distance between Earth and the Moon is about 384,000 kilometers. Surprisingly, this is enough space to line up all the other planets in the solar system, Mercury through Neptune, side by side, with a little room to spare. This mental image challenges our sense of scale, reminding us that even our close celestial neighbor is much farther away than it appears. The moon's apparent size in the sky is an illusion created by perspective in reality. Space is vast, even in our own cosmic backyard. Thinking about this scale can make lunar missions feel all the more impressive. Every spacecraft to the moon has crossed a gap large enough to hold the worlds of our solar system in a single row. The Milky Way is surrounded by a halo of invisible matter. Our galaxy doesn't end where the stars fade from view. Surrounding it is a massive halo of dark matter, an invisible form of mass that doesn't emit or absorb light, but exerts a powerful gravitational pull. This halo extends far beyond the visible disk of the Milky Way, shaping the orbits of stars and influencing how galaxies form. We can't see dark matter directly, but its presence is revealed through its effects on the motion of stars and gas. Some estimates suggest the halo contains much more mass than all the stars in the galaxy combined. Without it, the Milky Way would fly apart under its own rotation. This unseen structure is a reminder that most of the matter in the universe is something we cannot see, at least not yet. Time moves differently in strong gravity. According to Einstein's general theory of relativity, time passes more slowly in stronger gravitational fields. This means that near a massive object, such as a black hole or even Earth's surface, time moves slightly slower compared to regions with weaker gravity. The effect is tiny on Earth but becomes dramatic near extreme masses. In theory, an astronaut orbiting close to a black hole could experience only a few hours while years pass for someone far away. This phenomenon, known as gravitational time dilation, has been confirmed by experiments with atomic clocks on airplanes and satellites. It's not just a science fiction idea, it's a measurable reality that links space, time, and gravity in a single, elegant framework. The universe is full of wandering black holes. While supermassive black holes anchor the centers of galaxies, smaller black holes can roam freely through space. Some form from the collapse of massive stars and drift through the galaxy, invisible unless they interact with surrounding matter. Others may be ejected from their home systems by gravitational encounters or even the recoil from black hole mergers. Detecting them is difficult, but astronomers have begun identifying candidates by watching for their gravitational lensing effects on background stars. These wandering black holes are like cosmic ghosts, drifting silently through the galaxy, each one a point where space and time fold in on themselves. Some stars are powered by helium instead of hydrogen. Most stars fuse hydrogen into helium in their cores, but when the hydrogen runs out, heavier stars can ignite helium fusion, creating carbon and oxygen. In rare cases, stars lose their outer hydrogen layers entirely, revealing helium-burning cores from the start. These helium stars shine hotter and bluer than normal stars and have much shorter lifespans. They are thought to form through mass transfer in binary systems, where one star strips the outer layers from its companion. Studying them gives astronomers a window into late-stage stellar evolution and the processes that lead to supernova explosions. Astronomers have detected planets around pulsars. Pulsars are rapidly rotating neutron stars that emit beams of radiation, and in 1992, astronomers found planets orbiting Gao. 1. The first confirmed exoplanets ever discovered. These pulsar planets are exposed to intense radiation and would be inhospitable to life as we know it, but their existence shows that planets can form in even the cellular, most extreme environments. They may be remnants of a destroyed star or material captured after the pulsar's birth. The precision of pulsar timing makes it possible to detect the tiny gravitational tug of orbiting planets, revealing their presence even light years away. Light from distant stars can bend around massive objects. In Einstein's general relativity, mass bends the fabric of space-time, and light follows that curve. This means a massive object, such as a galaxy or black hole, can act like a lens, bending and magnifying the light of something behind it. Known as gravitational lensing, this effect allows astronomers to see galaxies so distant that their light would otherwise be too faint to detect. In some cases, the background object appears stretched into arcs or multiplied into several images. Gravitational lensing not only gives us a cosmic magnifying glass, but it also lets scientists map the distribution of dark matter, which causes additional bending despite being invisible. It's a reminder that space is not a flat stage, but a dynamic, warped landscape, where light itself is guided by the invisible curves of gravity. Our Sun is just one of hundreds of billions of stars in the Milky Way. From Earth, the Sun feels unique, but it is only one star among an estimated 200 to 400 billion in our galaxy. Many are larger or smaller, hotter or cooler, younger or older. Some have planets, some do not. The Sun is a G-type main sequence star, fairly ordinary by cosmic standards, but perfect for sustaining life on Earth. The sheer number of stars in the Milky Way means that even if a tiny fraction have habitable planets, there could be millions of worlds where life might arise. Every point of light we see in the night sky belongs to this vast stellar city, and most of the galaxy remains hidden from our view, its stars too faint or too far away for the naked eye to detect. There are stars that appear to blink out of existence. Astronomers have observed stars in old photographic plates that no longer seem to exist today. Some may have undergone dramatic changes, such as fading into white dwarfs or collapsing into black holes. Others might be explained by observational errors or unusual transient events like supernovae that were missed in real time. But a few cases remain mysterious, with no obvious explanation. These vanishing stars spark speculation about exotic phenomena, from failed supernova to entirely new kinds of astrophysical events. They remind us that even with our modern technology, the universe can still surprise us, and that our cosmic census is far from complete. Entire galaxies can merge into one. When galaxies collide, their stars rarely collide directly because of the vast distances between them. Instead, their mutual gravity pulls them into new shapes, creating streams of stars and clouds of gas that ignite bursts of star formation. Over time, sometimes hundreds of millions of years, the galaxies settle into a single, larger system. The Milky Way itself is the product of many past mergers and will one day merge with Andromeda. These cosmic unions reshape the architecture of the universe, recycling old stars, creating new ones, and building ever larger structures in the cosmic acrus. Web. Space can stretch and shrink without anything moving. In the framework of general relativity, space is not a fixed backdrop. It can expand, contract, and warp. During cosmic inflation, just after the Big Bang, space expanded faster than light, carrying matter with it. Even today, the expansion of the universe is stretching the distances between galaxies. On smaller scales, the opposite can happen. Gravity can pull matter together, shrinking space locally and binding galaxies into clusters. This means objects can move apart without actually traveling through space. Instead, the space between them is growing. It's one of the most counterintuitive aspects of modern cosmology, showing that our everyday notions of movement don't always apply on a cosmic scale. The Andromeda Galaxy is already visible to the naked eye. On a dark, clear night, far from city lights, you can see a faint, elongated smudge in the constellation Andromeda. This is the Andromeda Galaxy, over 2 million light-years away, the most distant object visible without a telescope. What you're seeing is the combined light of 1 trillion stars, shining across unimaginable distances. In photographs, Andromeda reveals spiral arms, dust lanes, and satellite galaxies, but even to the naked eye, its presence is humbling. It's not just a point of light, like the stars in our own galaxy. It's an entire island universe, slowly making its way toward us for an eventual merger, billions of years from now. Jupiter's magnetic field is strong enough to shrink your phone battery. Jupiter's magnetic field is the strongest of any planet in the solar system, about 20,000 times more powerful than Earth's. It creates intense radiation belts filled with high-energy particles, dangerous to both spacecraft and humans. If you could somehow stand within this field with an electronic device, the charged particles would quickly interfere with its operation, potentially draining or damaging it. This magnetic shield is generated by Jupiter's rapidly rotating metallic hydrogen interior and extends millions of kilometers into space, even now capturing some of Jupiter's moons within its influence. It's a planetary-scale force field, invisible but immensely powerful. Some stars explode without warning. While many supernovae are predictable in theory, occurring when a star reaches a certain stage in its life, some appear to happen unexpectedly. These may be caused by sudden instabilities in the star's core or by interactions with a close companion star that trigger collapse. In rare cases, the star might even explode more than once, ejecting outer layers in stages. Such events challenge our understanding of stellar evolution and remind us that even well-studied stars can harbor surprises. Observing them helps refine our models of how stars live and die. There are planets made almost entirely of gas. Gas giants like Jupiter and Saturn are composed mostly of hydrogen and helium, with only small rocky cores deep inside. Beyond our solar system, astronomers have found even more extreme examples. planets larger than Jupiter with densities so low they could almost float him. Water. These super-puffer planets may have thick atmospheres and tiny solid cores, making them resemble miniature stars more than Earth-like worlds. They often orbit close to their stars, where intense heat can inflate their atmospheres even further. Studying them helps us understand how planetary systems form and evolve. The universe may be infinite in size. Current observations suggest that on large scales, the universe is flat, meaning it could extend forever. If true, there may be regions so far away that their light will never reach us, no matter how long we wait. An infinite universe would contain endless variations of galaxies, stars, and planets, and perhaps even regions where conditions are identical to our own. While we cannot directly confirm infinity, the possibility stretches our imagination to its limits. It's a concept both exhilarating and humbling. No matter how far we look, there might always be more. We can see galaxies as they were billions of years ago. Light doesn't travel instantly. It moves at about 300,000 kilometers per second. Across the vast distances of space, this means we see celestial objects not as they are now, but as they were when their light began its journey. When we look at a galaxy 10 billion light-years away, we're seeing it 10 billion years in the past. The Hubble Space Telescope has captured images of tiny, faint galaxies from a time when the universe was less than 1 billion years old. These ancient snapshots show young galaxies bursting with new stars, colliding and evolving into the giants we see nearby today. In a sense, telescopes are time machines, allowing us to look back into an era long before Earth even existed. The farther we look, the closer we get to glimpsing the universe's earliest moments, frozen in light that has crossed cosmic history. Space is not completely empty. The vastness between stars and galaxies might seem like a perfect vacuum, but space is never truly empty. Even in the loneliest stretches of intergalactic space, there are stray atoms, particles, and the faint glow of background radiation from the Big Bang. In our solar system, the space between planets is filled with the solar wind, a constant stream of charged particles from the sun. Cosmic rays from distant supernova and other energetic events also pass through, striking spacecraft and even our own planet. On larger scales, immense filaments of gas and dark matter connect galaxies like threads in a cosmic web. These sparse but ever-present contents of space are invisible to the naked eye, yet they shape the movement, chemistry, and temperature of the universe. Even in what seems like nothingness, the universe hums with a faint and constant presence. The largest black holes are billions of times more massive than the Sun. At the centers of many galaxies lie supermassive black holes, with masses ranging from millions to billions of suns. The largest known, TOM 618, is estimated at over 60 billion solar masses, a gravitational anchor so powerful it shapes the movement of entire galaxies. These titans likely grew over billions of years, devouring stars, gas, and smaller black holes, or forming in the dense hearts of early galaxies. While their event horizons are immense, larger than our entire solar system, they remain invisible, their presence revealed only by the behavior of nearby matter. Gas spiraling into these giants' heats to extreme temperatures, emitting radiation that can be detected across the cosmos. Despite their name, supermassive black holes are not empty voids, but regions where gravity overwhelms all other forces, creating a point from which not even light can escape. There are galaxies that spin in the opposite direction to most others. Most spiral galaxies, including our Milky Way, rotate in a direction determined by how they formed. But astronomers have discovered rare galaxies whose stars and gas rotate the wrong way compared to the majority. These counter-rotating galaxies may have experienced dramatic collisions or mergers that flipped their rotation, or they may have absorbed streams of gas moving in an opposing direction. In some cases, only certain parts of the galaxy, like the inner disk or outer halo, spin backwards, creating a cosmic dance of competing motions. These unusual rotations provide clues about the violent and unpredictable events in galactic history. Studying them helps astronomers piece together how galaxies grow and evolve, showing that the universe's structures are shaped as much by chaos and chance as by orderly formation. Cosmic rays pass through your body every second. Invisible and harmless in small doses, cosmic rays are high-energy particles, mostly protons, that constantly rain down from space. They originate from powerful events like supernova, colliding neutron stars, and even active galaxies with supermassive black holes. When they strike Earth's atmosphere, they create showers of secondary particles that reach the ground and even pass through our bodies. Right now, several cosmic ray particles are traveling through you, unnoticed. Astronauts beyond Earth's protective atmosphere experience them more intensely, sometimes seeing flashes of light in their vision as particles interact with their eyes. While our planet's magnetic field and atmosphere shield us from most harmful effects, cosmic rays are a reminder that we live in a universe filled with unseen forces constantly passing through us, connecting us in a small way to the most energetic events in the cosmos. Some stars are so dense, they defy imagination. Neutron stars are the remnants of massive stars compressed into an object just 20 kilometers across, yet containing more mass than the Sun. In these conditions, atoms are crushed, and matter exists as a sea of neutrons packed so tightly that a single teaspoon would weigh billions of tons. The density is so extreme that its gravitational pull distorts the path of light and slows time. The surface is a thin crust over a core that may contain exotic states of matter we have never recreated on Earth. Neutron stars can spin hundreds of times per second, generating intense magnetic fields that shape their surroundings. They are the edge of physics as we know it, places where our current understanding of matter and energy begins to break down. A single supernova can outshine an entire galaxy. When a massive star dies in a supernova, the explosion can release more energy in a few weeks than the Sun will emit in its entire lifetime. For a brief period, the dying star can outshine all the billions of stars in its host galaxy combined. These cosmic explosions are visible across vast distances and serve as important markers for measuring the expansion of the universe. The shock waves from supernova sweep through space, triggering the birth of new stars in nearby gas clouds. They also forge heavy elements, iron in your blood, gold in jewelry, and scatter them across the cosmos. Without supernova, planets like Earth would lack the raw materials for life. They are both an end and a beginning, cosmic punctuation marks in the story of stellar evolution. The northern lights are caused by solar winds. Auroras occur when charged particles from the Sun, carried by the solar wind, interact with Earth's magnetic field and atmosphere. These particles are guided toward the polar regions, where they collide with atoms of oxygen and nitrogen high in the atmosphere. The energy from these collisions is released as light, painting the sky in shimmering curtains of green, pink, purple, and red. The exact colors depend on the type of atom and the altitude of the interaction. Auroras are not unique to Earth. They have been observed on Jupiter, Saturn, and even distant Uranus. They are living proof that the Sun and Earth are connected in a constant exchange of energy, and they remain one of nature's most beautiful and hypnotic displays. There are moons with atmospheres thicker than Earth's. Saturn's moon Titan has an atmosphere denser than our own, composed mostly of nitrogen with traces of methane and other gases. Its thick haze shrouds the surface, hiding a landscape of lakes, rivers, and seas of liquid methane and ethane. The pressure on Titan's surface is about 1.5 times that of Earth's, and temperatures are far below freezing. Despite the cold, Titan's atmosphere supports a methane cycle similar to Earth's water cycle, with clouds, rain, and seasonal changes. This dense atmosphere and complex weather make Titan one of the most Earth-like worlds in the solar system, albeit one that is deeply alien. The edge of the observable universe is moving away from us. Because the universe is expanding, the most distant regions are receding from us faster than the speed of light, not because they're moving through space quickly, because space itself is stretching. This means the edge of what we can observe is constantly changing. Light from beyond a certain distance will never reach us, no matter how long we wait. Currently, the observable universe has a radius of about 46 billion light-years, but its true size may be much greater, possibly infinite. As time passes, more galaxies will slip beyond our reach, leaving only those nearby visible. It's a reminder that the night sky we see today is just a temporary view, and that the cosmos will look very different to observers in the far future. Dark energy is pushing the universe apart. In the late 1990 ES, astronomers discovered something astonishing. The expansion of the universe isn't slowing down under gravity, as expected. It's speeding up. The cause appears to be a mysterious phenomenon called dark energy, which makes up about 70% of the cosmos. Unlike dark matter, which pulls with gravity, dark energy acts as a kind of cosmic repulsion, stretching space itself. Its exact nature is unknown, but its effects are everywhere. Distant galaxies are receding faster than they once did, and over billions of years, dark energy will push them so far away that their light can never reach us. In the far future, the universe could become a lonely place, with only our local group of galaxies remaining visible. Understanding dark energy is one of modern science's greatest challenges, because it may hold the key to the universe's ultimate fate. Some black holes are surrounded by swirling disks of fire. Material falling toward a black hole doesn't plunge straight in. Instead, it forms an accretion disk, a swirling, flattened ring of gas and dust heated to millions of Ks, degrees by friction and gravity. These disks glow brilliantly in X-rays and other high-energy light, making them visible to telescopes even though the black hole itself is invisible. In the most active galaxies, these disks can outshine the combined light of every star, earning them the name quasars. The inner edge of the disk spins close to the speed of light, and magnetic fields can channel some of the material into powerful jets that extend for thousands of light years. Accretion disks are extreme environments where matter is torn apart, heated, and transformed, the final stage before crossing the event horizon and vanishing forever. Stars can be torn apart by tidal forces. When a star strays too close to a black hole, the difference in gravitational pull between its near and far sides can rip it apart in a violent process called spaghettification. The star's material stretches into a long stream, with some flung into space and the rest spiraling toward the black hole, heating into a bright flare that can outshine the host galaxy for months. These tidal disruption events are rare, but they provide astronomers with valuable opportunities to study both black holes and the final moments of doomed stars. The physics behind them is the same as ocean tides on Earth, gravity pulling more strongly on one side than the other, but on an incomprehensibly more destructive scale. Astronomers have found a planet where it rains glass. Far from Earth, in the constellation Pegasus, lies a planet called HD 189733b, a gas giant orbiting so close to its star that its skies are a deep, vivid blue. But this color isn't from oceans or clear air, it's from silicate particles high in the atmosphere, which condense into glass-like droplets. Supersonic winds whip these particles sideways at speeds of up to 7,000 kilometers per hour, meaning that on this world, it quite literally rains chaos. Shards of glass hurtling through the air in a deadly storm. It's a place where beauty and danger exist in the same moment, a sapphire world glinting in starlight, but one no spacecraft could survive. Some galaxies contain trillions of stars. While the Milky Way holds hundreds of billions of stars, some galaxies, such as giant ellipticals, are far more massive, containing trillions. These cosmic giants often form through multiple mergers over billions of years, growing larger with each collision. Their sheer size means they can dominate galaxy clusters, influencing the motion of smaller galaxies around them. At their centers often lie supermassive black holes, many times the mass of the Milky Ways. From a distance, these galaxies look smooth and featureless, but up close they are densely packed with ancient stars, each one a sun with its own history. They are vast stellar metropolises, reminders of how diverse and grand the architecture of the universe can be. Time may flow differently in other parts of the universe. Einstein's theory of relativity shows that time is not absolute. It can pass at different rates depending on gravity and motion. In regions with intense gravitational fields, like near black holes, time slows relative to areas with weaker gravity. Even velocity can change the passage of time. A spacecraft moving near the speed of light would experience time more slowly than observers at rest. This means that across the universe, now is not the same everywhere. The idea has strange implications. Two events happening at the same moment from one viewpoint may occur at different times from another. The cosmos, it seems, doesn't have a single clock, but countless local ones, each ticking to the rhythm of its own surroundings. There are clouds of alcohol in space. In the vast molecular cloud Sagittarius B2, near the center of the Milky Way, astronomers have detected massive quantities of ethanol, the same type of chemo. Alcohol found in drinks. This cloud spans hundreds of light years and contains enough alcohol to fill trillions of pints. Of course, it's mixed with other chemicals and is far from drinkable, but its presence shows that complex organic molecules can form naturally in space. Such molecules are created on dust grains and released into space by radiation or heat, offering clues about the chemistry that may lead to life. Sagittarius B2 also contains other intriguing compounds, making it one of the richest chemical treasure troves in our galaxy. Some stars are on collision courses with each other. Stars are not fixed in space. They move through the galaxy under the influence of gravity. In most cases, these paths never cross, but in dense star clusters or binary systems, close encounters can happen. Some stars are locked in orbits that will eventually bring them together, merging into a single, more massive star. These stellar collisions can create unusually bright stars known as blue stragglers, or trigger nova-like events as their outer layers interact. In rare cases, they may even collapse into black holes or neutron stars. Such collisions are relatively rare on human timescales, but inevitable over the galaxy's long history, reshaping star systems and creating new cosmic subalii. Wonders. The Sun will one day become a white dwarf. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and swell into a red giant, engulfing Mercury and Venus, and possibly Earth. After shedding its outer layers into a glowing planetary nebula, the remaining core will collapse into a white dwarf, an Earth-sized remnant composed mostly of carbon and oxygen. This dense object will slowly cool over trillions of years, fading into a black dwarf, cold and dark. White dwarfs are common endpoints for stars like our Sun, and studying them gives astronomers a glimpse of our solar system's far future. Supermassive black holes can control entire galaxies. Though confined to the centers of galaxies, supermassive black holes can influence regions hundreds of thousands of light-years away. When actively feeding, they release jets and winds that can heat surrounding gas, preventing it from collapsing into new stars. In other cases, they can compress gas clouds, triggering bursts of star formation. This process, known as feedback, shapes the growth and evolution of galaxies over billions of years. Without the regulating influence of their central black holes, many galaxies might look very different, either choked with newborn stars or depleted entirely of star-forming material. The vacuum of space can boil your blood. In the absence of atmospheric pressure, liquids boil at much lower temperatures. This means that in the vacuum of space, unprotected human skin and fluids would experience ebulism, where water in the blood and tissues stops to vaporize. It wouldn't be a dramatic explosion. Your skin is strong enough to keep your body intact, but swelling, dizziness, and loss of consciousness would occur within seconds due to lack of oxygen. Astronauts rely on pressurized suits to maintain normal conditions, preventing these dangerous effects. Space's vacuum is not inherently cold or hot. It simply doesn't conduct heat well, so you'd lose warmth through radiation rather than touch. While we'll never be exposed like this outside fiction or accident, the reality underscores how hostile the cosmos can be and how vital the thin shield of our atmosphere is to our survival. Some stars pulse like beating hearts. Certain stars expand and contract rhythmically, growing brighter and dimmer in a steady pattern. Known as pulsating variable stars, these changes are caused by cycles of heating and cooling in the star's outer layers. Cepheid variables, for example, are so regular that astronomers use them as standard candles to measure distances across the universe. The periods of their pulses correspond directly to their intrinsic brightness, making them invaluable cosmic yardsticks. Other types, like Ara Lyrae stars, pulsate more quickly, often in just hours. Watching their light curves is like tracking a heartbeat, revealing not only their size and structure, but also clues about the history and age of the galaxies they inhabit. Some stars burn so hot they could vaporize you instantly. The hottest stars in the universe burn with temperatures exceeding 50,000 degrees Celsius at their surfaces and millions of degrees in their cores. They shine in a searing blue-white light, pouring out intense ultraviolet radiation that would strip away an atmosphere in moments. If Earth orbited one of these stellar furnaces, our oceans would boil away almost instantly. Such stars live fast and die young, burning through their fuel in just a few million years, a blink of an eye in cosmic terms. Their ferocity shapes galaxies, triggering the birth of new stars and carving vast bubbles in the interstellar medium. Yet from our safe distance, they are simply brilliant points in the night sky, their violence softened by the trillions of kilometers between us. Looking at them is to see both beauty and destruction in a single glance, the dual nature of the cosmos itself. There may be hidden oceans larger than Earth's beneath icy moons. Beneath the frozen crusts of moons like Europa, Enceladus, and Ganymede, scientists believe there may be vast oceans, some holding more water than all of Earth's seas combined. These alien oceans are kept liquid by tidal heating, where the moon's interior flexes under the gravitational pull of its planet, generating warmth. In darkness far from any sunlight, life might still thrive, drawing energy from hydrothermal vents on the ocean floor. Plumes of water vapor have even been detected erupting from Europa and Enceladus, hinting that their oceans might one day be sampled without drilling through kilometers of ice. These worlds are tantalizing because they suggest life could exist in places we once thought impossible. When we look up at Jupiter or Saturn, we're not just seeing distant planets. We may be looking at entire ecosystems hidden in the cold, waiting for the first premiere. Human-built probe to dive beneath their shells. There are moons covered in ice geysers. Saturn's moon Enceladus and Neptune's moon Triton both exhibit plumes of material erupting from beneath their icy crusts. On Enceladus, these geysers spray water vapor, ice particles, and organic molecules hundreds of kilometers into space, feeding Saturn's faint E-ring. Beneath the surface lies a global ocean kept liquid by tidal heating from Saturn's gravity. On Triton, nitrogen geysers vent material high into its thin atmosphere, driven by seasonal warming of its frozen surface. These icy plumes are more than spectacular sights. They offer a way to sample hidden oceans without drilling, and they hint that even distant frozen worlds can be active and possibly habitable beneath their shells. Space has no true up or down. In the microgravity of space, directions like up and down lose their meaning. Astronauts aboard the International Space Station can work in any orientation, flipping upside down without feeling inverted. Instead of gravity determining direction, astronauts orient themselves using the structure of the spacecraft, often choosing a floor and ceiling for convenience. In deep space, the concept becomes even more abstract. There is no universal reference for up or down, only relative positions between objects. This lack of fixed orientation is one reason space navigation relies on star maps, gyroscopes, and sensors, rather than intuition. The idea can be disorienting, but it's a reminder that our sense of direction is shaped entirely by life on Earth. A black hole's gravity can slow time to a crawl. Near the event horizon of a black hole, gravity is so strong that it warps space-time dramatically. To a distant observer, a clock near the horizon appears to tick more and more slowly, approaching a complete standstill as it reaches the edge. This is gravitational time dilation at its extreme. From the perspective of the person falling in, time passes normally, but the outside universe appears to speed up. In theory, one could witness millions of years of cosmic evolution in moments before crossing the horizon. This strange reality has been confirmed in less extreme cases by experiments on Earth and satellites in orbit, proving that time truly is flexible in the presence of intense gravity. There are rivers of stars in the Milky Way. Our galaxy is crisscrossed by vast stellar streams, elongated trails of stars that were once smaller galaxies or star clusters pulled apart by the Milky Way's gravity. These rivers can stretch for tens of thousands of light years, wrapping around the galaxy in graceful arcs. Studying them reveals clues about the Milky Way's past mergers and the distribution of dark matter shaping its gravitational field. The Sagittarius stream, for example, is the remnant of a dwarf galaxy currently being absorbed. These rivers are cosmic fossils, preserving the memory of events that unfolded over billions of years. Planets can orbit in opposite directions around the same star. In some rare multi-planet systems, one planet orbits in the same direction as the star's rotation, while another moves in the opposite direction. This retrograde motion is often the result of gravitational disruptions, such as a close encounter with another planet or a passing star. These chaotic events can flip a planet's orbit, creating systems that defy our expectations of orderly formation. Such configurations challenge current models of planetary dynamics and hint at the violent histories that shape solar systems. Some galaxies are shaped like perfect rings. Ring galaxies form when a smaller galaxy passes through the center of a larger one, triggering waves of star formation that spread outward in a circular pattern. The result is a glowing ring of young, blue stars surrounding a relatively empty core. Some rings are nearly flawless, looking like cosmic ripples frozen in time. The Cartwheel Galaxy is one of the most famous examples, its structure a product of a galactic collision millions of years ago. These unusual shapes are fleeting on cosmic timescales, lasting only until the stars disperse and the galaxy settles into a more typical form. There are stars that change color as they age. A star's color depends on its surface temperature, which changes over its lifetime. Young, massive stars burn hot and blue, while smaller, cooler stars glow red. As stars exhaust their fuel, they can swell into red giants, then shed their outer layers to reveal hot, blue-white cores. Some even pass through multiple color phases in relatively short periods. Observing a star's color and brightness gives astronomers insight into its mass, age, and chemical composition. In a way, a star's hue is a visible signature of its life story. A neutron star's magnetic field can shred atoms. Magnetars, a rare type of neutron star, have magnetic fields trillions of times stronger than Earth's. Such intense magnetism can distort the shapes of atoms, stretching them into long, thin structures and disrupting normal chemical bonds. These fields can also trigger massive starquakes on the magnetar's surface, releasing bursts of gamma rays detectable across the galaxy. The power of a magnetar's field is difficult to comprehend. If one were as close as the Moon, it could erase the data on every magnetic stripe and hard drive on Earth. They are among the most extreme and dangerous objects in the universe. The sun's light takes 8 minutes to reach Earth. The photons that leave the sun's surface travel at the speed of light, about 300,000 kilometers per second, reaching Earth in roughly 8 minutes and 20 seconds. But their journey actually begins much earlier, deep in the sun's core, where nuclear fusion produces energy. There, photons bounce from particle to particle in a dense plasma, taking thousands, even millions of years to reach the surface. Only then do they stream freely into space. This delay means the sunlight that warms your face today began its journey long before humans existed. The 8-minute travel time also means we see the sun as it was in the recent past, not exactly as it is now. In cosmic terms, this is nearly instantaneous, but it's still a reminder that even nearby light carries a whisper of history with it. Some planets orbit so close to their stars, they glow red hot. Exoplanets, known as hot Jupiters, orbit their stars at blistering proximity, sometimes closer than Mercury is to our Sun. Their atmospheres can reach temperatures of over 2,000 degrees Celsius, hot enough to vaporize metals. Some are tidally locked, with one side in perpetual daylight and the other in endless night, creating extreme temperature differences. On the day side, the heat can be so intense that clouds of vaporized rock or metal form. These worlds likely migrated inward after forming farther out, pulled closer by gravitational interactions. Observing them gives astronomers clues about how planetary systems evolve, and it challenges our understanding of what kinds of planets can survive in such hostile conditions. There are places in space where gravity cancels out. In multi-body systems like the Earth and Moon or Earth and Sun, there are points where the gravitational pulls of the two objects balance perfectly. Known as Lagrange points, these regions allow a spacecraft to remain in a stable position relative to both bodies with minimal fuel use. Some Lagrange points are home to swarms of natural objects, like the Trojan asteroids that shared Jupiter's orbit. Others are prime spots for space observatories, such as the James Webb Space Telescope at Sun-Earth L2, where it has a clear, stable view of deep space. These balancing points are like the calm eddies in a vast gravitational ocean, where the push and pull of massive bodies cancel out. The universe was once smaller than an atom. According to the Big Bang theory, the universe began as an incredibly hot, dense state, smaller than a single atom, about 8 billion years ago. In a fraction of a second, it underwent rapid inflation, expanding faster than the speed of light. Space itself stretched, carrying matter and energy outward in all directions. Over time, the universe cooled, allowing particles to form, then atoms, then stars and galaxies. Though we often imagine the Big Bang as an explosion in space, it was actually the expansion of space itself, everywhere at once. The idea that everything we see today, billions of galaxies, once fit into a space smaller than a grain of dust, is one of the most mind-bending concepts in science. Stars can swap material with their neighbors. In binary star systems, the two stars can orbit so closely, but one's outer layers spill over onto the other. This process, called mass transfer, can dramatically alter both stars' evolution. A star losing mass may shrink or even be stripped down to its core, while its companion grows more massive and luminous. In extreme cases, this interaction can trigger nova, sudden outbursts of brightness caused by accumulated material igniting on the surface of a white dwarf. These exchanges show that stars are not always solitary, stable objects. They can have relationships as dynamic and transformative as anything on Earth. Some galaxies are made almost entirely of dark matter. Astronomers have discovered galaxies whose visible stars and gas make up only a tiny fraction of their total mass. The rest appears to be dark matter, the invisible substance that exerts gravity but doesn't emit light. These dark galaxies are faint and difficult to detect, often revealed only by the way their gravity bends light from background objects or influences nearby galaxies. Studying them could reveal clues about how dark matter interacts with normal matter and why some galaxies fail to form many stars. They are ghostly reminders that most of the universe's mass is hidden from direct view. You can see the International Space Station with the naked eye. The International Space Station, orbiting about 400 kilometers above Earth, is the largest human-made object in space. When sunlight catches its solar panels just right, it appears as a bright, fast-moving point crossing the night sky. No telescope is needed, just timing. The station completes an orbit roughly every 90 minutes, traveling at over 27,000 kilometers per hour. From inside, astronauts see 16 sunrises and sunsets each day. Its visibility from Earth makes it a rare and inspiring example of space exploration you can witness with your own eyes. A moving star that's home to humans as it circles our planet. Black holes can merge into even larger black holes. When two black holes spiral toward each other, they lose energy in the form of gravitational waves, ripples in space-time predicted by Einstein and First DE, detected in 2015. As they draw closer, their orbits speed up until they merge in a fraction of a second, forming a single, more massive black hole. The collision releases an enormous amount of energy, not as light, but as gravitational waves that travel across the cosmos. These events allow astronomers to study black holes directly, providing insights into their masses, spins, and how often they form. Mergers are among the most powerful events in the universe, reshaping space-time itself. There are giant clouds of gas, larger than galaxies. In deep space, astronomers have observed enormous clouds of hydrogen gas stretching over 1 million light-years, bigger than entire galaxies. These colossal structures can serve as the raw material for future generations of stars and planets, or as the leftover debris from galactic collisions. Some are illuminated by nearby quasars, making them visible across billions of light years, while others remain dark and hidden. Their sheer scale is hard to imagine. A single one could envelop the Milky Way and still extend far beyond. The speed of light is the ultimate cosmic speed limit. In the vacuum of space, nothing can travel faster than light, about 1.08 billion kilometers per hour. This limit is built into the laws of physics, affecting everything from the way we communicate across space to how galaxies evolve. Even gravitational waves travel at this same speed. For spacecraft, this means interstellar journeys will always require significant time. Even the nearest star beyond the Sun, Proxima Centauri, is over 4 years away at light speed. The speed of light is not just a number, it's a fundamental part of the structure of space-time, shaping what is possible in our universe. Some planets have rings more magnificent than Saturn's. Saturn's rings are dazzling, but they're not the largest or most complex in the universe. Astronomers have found exoplanets with ring systems hundreds of times larger, so vast they would dominate the night sky if seen from a nearby moon. One such world, J1407b, appears to have over 30 separate rings stretching millions of kilometers in diameter. These rings may be made of ice, dust and rock, and could one day form moons as material clumps together. The sheer scale of these structures challenges our sense of planetary beauty and makes Saturn's rings, magnificent as they are, seem modest by comparison. The Milky Way is moving through space at incredible speed. Our galaxy is not stationary. It's hurtling through the universe at about 2 million kilometers per hour, drawn toward a mysterious region known as the Great Teen, a tractor. This movement is the result of gravitational pulls from nearby galaxy clusters and the overall cosmic web. We don't feel this speed because everything around us, from the Sun to Earth's atmosphere, shares the same motion. Yet it means the night sky is never fixed. Over millions of years, the positions of constellations change, and our place in the universe is constantly shifting. There are planets with 2 or more suns. In some star systems, planets orbit not one sun, but 2 or more, creating skies with double or triple sunrises and sunsets. These worlds are called circumbinary planets if they orbit both stars together, or multi-star planets if they move within a more complex gravitational dance. The varying positions of the suns could create extreme climates, with fluctuating heat and light patterns unlike anything on Earth. Scenes reminiscent of science fiction worlds like Tatooine are real, and studying them expands our understanding of how planetary systems form and survive in diverse environments. The universe might contain an infinite number of parallel realities. One interpretation of cosmic inflation suggests that our observable universe is just one bubble in an endless multiverse. If space truly extends infinitely, then every possible arrangement of matter could occur somewhere, including other universes where stars, galaxies, and even versions of ourselves exist with slight or dramatic differences. This idea is speculative, but it's consistent with certain mathematical models. While we have no way to directly observe these other realities, the concept stretches our imaginations to the furthest edge of possibility, blurring the line between physics and philosophy. Some stars die in collapses so violent they twist space-time. When a massive star collapses into a neutron star or black hole, the process can send powerful ripples through space-time known as gravitational waves. If the collapse is asymmetric, uneven in its distribution of mass, it can twist and distort space in ways we can detect from Earth. These events are incredibly rare to catch in real time, but they allow astronomers to study the physics of extreme matter and the behavior of gravity under the most intense conditions. Each detection adds to our understanding of how stars live, die, and leave their mark on the universe. There are asteroids with their own mini-moons. Some asteroids are accompanied by tiny companion bodies, small rocks captured by the asteroid's gravity. These moonlets can orbit for millions of years or be lost after a close planetary encounter. The binary asteroid Didymos and its moon Dimorphos became famous in 2022 when NASA DART spacecraft intentionally collided with Ka. Dimorphos to test asteroid deflection methods. Such systems reveal that even small bodies can have complex gravitational relationships, and studying them can help protect Earth from potential future impacts. The Big Bang created more than just matter. When the universe began, it didn't just produce matter, it also created antimatter, light, and the seeds of all fundamental forces. For reasons not fully understood, matter came to slightly outweigh antimatter, allowing a material universe to exist. The Big Bang also left behind a faint afterglow, the cosmic microwave background, which still fills space today. Within fractions of a second, the laws of physics as we know them emerged, setting the stage for everything from the formation of atoms to the birth of galaxies. The night sky contains light from long-dead stars. Many of the stars you see have already ended their lives, especially those far away. Their light began traveling toward us long before they burned out, meaning we see them as they were, not as they are now. In some cases, the light is thousands of years old for distant galaxies. It's billions of years old. Looking at the night sky is, in a very real sense, looking into the past, a cosmic history book written in light, where each point tells a story from a different chapter. The universe is life. Every atom in your body was forged in a star. The hydrogen in your body formed in the first minutes after the Big Bang, but all heavier elements, carbon, oxygen, calcium, iron, were forged inside stars through nuclear fusion. When those stars died, they scattered their enriched material into space, where it eventually formed new stars, planets, and life. This means you are literally made of star stuff, your atoms recycled from ancient suns that lived and died long before Earth existed. It's a connection that links us to the cosmos in the most literal way possible. Somewhere in the universe, a planet like Earth may be waiting. With billions of galaxies, each containing billions of stars, it's statistically likely that many planets with conditions similar to Earth exist. Some may have oceans, continents, and atmospheres capable of supporting life. While we have yet to find a true Earth twin, telescopes are constantly discovering potentially habitable worlds in distant star systems. One day, we may detect signs of life, or even visit such a planet. Until then, the idea that somewhere, far beyond our reach, another world might be home to life offers both mystery and hope. Polaris has not always been the guiding North Star. For travelers in the Northern Hemisphere, Polaris has long been a faithful companion. Sitting almost exactly above Earth's North Pole, it marks true north in the sky. But Earth itself slowly wobbles on its axis in a cycle called precession. Over thousands of years, this gentle motion shifts the position of the stars relative to our poles. Polaris has not always been our North Star, and it will not remain so forever. In the time of the ancient Egyptians, for example, the star Thuban in the constellation Draco held that title. In about 12,000 years, the brilliant Vega will take its turn. This slow celestial dance means that humanity's guiding star changes with the ages. Polaris feels eternal when we look at it tonight, steady and bright, yet even it is just one marker in a long and shifting cycle written across the heavens. Ancient travelers navigated oceans and deserts by patterns in the night sky. Long before compasses and satellites, The sky was humanity's first map. Sailors crossing the vast Pacific memorized the rise and fall of constellations, using them as guides over featureless waves. Nomadic peoples in deserts did the same, orienting themselves by the position of stars. Polaris, steady above the northern horizon, was especially valuable for finding direction. In the southern hemisphere, navigators used the Southern Cross. Entire systems of knowledge grew around these observations. Polynesian wayfinders, for example, carried the positions of hundreds of stars in memory, passing them down through generations. These maps were more than practical. They were cultural treasures, woven into stories and songs so they could never be forgotten. When you look up at the night sky, you're seeing the same compass points that once guided caravans, armies, and explorers, carrying them across oceans and continents. Long before any mechanical device existed, the Milky Way appears as a hazy band because we are looking through its disk. On a truly dark night, far from city lights, a misty river of light stretches across the sky. This is the Milky Way, and its glow comes from the combined light of billions of distant stars. The reason it forms a band is that we are inside the galaxy, looking along its flat, disk-like structure. Imagine standing inside a vast spinning wheel and gazing through its rim. That's what we see from Earth. The concentration of stars, gas, and dust in the disk blurs together into a luminous haze. In ancient times, cultures around the world gave it names: a celestial river, a road of spirits, the backbone of the night. Today, we know it as the plane of our galaxy, and every glowing wisp in that band is another sun, another solar system, another possible world. The Milky Way is both home and horizon. Our galaxy contains hundreds of billions of unseen suns. The stars you see overhead are only the tiniest fraction of what actually fills our galaxy. Astronomers estimate that the Milky Way contains somewhere between 200 and 400 billion stars. Most of them are too faint or too distant to be seen without telescopes. Many are red dwarfs, small and dim compared to our sun, but incredibly numerous. Others are hidden behind clouds of gas and dust, their light only revealed through infrared observations. There may also be countless wandering worlds, planets not bound to any star, drifting unseen through the dark. When you look up at a night sky filled with a few thousand stars, it's humbling to realize that what you see is only a pinprick of the Milky Way's true population. Our galaxy is so full of suns that even in a lifetime, no eye could ever count them all. Shooting stars are not stars at all, but grains of cosmic dust burning in the night sky. The streak of a shooting star feels magical, sudden, bright, and gone in an instant. But despite the name, these flashes aren't stars. They're usually fragments no bigger than a pebble, often smaller than a grain of sand. As they plunge into Earth's atmosphere at tens of thousands of miles per hour, the air in front of them compresses and heats up, causing them to glow brilliantly before disintegrating. Most never reach the ground. What we see is their final blaze, a farewell spark in the sky. Some arrive from comets, their trails leaving behind streams of dust that Earth crosses each year. Others are simply random debris wandering the solar system. They may be tiny, but their brilliance comes from speed and energy, not size. In every streak, the universe leaves us a fleeting reminder that space is never still. From the darkest places on Earth, thousands more stars appear in the night sky. Most of us live under skies dimmed by artificial light. Street lamps, cities, and glowing highways all wash out the stars. But in the rare places untouched by this glow, remote deserts, mountaintops, isolated islands, the view changes entirely. Instead of a few dozen bright points, the heavens become densely crowded, alive with thousands upon thousands of stars. The Milky Way swells into a broad, glittering arc, bright enough to cast shadows. In these skies, you can see faint smudges that are actually distant galaxies, glowing clusters of stars, and sometimes even the delicate color of nebulae. Astronomers call such places dark sky sanctuaries, and they are increasingly rare. To stand beneath one is to see what every human before modern lighting once saw: a universe alive with stars, humbling in its immensity and breathtaking in its clarity. Some places never glimpse the Milky Way because of light pollution. For many people around the world, the Milky Way is no longer a part of daily life. In heavily populated regions, artificial light has erased it from view. Entire generations grow up without ever seeing the river of stars that was once central to human culture. Light pollution doesn't just dim the stars, it drowns them completely, leaving only the brightest planets and a few scattered points. Cities that glow all night send light upward, scattering in the atmosphere and creating a permanent haze. As a result, in some places, the Milky Way is effectively gone. Yet the stars are still there, waiting behind the veil. Astronomers and conservationists are working to preserve dark skies, not just for science, but for our sense of wonder. To see the Milky Way with your own eyes is to reconnect with a view that belongs to all of humanity. Constellations slowly change shape over thousands of years. Constellations feel timeless, their patterns passed down through generations as if frozen in the sky. But in truth, the stars that make up Orion, Ursa Major or Cassiopeia are not fixed points. Each star is moving through the galaxy with its own velocity, its own trajectory around the galactic center. Because they are so far away, their motions are imperceptible to us within a single lifetime. Yet over tens of thousands of years, the familiar outlines we know begin to warp and dissolve. Orion's belt will eventually lose its straight line. The Big Dipper will no longer look like a dipper at all. Astronomers can project forward in time to see how the sky will appear in the distant future, and the constellations are nearly unrecognizable. The night sky is not a permanent picture, but a slow, shifting dance, one that reveals how dynamic our galaxy truly is. The southern hemisphere reveals constellations northern eyes never see. For anyone raised under northern skies, traveling south of the equator can feel like stepping into a new world after sunset. Familiar constellations like the Big Dipper vanish completely, sinking below the horizon. In their place, new shapes emerge. The Southern Cross, bright and compact, long used by navigators. Nearby, the two Magellanic Clouds, small galaxies orbiting our own, appear as ghostly smudges visible to the naked eye. Entire patterns of stars form constellations unfamiliar to northern stargazers. The emu in the sky, recognized by indigenous Australians, or the majestic Centaurus striding across the heavens. For those in the southern hemisphere, these constellations are as natural and recognizable as Orion is to the north. Together, they remind us that the sky is shared, but perspective changes everything. Half of Earth sees a view, the other half never does, and the universe above is always larger than what we know. The Andromeda Galaxy is faintly visible in the night sky without a telescope. Most galaxies lie far beyond the reach of human eyesight, but one is close enough to reveal itself unaided: Andromeda. Under dark skies, it appears as a dim, misty blur, more like a cloud than a structure of stars. Yet that hazy smudge is staggering in scale. Andromeda is a spiral galaxy like our own, containing perhaps 1 trillion stars, stretching more than 200,000 light-years across. Its light has traveled over 2 million years to reach Earth. Ancient observers saw it too, long before telescopes existed, and recorded it as a faint patch among the stars. To realize that you can step outside, look up, and actually see another galaxy with your eyes alone is one of astronomy's most humbling experiences. That faint blur is not just a single object, it's an entire island universe, with suns, planets, and mysteries of its own. The light from Andromeda began its journey more than 2 million years ago. When you glimpse the faint glow of the Andromeda galaxy, you are looking into the deep past. Its light has traveled for more than 2 million years across intergalactic space. That means the glow reaching your eyes tonight left Andromeda long before humans existed. When that light began its journey, Earth was home to early ancestors who had not yet developed the tools or language we take for granted. Entire species have risen and fallen in the time it has taken for that faint gleam to cross the void. And while we see Andromeda as it was, the galaxy itself has moved, evolved, and continued to form new stars. In another 4 billion years, Andromeda and the Milky Way will collide and merge into a single vast galaxy. For now, the light from its ancient stars serves as a living time capsule, carrying history across unimaginable distance. The night sky once contained stars that no longer exist today. It is easy to think of the stars as permanent, eternal lights above us. Yet stars are born, live, and die, often in violent ways. Because starlight takes time to reach Earth, some of the stars recorded in ancient times have since perished. Astronomers studying old star charts occasionally discover descriptions of bright objects that no longer shine in today's sky. These may have been massive stars that exhausted their fuel and exploded as supernova, leaving only faint remnants behind. Others may have collapsed into neutron stars or black holes, invisible without specialized instruments. The sky is constantly renewing itself, with new stars being born, even as old ones fade away. What we see above us is not a fixed tapestry, but a changing story, a record of both what is and what once was. Every glittering point is temporary, even if its life far outlasts ours. A star's color reveals its temperature, from cool red to blazing blue. Not all stars shine the same. Some glow with a soft orange red, others with a pale blue-white brilliance. This difference is more than cosmetic, it reveals their temperatures. Red stars, often called red dwarfs or red giants depending on their size, are cooler, radiating at a few thousand degrees. Blue stars, by contrast, blaze at tens of thousands of degrees, their surfaces searing hot and their lifespan short. Our own sun, with its steady yellow-white light, sits in between, a medium-temperature star. To astronomers, these colors are like fingerprints. By splitting starlight into its spectrum, they can measure temperature, composition, and even motion. To the human eye, the colors of stars are subtle, often masked by the atmosphere, but with practice you can spot them. Each color tells a story about a star's nature, its energy, and its place in the grand life cycle of the cosmos. Stars appear to twinkle in the night sky because of Earth's atmosphere. The twinkle of a star can feel enchanting, like nature's own sparkle. But what you're really seeing is turbulence in Earth's atmosphere. As starlight travels through the layers of air above us, it bends and shifts slightly with changing densities and temperatures. The effect makes the light appear to flicker or jump, even though the star itself is shining steadily. Planets, by contrast, usually appear more stable because they are closer and present a larger disk of light, less affected by the shifting air. Astronomers call this effect atmospheric scintillation, and it's the reason telescopes on Earth can never achieve perfect clarity. To overcome it, observatories are built on mountaintops where the air is thinner and steadier, or even launched into orbit to bypass the atmosphere entirely. What looks like a magical shimmer is really a reminder of the thin, restless blanket of air we live beneath. In space, those same stars shine with steady clarity. Astronauts aboard the International Space Station or spacecraft beyond Earth's atmosphere see stars very differently from us. Without the constant interference of air currents, starlight arrives in perfect beams, steady and unwavering. The difference is striking. Instead of twinkling points, stars shine with sharp precision, each one a fixed jewel against the blackness. This clarity is one reason telescopes like Hubble produce images of breathtaking detail freed from Earth's atmosphere. They can capture the universe as it truly, quote, looks. The steady glow in space also reveals the subtler colors of stars more vividly than what we usually see from the ground. While twinkling can feel romantic or nostalgic, the view from orbit shows the sky in its raw form, stable, radiant, and clear. It's a reminder that our atmosphere both protects and distorts, sheltering us while gently disguising the true face of the cosmos. Some stars grow hot enough to fuse helium and carbon deep inside. The energy of a star comes from nuclear fusion, the process of pressing smaller atoms into larger ones. For most of its life, a star fuses hydrogen into helium. But massive stars don't stop there. As their cores grow hotter and denser, they begin fusing helium into carbon, oxygen, and even heavier elements. This cycle builds the building blocks of life itself. Every atom of carbon in your body, every molecule of oxygen you breathe, was created inside a star that once blazed and burned. Eventually, when such stars reach their limits, they collapse and explode, scattering these elements into space to seed new stars and planets. The cosmos is a kind of recycling system, with each generation of stars creating the raw materials for the next. When we look up at a brilliant blue giant or a fading red supergiant, we are seeing furnaces that forge the future. Sirius blazes as the brightest star in the night sky. Sirius, known as the dog star, dominates the night with its brilliance. Found in the constellation Canis Major, it shines nearly twice as bright as the next brightest star, Canopus. Its name comes from the Greek word for glowing, and it has lived up to that reputation across cultures and centuries. Part of its brightness comes from proximity. Sirius lies only about 9 light-years away, making it one of our nearest stellar neighbors. But it is also intrinsically luminous, shining more than 20 times brighter than the sun. Ancient Egyptians watched for its rising, linking it to the flooding of the Nile. Today, it is still one of the most reliable markers in the winter sky, easy to spot, even from cities. Sirius is not alone either. It has a faint white dwarf companion, the dense core of a long-dead star, orbiting it every 50 years. Sirius has inspired myths across nearly every culture. From ancient Mesopotamia to the Pacific Islands, Sirius has been more than just a bright point of light. It has been a symbol, an omen, and a guide. The Egyptians associated its yearly rising with the life-giving floods of the Nile, weaving it into their calendar. The Greeks linked it with heat and madness, giving us the phrase, dog days of summer. In Polynesian navigation traditions, it was an essential star for long voyages. For indigenous peoples of North America, it appeared in legends and seasonal markers. Across the world, cultures recognized its brilliance and gave it significance, tying it to cycles of agriculture, migration, and storytelling. That Sirius can be so many things to so many people speaks to its power. It is just a star, a ball of burning hydrogen and helium, yet its place in human imagination has made it one of the sky's most enduring symbols. The Pleiades cluster sparkles like a tiny swarm of fireflies in the night sky. The Pleiades, sometimes called the Seven Sisters, is one of the most beloved sights overhead. This small cluster of stars lies in Taurus and is visible even in areas with some light pollution. Through the naked eye, most people see 6 or 7 stars, though in reality, the cluster contains hundreds. With binoculars, the view transforms into a glittering swarm, each star a youthful blue sun burning brightly. Ancient cultures around the world recognized the Pleiades, often weaving them into myths of family or pursuit. The Japanese name for the cluster is Subaru, now immortalized in the car company's logo. The Pleiades are relatively close by, only about 400 light-years away, and still wrapped in faint dust clouds that reflect their light. They are a reminder that not all beauty in the night sky is distant or faint. Some wonders are close enough to feel intimate. The Orion Nebula glows faintly within Orion's sword. If you trace the constellation Orion, beneath his famous belt lies a short line of stars known as the Sword. In its center is a fuzzy patch of light visible to the naked eye on dark nights. This is the Orion Nebula, one of the brightest and closest stellar nurseries in the galaxy. Through binoculars or a small telescope, it resolves into swirls of glowing gas lit by newborn stars. Astronomers estimate that thousands of stars are forming there, shaping the clouds with their energy. To ancient stargazers, it was simply a mysterious blur. But today, we know it as a place where the story of stars begins. The Orion Nebula is only about 1,300 light-years away, close enough that it has become one of the most studied regions in the sky. Every glance at it is a look at creation in progress. Some nebulae shine because their gases are energized by nearby stars. Nebulae are the great canvases of the cosmos, clouds of gas and dust that stretch for light-years. Some glow brightly because they are energized by powerful radiation from nearby stars. Ultraviolet light streams out from these massive suns, striking the atoms in the nebula and causing them to emit colorful light of their own. These are called emission nebulae, and they paint the sky with reds, greens, and blues, depending on the elements within them. The Orion Nebula is one famous example, glowing with pinkish light from hydrogen. Without the stars that energize them, these clouds would be dark and invisible, blending into the void. Instead, they shine as luminous beacons, signaling regions where stars are born. What looks delicate and soft to us is in fact a cauldron of activity, shaped by energy and gravity into some of the most beautiful sights in astronomy. Others glow only by reflecting starlight like cosmic mirrors. Not all nebulae create their own light. Some simply reflect the brilliance of nearby stars. These are called reflection nebulae, and they shine in a softer, gentler way. Dust grains within them scatter starlight, often giving them a distinctive blue hue, much like Earth's sky appears blue because of scattered sunlight. One famous example is the nebulosity surrounding the Pleiades cluster, where bright blue stars illuminate thick clouds of dust. These nebulae are like cosmic mirrors, catching and redirecting light across the void. They often appear near young star clusters, where plenty of hot, bright stars are available to shine on them. Though less dramatic than glowing emission nebulae, reflection nebulae are delicate reminders that the universe is full of subtlety as well as grandeur. They are the whisper to the other nebulae's shout, faint but exquisite in their quiet shimmer. Many stars are not single but pairs orbiting each other. When you look up at the sky, it's easy to imagine each star as a solitary sun. But in reality, many are not alone. Binary systems, pairs of stars orbiting a common center of mass, are incredibly common. Some are nearly equal in size, dancing around each other in graceful balance. Others are mismatched, with a massive star tugging a smaller companion in wide loops. To the eye, many binaries appear as a single point of light, their closeness masking their dual nature. With telescopes, astronomers can separate them or detect their influence through gravitational pulls. These systems are not rare curiosities, but may actually be the norm. Our Sun, in its solitude, could be the exception rather than the rule. Binary stars remind us that even in the vast loneliness of space, companionship is common, and the universe is full of unlikely partnerships. Binary systems are more common than solitary suns like ours. It might seem natural to assume that most stars resemble the Sun, solitary, with a family of planets in orbit. But surveys suggest the opposite. Binary and multiple star systems may outnumber single stars. In some cases, stars form together from the same cloud, locked into gravitational bonds that last for billions of years. In others, stars capture each other later through close encounters. Binary systems can be peaceful, or they can be tumultuous. A massive star can strip material from its smaller partner, creating spectacular disks of gas. Or one can collapse into a white dwarf, neutron star, or black hole, reshaping the relationship entirely. For planetary systems, life under two suns would be profoundly different. Imagine a sky with double sunsets, or a world where two dawns rise each morning. Solitary stars like ours are special, but perhaps not the most common story in the galaxy. There are even triple and quadruple star systems bound together. If two stars orbiting each other seems complex, nature goes even further. Some systems host 3 or even 4 stars, bound together in intricate gravitational relationships. In a triple system, 2 stars may orbit closely while a third circles farther out, like a cosmic dance with nested steps. In quadruple systems, the arrangements can become even more elaborate, with pairs orbiting pairs. To us, they may appear as a single point of light, but telescopes reveal the truth, a miniature galaxy in its own right. For any planets within these systems, the skies would be extraordinary. Sunrises and sunsets could involve multiple suns, casting overlapping shadows and floods of shifting light. These systems are reminders that the cosmos is inventive, crafting arrangements far beyond the familiar. While our single sun feels normal to us, elsewhere, entire solar systems live under the glow of several suns at once. Cepheid variable stars pulse rhythmically, like cosmic lighthouses in the night sky. Some stars do not shine with steady brightness. Cepheid variables expand and contract in a regular rhythm, causing their light to brighten and fade in cycles that can last days or weeks. To the naked eye, they appear to flicker on cosmic timescales, but to astronomers, they are invaluable tools. The period of their pulsation is directly related to their intrinsic brightness. By measuring how quickly they pulse and comparing it to how bright they appear, astronomers can calculate their distance. This discovery, made in the early 20th century, unlocked the ability to measure the scale of the universe. Cepheids became mile markers, showing us the vast distances to nearby galaxies. What began as the curiosity of a star that seemed to breathe in and out became one of the most important tools in cosmology. Each pulsing cepheid is both a marvel and a measuring stick for the cosmos. These pulsations once revealed the true scale of the universe. For centuries, the size of the universe was a mystery. Were the stars nearby pinpricks, or unimaginably distant? Cepheidae variable stars provided the answer. In the 1920s, astronomer Edwin Hubble studied Cepheidae in the Andromeda galaxy. By measuring their pulsation periods, he determined their intrinsic brightness, and from that, their distance. The result was staggering. Andromeda was far beyond the limits of the Milky Way. It was another galaxy altogether. The discovery expanded the universe overnight, transforming it from a single island of stars into a cosmos filled with countless galaxies. Cepheids were the key, simple rhythmic beacons that bridged the gulf between us and the wider universe. Today, even with advanced telescopes and satellites, they remain essential tools for measuring cosmic distances. Each pulse is a heartbeat of the cosmos, steady and reliable, reminding us how the simplest patterns can unlock the greatest truths. Some stars balloon into red supergiants hundreds of times larger than the Sun. Not all stars remain small and steady like our Sun. Some, when they near the end of their lives, swell into titanic red supergiants. These stars expand to such immense proportions that if one replaced the Sun, its surface could stretch beyond the orbit of Mars. Despite their size, their outer layers are thin, glowing with a deep red hue as the star struggles to sustain itself. Within, their cores fuse heavier elements in a frantic effort to maintain balance against gravity. These giants live fast and die young, their immense energy burning through fuel at astonishing rates. They are rare compared to smaller stars, but unforgettable in scale and brightness. Looking up at one is to glimpse a dying star in its final chapter, swollen and unstable, destined for collapse. Red supergiants remind us that even the grandest stars cannot escape time. Betelgeuse in Orion is nearing the end of its life. High on a winter night, the constellation Orion dominates the sky. At his shoulder burns Betelgeuse, a ruby-red star that has fascinated stargazers for centuries. Betelgeuse is a red supergiant, swollen to hundreds of times the size of our Sun. Astronomers know it is nearing the end of its life, having exhausted the hydrogen that once fueled it. Inside, it now fuses heavier elements, building toward an inevitable collapse. Betelgeuse's brightness varies dramatically, sometimes dimming so noticeably that it sparks speculation across the world. In 2019, a great fading led many to wonder if it was about to explode. Although it returned to its usual glow, the event reminded us of its fragile state. Betelgeuse is a star in its twilight, and its fate is sealed. Whether it endures for another 100,000 years or only a fraction of that, it will eventually die in spectacular fashion. Betelgeuse may one day explode as a supernova visible in the night sky, even in daylight. When Betelgeuse finally reaches the end, it will not fade quietly. It will explode as a supernova, a detonation so powerful it will outshine all other stars in the sky. For weeks or even months, the light from its death could be visible even during the day, brighter than the full moon. Such an event has happened before in history, recorded by ancient astronomers when nearby stars collapsed. Betelgeuse lies about 600 light-years away, close enough for us to witness its brilliance, but far enough to pose no danger to Earth. The explosion will leave behind a dense remnant, perhaps a neutron star, while its outer layers scatter across space, enriching the cosmos with elements like oxygen and iron. When it happens, humans everywhere will look upward, seeing the same brilliant beacon in the sky. A reminder that stars, too, live and die in extraordinary ways. Supernova can briefly outshine entire galaxies. The death of a massive star is among the most violent events in the universe. In a supernova, the collapsing core rebounds with such ferocity that the entire star is torn apart in a single instant. For a brief period, the explosion can release more energy than all the other stars in a galaxy combined. From Earth, such events may appear as sudden bright stars where none existed before. Some fade within weeks, others linger for months. Beyond their spectacle, supernovas serve as cosmic engines, scattering the elements forged in stellar hearts into surrounding space. Without them, the building blocks of planets and life would not exist. The brilliance of a supernova is fleeting, but its legacy endures forever. To imagine an entire galaxy overshadowed by the death of a single star is to glimpse both the power and the impermanence written into the fabric of the cosmos. The Crab Nebula is the remnant of an explosion recorded in the night sky by ancient astronomers. In the year 1054, observers in China and across the world recorded the sudden appearance of a dazzling new star. It shone brightly for weeks, visible even in daylight, before fading from view. Today, we know that event was a supernova, the death of a massive star. The remnant still lingers in the sky, known as the Crab Nebula. Through telescopes, it appears as a tangled web of glowing filaments, the expanding shell of gas and dust cast off by the explosion. At its center lies a pulsar, the collapsed, spinning core of the original star, still sending out pulses of radiation like a cosmic lighthouse. The Crab Nebula is a time capsule, a living bridge between ancient records and modern astronomy. When we see it, we are seeing both the memory of a star's death and the continuing life of its remnant. Pulsars spin with such precision they rival atomic clocks. Pulsars are among the strangest objects in the cosmos. They are the collapsed cores of massive stars, left behind after a supernova. Composed almost entirely of neutrons, they are unimaginably dense. A teaspoon of pulsar matter would weigh as much as a mountain. Many pulsars rotate at astonishing speeds, sending beams of radiation sweeping across the universe like the beams of a lighthouse. From Earth, these appear as regular pulses of light or radio waves, each one arriving with such reliability that astronomers can use them as cosmic clocks. Some pulsars spin dozens of times per second, while the fastest known rotate hundreds of times each second. Their stability rivals that of the best atomic clocks on Earth, allowing astronomers to use them for measuring cosmic distances and testing the laws of physics. These tiny, collapsed remnants remind us that time itself can be written in starlight. Magnetars wield magnetic fields trillions of times stronger than Earth's. Among the many exotic remnants of dead stars, magnetars stand apart. Like pulsars, they are neutron stars, but they possess magnetic fields so intense they defy comprehension. A magnetar's field is trillions of times stronger than Earth's, capable of distorting atomic structures themselves. These fields can twist and snap violently, producing bursts of high-energy radiation that ripple across space. Astronomers detect them as sudden flares, brief but powerful. Though small, only about 20 kilometers across, magnetars contain the mass of multiple suns. Their strength makes them dangerous even at great distances. A magnetar close to Earth could wreak havoc on our planet's magnetic field. Fortunately, none exist nearby. Instead, they remain distant curiosities, extreme laboratories where the rules of physics are pushed to their limits. Magnetars show us that the universe is not just vast, but capable of producing forces so extreme they border on the unimaginable. Black holes hide in the night sky, revealed only by their effects. A black hole is not an object we can see directly. Its gravity is so strong that not even light can escape, rendering it invisible against the backdrop of space. Yet their presence can be detected by what they do to their surroundings. Matter spiraling into a black hole heats up, glowing brightly in X-rays before vanishing. Stars caught in their pull may orbit unseen companions. betraying the black hole's mass. Even space itself curves inward around them, warping the paths of light. To the naked eye, black holes are invisible, but through telescopes and careful observation, astronomers have uncovered many scattered throughout the galaxy. Some are the remnants of massive stars, while others lurk at the hearts of galaxies. They are the unseen anchors of cosmic drama, reminding us that the most powerful forces in the universe often hide in silence and shadow. Some consume nearby stars and flare brightly as they feed. When a black hole orbits close to a companion star, it can draw matter from its neighbor. Gas from the star spirals inward, forming an accretion disk, a whirling ring heated to millions of degrees. This process produces powerful X-ray emissions, making the once invisible black hole one of the brightest objects in the sky at those wavelengths. To an observer, it looks like a flickering beacon, sometimes growing brighter, sometimes fading as the flow of matter changes. In extreme cases, black holes emit jets of material traveling near the speed of light, blasting across space for thousands of light years. Though the idea of a star being consumed sounds catastrophic, it is part of the cosmic cycle, redistributing matter and energy. These dramatic systems reveal that black holes are not simply voids of emptiness, but active players in shaping the dynamics of galaxies. The heart of our galaxy conceals a supermassive black hole. At the very center of the Milky Way lies an invisible giant, Sagittarius A*, a supermassive black hole with a mass millions of times greater than the Sun. Though it cannot be seen directly, its presence is revealed by the orbits of stars whipping around it at incredible speeds. In 2019, astronomers captured its shadow for the first time, using a network of radio telescopes spanning the globe. The image showed a glowing ring of light, matter heated to extremes as it spirals inward, surrounding a dark center where light itself cannot escape. Supermassive black holes like this one are thought to lurk at the cores of most galaxies, shaping their evolution through gravity and energy. That our own galaxy is anchored by such a force is both humbling and awe-inspiring. It is the silent heart of the Milky Way, unseen yet profoundly influential. Beyond our sight, the night sky holds countless galaxies. The stars above may feel abundant, but what we see is only the beginning. Beyond the Milky Way, countless galaxies populate the universe. Each contains billions, sometimes trillions of stars. With telescopes, faint smudges of light resolve into spirals, clusters, and ellipses, island universes scattered across the cosmos. The Hubble Space Telescope once stared at a seemingly empty patch of sky for days, revealing thousands of hidden galaxies in a space no larger than a grain of sand, held at arm's length. This discovery showed that wherever you look, the universe is overflowing with galaxies. To the naked eye, a mere few, like Andromeda or the Magellanic Clouds, can be seen. But with the right tools, the blackness between stars transforms into an ocean of light. The night sky is not just a canopy of stars. It is the edge of a vast universe of galaxies. Through telescopes, galaxies appear in spirals, ellipses, and chaotic forms. Galaxies are not all alike. Some form graceful spirals, with sweeping arms of stars curving outward from a bright core. Others are smooth and featureless ellipses, vast balls of ancient stars glowing faintly. Still others are irregular, their shapes distorted by collisions or bursts of star formation. Each type tells a story about its history. Spirals are active, full of young stars and gas. Ellipticals are older, quieter, often the result of mergers. Irregulars are the misfits, still settling into shape. Through telescopes, the diversity of galaxies is astonishing. Some shine brightly, Others appear as faint smudges barely visible. Yet every one is a universe of its own, containing stars, planets, and mysteries beyond counting. To see them is to realize how endlessly inventive the cosmos is, shaping order and chaos alike into luminous forms that drift through the darkness of space. Some galaxies collide and merge in slow-motion dances. Though the distances between stars within a galaxy are immense, galaxies themselves are not so isolated. They are bound by gravity into clusters and groups, and their paths often intersect. When galaxies collide, it is not an explosive crash, but a slow-motion dance lasting hundreds of millions of years. Their stars mostly pass by one another, but their gas and dust clouds collide, triggering bursts of new star formation. Gravity stretches their shapes into spirals, tails, and arcs. Over time, the galaxies merge, becoming one larger system. Our own Milky Way is destined for such a fate, eventually merging with the Andromeda Galaxy. Far in the future, the two will become a single massive elliptical galaxy. For now, we watch others in the distance, their cosmic ballets frozen in time, each collision a reminder that nothing in the universe is static, not even the galaxies themselves. The Magellanic Clouds are two satellite galaxies visible in southern night skies. From the southern hemisphere, two faint, cloud-like patches of light linger near the Milky Way. These are the large and small Magellanic Clouds, dwarf galaxies orbiting our own. To the naked eye, they appear as subtle smudges, but through telescopes they reveal themselves as bustling systems filled with stars, clusters, and nebulae. They are irregular in shape, distorted by their gravitational dance with the Milky Way. Within them lie stellar nurseries like the Tarantula Nebula, one of the most active star-forming regions known. For observers in the north, the Magellanic Clouds are invisible, forever hidden below the horizon. For those in the south, they are familiar companions, woven into cultural traditions for centuries. These galaxies are reminders that the Milky Way is not alone, but part of a larger family of galaxies, orbiting, merging, and shaping one another across cosmic SAS. Time. Star clusters are like glittering families bound by gravity. Not all stars live in isolation. Many are born together in groups called star clusters, bound by gravity. These clusters can range from small gatherings of a few hundred stars to massive groups containing thousands. Open clusters, like the Pleiades, are loose and youthful, their stars still close to their birthplace in interstellar clouds. Globular clusters, by contrast, are dense, spherical gatherings of ancient stars, tightly packed into dazzling spheres. To the eye, star clusters appear as sparkling knots, brighter than the stars around them. Through telescopes, they explode into fields of brilliance, each point of light a sun with its own story. Clusters are laboratories for astronomers, offering insights into stellar evolution and galactic history. To stand beneath a dark sky and glimpse one is to see a family of stars still holding together, bound by forces that have lasted for billions of years. Globular clusters can hold hundreds of thousands of suns. Globular clusters are among the most spectacular sights in astronomy. These spherical gatherings can contain hundreds of thousands, sometimes even millions of stars, packed into a region only a few dozen light-years across. In their centers, the density of stars is so great that they appear to blur together, like a swarm of fireflies. Most globular clusters orbit the outer regions of galaxies, including our Milky Way, which has more than 100 of them. They are ancient, often more than 10 billion years old, containing some of the oldest stars in existence. To the naked eye, they may look like faint, fuzzy patches, but telescopes reveal them as dazzling globes of light. Globular clusters are fossils of the early universe, survivors from the time when galaxies were first forming. Their beauty lies not only in their glittering appearance, but in their endurance across cosmic history. Some of these clusters are nearly as old as the universe itself. Globular clusters are time capsules, preserving the earliest stars ever formed. Many are nearly as old as the universe itself, dating back more than 12 billion years. These ancient stars contain very few heavy elements, reflecting a time before supernova had enriched the cosmos with the ingredients for planets and life. To study them is to look back into a nearly primordial universe, when stars were first igniting in the dark. The fact that these clusters still exist today, orbiting the edges of galaxies, shows their resilience. They have survived countless galactic mergers, collisions, and gravitational disturbances, yet remain intact. When you gaze at one through a telescope, you are not just seeing stars, you are witnessing relics from the dawn of time, glowing beacons that have endured almost as long as the universe itself. They are among the oldest living witnesses of creation. Meteor showers return every year as Earth crosses comet trails in the night sky. Several times a year, Earth passes through streams of debris left behind by comets. As we move through these trails, countless tiny particles enter our atmosphere and burn up, creating meteor showers. Unlike random shooting stars, meteor showers produce multiple streaks within a single night, often radiating from a particular point in the sky. The Perseids, Geminids, and Leonids are some of the most famous, each linked to a parent comet or asteroid. These showers are predictable, recurring on the same dates year after year as Earth revisits the same paths. For stargazers, they are one of the most rewarding events to witness, filling the sky with fleeting streaks of light. Though the meteors are often no larger than sand grains, their fiery trails remind us that Earth is constantly moving through a living solar system, intersecting with the Precursor, remnants of ancient wanderers. The Perseid meteor shower in August is among the most famous. Every August, the Perseid meteor shower graces the skies, producing some of the most reliable displays of shooting stars. Originating from the debris trail of Comet Swift-Tuttle, the Perseids are active for several weeks, but peak around mid-August. During this time, observers under dark skies may see dozens of meteors per hour, sometimes more during bursts. The Perseids are known for their bright, fast streaks, many leaving glowing trails that linger for moments after. They appear to radiate from the constellation Perseus, which gives them their name. For centuries, people have watched the Perseids, weaving them into folklore and marking them as a highlight of summer nights. Today, they remain a favorite for stargazers around the world, combining predictability with beauty. Each meteor is a tiny fragment of a comet, burning brightly as it falls, a yearly reminder of the connection between Earth and the wider cosmos. Ancient records describe brilliant showers streaking across the night sky. Meteor showers have not gone unnoticed by history. Ancient Chinese, Korean, and European texts describe sudden bursts of falling stars, sometimes numbering in the hundreds in a single night. These records often carried symbolic weight, interpreted as omens or portents. One famous Leonid shower in the 1830s produced thousands of meteors per hour, filling the sky with blazing streaks and sparking awe and fear alike. Witnesses thought the world might be ending. For astronomers, these historical accounts are more than curiosities. They help track the orbits of comets and the evolution of meteor streams. By comparing past records with modern observations, scientists can understand how debris trails spread and shift over centuries. What was once seen as mysterious fire in the sky is now recognized as a predictable cosmic event. Yet the wonder remains. Even today, when meteors fill the heavens, they inspire the same sense of awe. The Geminids are unusual, born from an asteroid rather than a comet. Most meteor showers are gifts from comets, fragile, icy wanderers that leave behind long trails of dust. But the Geminids, one of the brightest showers of the year, come from something stranger, an asteroid. Their parent body is rocky, compact, and behaves more like a burnt-out comet than a true asteroid. As it approaches the Sun, Phaethon sheds dusty debris that Earth later crosses each December. When those grains slam into our atmosphere, they flare brilliantly as Geminid meteors. Unlike many other showers, the Geminids are famous for their intensity and their variety of colors, flashing white, yellow, and even green. At their peak, hundreds of meteors can streak across the heavens in a single night. That they come from an object neither fully comet nor asteroid makes them unique, a cosmic in-between, a reminder that not everything fits neatly into categories. Fireballs can blaze bright enough to cast shadows at night. Most shooting stars are faint streaks, gone before you can even make a wish. But every so often, one arrives with more brilliance than the rest. These meteors are called fireballs, and their light can rival or even surpass Venus, the brightest planet in the sky. A true fireball can momentarily cast shadows, illuminating the landscape like a brief, silent explosion in the heavens. They're usually caused by larger fragments of rock or metal, sometimes as big as a fist or even larger, hitting the atmosphere at tremendous speeds. As they burn, they often leave glowing trails that linger for seconds. Some fragment and flare multiple times, as though breaking apart in mid-air. Fireballs have startled people for millennia, inspiring awe and fear in equal measure. To see one is to witness a reminder of the energy locked inside even the smallest fragments drifting through space. Bolides explode with thunderous sound as they break apart. A bolide is a fireball taken to the extreme. It doesn't just blaze across the heavens, it detonates. These brilliant meteors explode in the atmosphere with enough energy to produce a flash that can rival the sun and a sound like rolling thunder. Sometimes they break windows or rattle buildings, as with the Chelyabinsk meteor in Russia in 2013. Bolides occur when larger meteoroids, perhaps meters across, strike Earth's atmosphere at hypersonic speeds. The immense pressure of the air causes them to fragment violently, releasing their stored energy in a tremendous burst of light and sound. Ancient records tell of skies filled with fire and booming noises, descriptions that almost certainly came from bolides. Though rare, they remind us that Earth is constantly passing through a shooting gallery of debris, and while most burn harmlessly, some arrive spectacularly, shaking the ground and echoing across the night. Earth is constantly brushed by tiny meteors every night. Even on nights with no meteor shower, Earth is quietly sweeping through streams of space dust. Tiny grains, often no larger than sand, strike our atmosphere continuously. Each one burns up in an instant, too faint for most eyes to notice. Astronomers estimate that more than 100 tons of meteoritic material fall into our atmosphere every single day. That means countless shooting stars are streaking above us at all times, though only a few are bright enough to catch our attention. Larger particles occasionally flare brightly, but most vanish unseen. These cosmic specks are the remnants of comets, asteroids, and collisions in the solar system, endlessly drifting until Earth happens to cross their path. To look up at the stars is to know that the sky is never still. Tiny pieces of the universe are always arriving, burning silently in the darkness. Some meteors leave glowing trails that linger in the night sky like smoke. While most shooting stars vanish in the blink of an eye, some leave behind luminous streaks that hang in the air long after the meteor itself has burned away. These trails are called trains, They form when a fast-moving meteor ionizes the gases in Earth's upper atmosphere, leaving behind a glowing path of charged particles. Depending on conditions, trains can shimmer for minutes, twisting and curling as high-altitude winds reshape them. Sometimes they resemble wisps of smoke, but unlike smoke, they shine faintly with their own ghostly light. Astronomers have studied these trails to better understand both meteors and the winds at the edge of space. The Sky Watchers, they're among the most magical sights of a meteor shower, like a signature written across the sky by something passing from one world into another, fading slowly as though reluctant to leave. The moon is our closest and brightest companion in the night sky. For as long as humans have looked upward, the moon has been our most faithful companion. It is far closer than any star, only about 238,000 miles away, and yet it feels infinite in its moods and forms. It shines not with its own light, but with the reflected glow of the sun, waxing and waning in a cycle that shapes our sense of time. No other object dominates the heavens so completely. The moon has guided storytellers, inspired poets, and served as a natural clock for early civilizations. Its gravity pulls at our oceans, creating the tides that shape life along the shores. Unlike the wandering planets or fleeting comets, the moon is always there, rising and setting with quiet regularity. To step outside and see it is to share a view seen by every human who ever lived. Its phases served as humanity's first calendar. Long before written words or carved stone, humans tracked the sky. The most obvious cycle to follow was the moon's. Its waxing crescent, bright fullness, and fading crescent again form a repeating pattern of about 29.5 days. Early peoples used this cycle to mark the passing of time, planting and harvesting by its phases, celebrating rituals at the new or full moon. Lunar calendars still exist today in many cultures, shaping holidays and traditions across the world. Even our word month is rooted in the moon. Watching it shift night after night gave early observers a reliable rhythm to life. Unlike the sun's yearly cycle, the moon's shorter phases were immediate and visible. They tied the heavens to the daily needs of survival, turning the sky into a clock and calendar long before humanity built its own. Lunar eclipses transform the moon into a copperid orb. Every so often, the moon slips into Earth's shadow, and something extraordinary happens. Instead of disappearing completely, it takes on a deep, coppery glow. This is a lunar eclipse. The reason the moon does not vanish is that Earth's atmosphere bends sunlight, filtering out the bluer wavelengths and casting the longer, redder light into the shadow. From the surface of the moon, Earth would appear as a black disk surrounded by a ring of fiery sunsets all around its edges. That crimson light bathes the lunar surface, reflecting back to us as the haunting blood moon. To stand beneath a clear lunar eclipse is to watch the moon become both familiar and alien, still hanging above, but changed into something shadowed, glowing. Strange. These events can last hours, giving everyone on the night side of Earth a chance to share in the view. Many cultures feared the blood moon as a night sky omen. The eerie red glow of a lunar eclipse has always stirred human imagination. In ancient times, before science explained the phenomenon, people often saw it as a warning. The Inca believed a jaguar was attacking the moon, staining it with blood. In parts of Mesopotamia, eclipses were thought to signal danger for kings, prompting rituals to protect rulers. Some Native American traditions described the moon being consumed or wounded, inspiring chants and ceremonies to restore it. Across the world, the blood-red moon was a celestial omen of war, of famine, of change. Yet, not all traditions feared it. Some cultures viewed the eclipse as a time of renewal or cosmic balance. Today, we understand the science, but the sight still carries a primal weight. Watching the moon blush red in the night sky feels ancient, as though tapping into the same awe felt by every generation before us. A total lunar eclipse can last for more than an hour. Unlike the brief spectacle of a solar eclipse, a total lunar eclipse unfolds slowly and lingers. The moon drifts gradually into Earth's shadow, darkening, then glowing red. Once fully immersed, the total phase can last over an hour, sometimes close to 2. During this time, the moon hovers in its coppery cloak, its face dimmed but still visible. Everyone on the night side of Earth can see it, making it one of the most accessible celestial events. Ancient people gathered to watch, telling stories of gods, spirits, and omens. Today, families and astronomers still do the same, marveling at a spectacle that requires no telescope, only a clear sky. As the moon finally drifts free of the shadow, its familiar silver light returns, and the world feels restored. The slow unfolding makes a lunar eclipse one of the most meditative shows in the heavens. Solar eclipses sweep Earth with a racing shadow. When the moon drifts directly between Earth and the sun, a shadow falls upon the land. But this shadow is not still. It races across the surface, sweeping from west to east at speeds faster than sound. From above, astronauts see it as a dark, moving circle crossing oceans and continents. On the ground, the approach is unmistakable. Light dims, the temperature drops, and silence falls over the landscape. Within minutes, day becomes twilight. Only those standing within the narrow path of totality experience the full eclipse, a fleeting window when the sun vanishes behind the moon. Ancient people surely felt fear as darkness rushed toward them, but today, many travel thousands of miles to stand in that shadow, to witness the rare geometry of Tao. 3 celestial bodies aligned. It is a reminder of how delicate and precise the dance of the cosmos truly is. During totality, stars emerge in the daytime sky. Totality transforms the familiar into something dreamlike. For a few minutes, the sun's blazing light is blocked entirely by the moon, and a dark twilight falls in the middle of the day. In that strange light, stars appear. Venus often shines first, radiant and unmissable, followed by bright stars like Sirius or Regulus. Mercury may be spotted as well, something impossible on an ordinary afternoon. The world grows hushed. Birds settle into roosts. Insects begin their nighttime chorus, and the air feels cooler. Overhead, the sun's corona stretches outward, a delicate crown of light, usually hidden by the overwhelming brilliance of day. To see stars burn in the middle of the day is startling, a reminder that they are always there, patiently shining, whether we can see them or not. For those few minutes of totality, Earth feels suspended between 2 worlds, day and night intertwined. Ancient astronomers could predict eclipses with surprising accuracy. Long before telescopes, ancient astronomers watched the skies with careful devotion. They noticed that eclipses were not random, but part of repeating cycles. The Babylonians discovered the Saros cycle, a rhythm of about 18 years that allowed them to forecast eclipses with remarkable precision. In China, royal astronomers recorded eclipses as omens tied to the fate of emperors, keeping meticulous records stretching back thousands of years. The Maya aligned their great temples with the sun and moon, building calendars that reflected their movements. Even without modern science, these civilizations learned to anticipate celestial events that once terrified entire communities. To stand beneath a darkened sun and know it would return must have felt like power, proof that order lay within the heavens. Their careful records became the foundation for our own understanding, turning mystery into predictability and fear into reverence for the patterns of the cosmos. Venus shines so brightly in the night sky, it can cast shadows. Venus is no ordinary point of light. Often, it is the first to appear in the evening or the last to fade at dawn, a steady lantern in the heavens. Its brilliance is so intense that, under the darkest skies, it can cast faint shadows on the ground, a trick only the full moon can otherwise perform. This brightness comes from its thick reflective clouds, which bounce sunlight efficiently back into space. To ancient people, Venus seemed twofold: the morning star rising before dawn and the evening star glowing after sunset. Only later did they realize it was the same celestial body. Galileo's telescope revealed its phases, like the moon, evidence that it orbited the sun. Today we know its beauty hides a hostile surface, where heat and pressure crush any visitor. Yet from Earth, Venus glows serenely, a radiant beacon bright enough to mark its presence with shadows. Jupiter gleams steadily, outshining most stars. Jupiter is the monarch of the planets, immense and commanding. To the naked eye, it shines as a steady point, brighter than almost every star. Unlike stars, which twinkle through Earth's atmosphere, Jupiter's light is constant, unmistakable against the constellations. Ancient cultures revered it, tying its brilliance to gods of thunder, power, and rulership. Its steady glow masks a world of turmoil, storms swirling in bands of color, with the Great Red Spot, a storm larger than Earth, raging for centuries. When it rises into the night, its presence is undeniable, drawing the eye and holding it. To follow Jupiter across the sky is to watch a giant in slow motion, orbiting far beyond our world, yet visible with startling clarity. Each time it gleams overhead, it reminds us of the scale of the solar system, where even the faintest glow hides unimaginable immensity. With binoculars, its moons appear as tiny jewels beside it. One of the simplest wonders of astronomy requires nothing more than a steady hand and a pair of binoculars. Look at Jupiter, and you may see 4 small lights beside it. These are its largest moons: Io, Europa, Ganymede, and Callisto. Discovered by Galileo in 1610, they shattered the belief that all heavenly bodies revolved around Earth. To the eye, they appear as delicate points, aligned in shifting patterns night after night. Yet each is a world. Ganymede is larger than Mercury. Europa hides an ocean beneath its icy crust, perhaps home to alien life. Io is alive with constant volcanic eruptions. Callisto is scarred with craters older than recorded history. Watching them drift around their giant planet is to see motion on a cosmic scale, proof that other worlds orbit far beyond our own. Even today, their quiet dance feels revolutionary, as it did 4 centuries ago. Saturn's rings can be glimpsed through even a small telescope. Saturn is a planet of quiet beauty, golden and steady in the night sky. To the naked eye, it is lovely, but through a small telescope, the view transforms. Suddenly, a world appears encircled by rings, delicate and impossible. No other sight is quite like it. The rings stretch hundreds of thousands of kilometers, yet they are so thin they almost disappear when viewed John. They are made of icy fragments, some tiny as dust, others the size of mountains, all orbiting together in shimmering bands. Galileo saw them first, though his telescope was too crude to reveal their nature. Centuries later, they remain a favorite target for backyard astronomers. These rings are not eternal. They are slowly crumbling, raining particles into Saturn's atmosphere. In 100 million years, they may be gone, but for now, they remain one of the most exquisite spectacles the sky offers. Mars sometimes glows brighter than Jupiter with a ruddy light. Mars usually hangs modestly in the heavens, a small red ember among the stars. But every 26 months, Earth and Mars line up in opposition, bringing the red planet closest to us. In those moments, it outshines all but Venus, sometimes even Jupiter, glowing fiercely with a ruddy hue. Ancient people saw its fiery light as a symbol of war and blood, naming it after gods of battle. Through telescopes, it reveals ice caps, shifting dust storms, and valleys carved by ancient rivers. During great oppositions, Mars becomes striking, bright enough to command attention from even casual stargazers. Then it retreats, fading back into the background. Its brilliance comes and goes in cycles, a heartbeat between two planets sharing a cosmic neighborhood. Each close approach renews fascination, a chance to look across the void at a world both alien and strangely familiar, waiting for us to return. Mercury is elusive, hiding near the sun's glare. Mercury is a world of secrecy. Always hugging close to the sun, it rarely strays high enough to be seen easily. Most people have never glimpsed it, even though it is visible a few times each year. It rises briefly before dawn or sets just after sunset, shining faintly near the horizon, before vanishing back into sunlight. To ancient observers, it was a quicksilver wanderer, darting across the heavens with unusual speed. It was so tricky to follow that some cultures thought the morning and evening appearances were two different planets. When Galileo's telescope revealed its phases, like those of Venus and the Moon, it became clear Mercury orbited the Sun. Today, it is still a challenge, rewarding patient eyes during moments of greatest elongation. For those who find it, Mercury feels like a hidden treasure, a fleeting ember at the edge of day's light. Uranus and Neptune can just barely be spotted under pristine skies. The solar system extends farther than the ancients could imagine, into realms where faint worlds circle in silence. Uranus, a pale greenish dot, is just bright enough to be glimpsed with the naked eye from the darkest locations, though few ever recognize it. Neptune is fainter still, invisible without optical aid. Their discoveries belong to modern astronomy: Uranus in 1781 by William Herschel and Neptune in 1846, detected first by Dia. Mathematics predicting its position. To glimpse them today is to look to the very edges of what can be seen from Earth. Through telescopes, Uranus appears serene, featureless, while Neptune reveals stormy bands of deep blue. They remind us that not all worlds reveal themselves easily. Hidden in the dark, faint and slow-moving, they are silent sentinels on the outskirts of our planetary family, waiting for curious eyes to seek them out. Comets occasionally streak the night sky with glowing tails. Every so often, a visitor arrives from the depths of the solar system. A comet, made of ice and dust, ventures inward toward the sun. As it heats, gas and dust stream outward, forming a glowing coma and tails that can stretch millions of kilometers. These tails always point away from the sun, sculpted by solar wind and radiation. Some comets become dazzling, dominating the sky for weeks. Hale-Bopp in 1997 and Neowise in 2020 captivated millions, drawing AIs upward. Others are faint whispers, glimpsed only through telescopes. Comets have always stirred awe, for they appear suddenly and vanish without warning, unlike the steady planets and stars. They are fragments from the dawn of the solar system, icy archives carrying secrets of creation. To watch one sweep across the sky is to see a messenger from the outer dark, ephemeral and timeless all at once. Some return only after thousands of years away. Comets move in elongated orbits, some circling the Sun in a matter of years, others taking millennia. Those with long periods may appear once in recorded history, then vanish into the void until far future generations see them again. Their paths carry them beyond Pluto, into the Oort cloud, a vast, unseen reservoir of icy bodies at the solar system's edge. When gravity nudges one inward, it begins a journey measured not in lifetimes, but in civilizations. By the time it returns, languages may have changed, empires may have risen and fallen, and the world itself may be transformed. Imagine an ancient skywatcher recording a comet thousands of years ago, never knowing that the same body will blaze again in our own time. These long-period comets connect us across history, their rare returns stitching together the stories of countless human eyes turned skyward. Halley's Comet visits roughly once every 76 years. Among comets, one is legendary. Halley's Comet is bright, reliable and well documented, returning every 76 years on average. Its appearances are woven into human history. Chinese astronomers recorded it in ancient times. It was depicted in the Bayeux Tapestry in 1066, seen as a portent of conquest. Mark Twain was born as Halley's arrived in 1835 and died during its return in 1910, famously predicting he would. Its path takes it deep into the inner solar system, where sunlight ignites its icy surface into brilliance. Generations pass between its visits, making it a celestial link between grandparents and grandchildren, a reminder of how brief human lifetimes are, compared to cosmic cycles. The next time it graces our skies will be in 2061, and once again, it will remind us of the continuity of time, stretching far beyond individual lives. For centuries, comets were feared as omens of disaster. Before science revealed their nature, comets struck fear into human hearts. Unlike the steady stars and familiar planets, they appeared suddenly, blazing across the heavens without warning. To ancient peoples, their unpredictable presence marked upheaval, wars, plagues, the deaths of kings. The Chinese kept meticulous records of them, interpreting each as a heavenly signal. In Europe, they were dreaded hairy stars, associated with fire and blood. Even into the Renaissance, comets carried reputations as harbingers of catastrophe. Only in the 17th century did astronomers like Edmond Halley begin to understand them as natural phenomena, icy wanderers following predictable paths. Today, comets inspire wonder rather than fear, but the weight of history remains. To imagine a medieval villager gazing at a blazing comet is to feel the raw awe these sudden visitors once provoked. Not beauty, but an omen from the dark beyond. Some comets have crumbled in full view of Earth. Not every comet survives its journey toward the Sun. Some go unstable as heat cracks their icy bodies, and they break apart before our eyes. In 1994, comet shoemaker Levy 9 shattered into fragments that collided spectacularly with Jupiter, each impact leaving scars larger than Dar, Earth itself. More recently, comet Eason, once predicted to dazzle in 2013, disintegrated as it passed close to the Sun, leaving only a faint trace. Watching a comet crumble reminds us that these objects are fragile, held together loosely, remnants from the solar system's earliest days. They can flare suddenly in brightness, then vanish forever, undone by the very star that reveals them. Their destruction is dramatic, but it also teaches astronomers about their composition, unlocking secrets from the dawn of planetary formation. In their fiery deaths, comets remind us of how delicate the building blocks of worlds can be. Auroras drape the night sky in shimmering curtains of light. In the far northern and southern skies, nights sometimes glow with ethereal light. Curtains of green, purple, and crimson ripple across the heavens, shifting and flickering as if painted by unseen hands. These are auroras, the northern and southern lights. They form when charged particles from the sun stream toward Earth and collide with our atmosphere, energizing atoms and making them glow. Each color comes from a different gas. Oxygen paints the sky green and red, while nitrogen glows blue and purple. For those who witness them, auroras feel alive, moving and pulsing with an otherworldly rhythm. They have inspired myths for millennia, spirits dancing, ancestors speaking, or battles waged in the sky. Even with scientific understanding, the beauty remains. To stand beneath an aurora is to feel the planet's connection to the sun directly above you, written in light across the canvas of night. These lights form when solar winds strike Earth's atmosphere. Auroras begin far from Earth, in the furnace of the sun. Solar flares and coronal mass ejections hurl streams of charged particles into space. Some of these reach Earth, where our magnetic field guides them toward the poles. There, they strike the upper atmosphere, colliding with atoms of oxygen and nitrogen. Those atoms absorb the energy, then release it as light, creating shimmering displays that dance across the polar skies. The process is invisible from space, but breathtaking on the ground. Stronger solar storms make the lights more vibrant and push them farther from the poles, sometimes as far south as the Mediterranean or the southern United States. Each aurora is unique, shaped by the strength and direction of solar winds. To witness one is to watch Earth's shield at work, transforming invisible solar fury into beauty, violence turned into luminous serenity. In the far north, auroras can appear almost nightly. For those who live in the high latitudes, auroras are not rare miracles, but recurring companions. In Alaska, northern Canada, Scandinavia, and Siberia, the auroral oval arcs across the sky, and during long winter nights, the lights may appear several times a pow. Weak, sometimes almost nightly. Locals grow up accustomed to their glow, stepping outside on cold evenings to see the horizon pulsing with green or curtains rippling above. Tourists travel great distances in hopes of glimpsing them, waiting in icy darkness for hours. The aurora's regularity in these regions is a gift of geography. Earth's magnetic field funnels solar particles into those skies more often than anywhere else. Yet even for those who see them frequently, auroras never lose their wonder. They are both predictable and unpredictable, familiar yet never the same. Each night sky painted anew by the invisible hand of solar winds. Auroras also shimmer above planets beyond Earth. Earth is not alone in wearing these curtains of light. Other planets with magnetic fields also host auroras. Jupiter's are enormous, powered not only by the solar wind but also by its volcanic moon Io, which spews material into space. These auroras can be larger than Earth itself, glowing in ultraviolet light invisible to human eyes. Saturn has its own, tracing arcs across its poles, while even Uranus and Neptune display auroras shaped by their tilted magnetic fields. Mars, with only remnants of a magnetic field, hosts patchy auroras in localized regions. Studying these lights across the solar system reveals how planets interact with both their star and their own magnetic environments. It also reminds us that auroras are not unique to Earth. They are cosmic phenomena, written wherever winds of charged particles meet magnetic fields. What we see as beauty is a universal signature of energy. The zodiac constellations once guided planting and harvests. Long before calendars, humans looked to the stars for guidance. The zodiac, 12 constellations along the sun's path through the sky, became a celestial calendar. Farmers noticed that when certain stars rose at dawn or set at dusk, the seasons were shifting. The appearance of Virgo or Taurus might signal planting, while Scorpio's return marked harvest. This practical knowledge helped civilizations thrive, tying human survival to the motions of the heavens. Over time, the zodiac became more than a calendar. It evolved into astrology, with constellations linked to personalities and fate. Yet its roots were practical, born from the need to measure time and anticipate the cycles of the Earth. Today, the zodiac remains familiar, though its stars have shifted slightly due to the slow wobble of Earth's axis. Its constellations remind us of the deep bond between human life and the rhythms of the cosmos. The ecliptic marks the sun's yearly path through the constellations. If you watch the sun from the same spot every day, it doesn't wander randomly through the heavens. Instead, it follows a steady path, tracing a great circle across the sky over the course of a year. This path is called the ecliptic. Along it, the sun appears to move from constellation to constellation, guiding the changing seasons. The moon and the planets stay close to this line as well, their orbits aligned with Earth's. For ancient skywatchers, the ecliptic was more than a pattern, it was the spine of the heavens, the stage where the most important celestial actors appeared. Even today, astronomers use it to map planetary positions, and astrologers place their signs upon it. When you follow the ecliptic, you are retracing humanity's first calendar, a line etched into the sky by the rhythm of Earth's orbit around the star that sustains us. Precessions slowly shift stellar positions over millennia. The stars feel eternal, fixed in their constellations. Yet they are not perfectly still. Over thousands of years, Earth's axis wobbles like a spinning top. This slow movement is called precession, and it gradually changes the position of the stars in our sky. Today, Polaris sits almost exactly at the North Celestial Pole, guiding travelers as the North Star. But in ancient Egypt, around 5,000 years ago, it was a different star, Thuban, that held that place of honor. In another 12,000 years, Vega will shine where Polaris is now. Constellations too slowly shift, their outlines subtly changing as the background moves. To us, these changes are imperceptible, but across civilizations they matter deeply, altering calendars and the alignment of temples built to track the heavens. Precession is a reminder that even the most seemingly unchanging things are still in motion, slowly rewriting the sky. The night sky looked different when dinosaurs roamed Earth. Imagine standing on Earth 100 million years ago, when giant reptiles ruled the land. If you looked upward, the constellations we know today would not exist. Stars drift slowly over time, and the familiar patterns, Orion, Ursa Major, Scorpius, were arranged differently back then. Some had not yet taken the shapes we recognize, while others were skewed into unfamiliar forms. The Milky Way still arched across the sky, but its details would have appeared subtly different. Our ancestors never saw that view, but the dinosaurs did, their world bathed in light from stars long since moved. To think that the heavens have shifted so dramatically reminds us how dynamic the universe is. Even the constellations we see as fixed landmarks are temporary, fragile pictures in motion. Millions of years from now, future skies will look strange to human eyes, just as they did to the dinosaurs. Some stars move so swiftly, they distort constellations over time. Constellations are not permanent. They are illusions of perspective, stars at vastly different distances forming shapes by chance. Over time, individual stars drift, slowly altering these patterns. Most move so gradually we never notice, but a few streak across the background with unusual speed. Over thousands of years, these fast movers distort the constellations, bending their outlines. Orion's belt will one day look uneven. The Big Dipper's familiar scoop will eventually lose its shape. These changes happen over spans longer than a lifetime, but across millennia, the night sky transforms. Astronomers measure these motions as proper motion, a subtle shift against the background. By mapping them, we can predict the appearance of future skies or reconstruct the heavens of the distant past. The stars remind us that constellations are not eternal carvings but fleeting alignments, momentary patterns in a universe where everything is always on the hour. Move. Barnard's star drifts faster across the night sky than nearly any other. One star, dim and reddish, moves faster against the background than almost any other. Barnard's star, a faint red dwarf just 6 light-years away, shifts its position noticeably even within a human lifetime. Astronomers call this proper motion, and Barnard's is the largest of all known stars. Year by year, it creeps across the sky, a restless traveler compared to its neighbors. Though invisible to the naked eye without a telescope, it has captured scientific attention for over a century. Once, astronomers even believed planets orbited it, sparking speculation about alien life. Those worlds proved elusive, but the fascination remains. Barnard's star is old, perhaps twice the age of the Sun, and will continue drifting long after our world is gone. It reminds us that the stars we think of as fixed are not fixed at all. They wander, and some wander faster than others. Satellites drift like artificial stars across the night sky. If you watch carefully after twilight, you may notice a point of light moving steadily across the heavens. Unlike airplanes, it makes no sound and leaves no blinking lights. It is a satellite, reflecting sunlight as it orbits Earth. Thousands of them circle above us now, forming a silent population of artificial stars. Their paths are predictable, rising in the west and gliding eastward before fading into Earth's shadow. Early satellites like Sputnik were greeted with wonder, their faint signals inspiring both excitement and fear. Today, constellations of satellites fill the skies, aiding communication, weather forecasting, and navigation. But their growing numbers also raise concerns about crowding the heavens. For the stargazer, spotting one is still magical. To watch a satellite glide overhead is to glimpse humanity's presence in space. Small metal messengers joining the ancient lights that have shone above us for countless ages. The International Space Station often outshines everything but the Moon. The International Space Station, a laboratory orbiting full 100 kilometers above Earth, is one of the brightest objects in the night sky. When sunlight catches its vast solar panels, it glows so brilliantly it can outshine every star and even rival Venus. To the naked eye, it appears as a fast-moving star gliding across the horizon in just a few minutes. For those who know when and where to look, it is a thrilling sight, a reminder that people are up there, circling the planet at over 27,000 kilometers per hour. Inside, astronauts live and work, conducting experiments and watching Earth pass beneath them 16 times a day. The station itself is a symbol of cooperation, built by nations working together. Each time it crosses overhead, it connects the vastness of the sky with the human story, a bright reminder of our fragile presence in space. Satellite flares can briefly rival Venus in brightness. Some satellites do more than simply glide, they flare. When sunlight reflects off their surfaces at just the right angle, they flash brilliantly, outshining nearly every object in the sky. The old iridium satellites with their flat antenna panels were famous for this, producing dazzling bursts visible even from cities. These flares could rival Venus in brightness, startling those who happened to be watching. They last only seconds before fading back into the background. For astronomers, they were both a nuisance and a wonder. Light pollution in one sense, but also a striking example of orbital mechanics at work. Even as satellite designs change and the iridium flares fade into history, new reflections still surprise stargazers. To see a sudden flash from an artificial star is to witness the interplay of sunlight, geometry, and technology, a fleeting spark linking Earth to the machinery. Circling above, rockets sometimes paint glowing trails across the upper atmosphere. When rockets launch, their fiery engines cut through the atmosphere, leaving glowing trails that can stretch for hundreds of kilometers. At high altitudes, these plumes expand and catch the sunlight, even when the ground below lies in darkness. The result is a spectacular vision. Luminous clouds twisting and spreading, shimmering with rainbow hues as ice crystals scatter light. To onlookers who do not expect it, the sight can be startling, resembling a supernatural phenomenon. In truth, it is human technology meeting the upper reaches of the atmosphere, where thin air and sunlight combine to create beauty. These displays are often visible across entire regions, turning ordinary evenings into unforgettable experiences for those who happen to glance upward. They remind us that even the work of rockets, machines of fire and force, can leave behind moments of wonder written gently across the sky. The night sky has grown busier with human-made lights in orbit. For most of history, the sky belonged to nature alone. Stars, planets, comets, and meteors were the only moving lights. But in just a few decades, humans have added thousands of their own. Satellites, space stations, and debris now circle the planet, many reflecting sunlight as they pass overhead. To the naked eye, these appear as moving stars, crossing paths with constellations and streaking through long-exposure photographs. For astronomers, the growing swarm poses challenges, interfering with observations and leaving trails across images of the universe. Yet for ordinary skywatchers, the sight can be strangely comforting, proof that Earth has reached into space, leaving its own quiet signature. The heavens have become a shared space between natural wonders and human creations. Each artificial light is a reminder of our species' ambition and of how quickly we have filled even the quietest places with traces of ourselves. The Hubble Space Telescope revealed breathtaking deep-sea vistas. Launched in 1990, the Hubble Space Telescope has shown us the universe as never before. Orbiting high above the blur of Earth's atmosphere, it captures images with clarity no ground-based telescope could match. Its views of galaxies, nebulae, and star clusters have become iconic, filling books and screens with colors and detail. The pillars of creation, the Sombrero Galaxy, and countless glowing clouds of star birth have entered our imagination because of Hubble. Beyond beauty, it has provided crucial science, measuring the age of the universe, tracking the expansion of space, and uncovering the secrets of distant worlds. For more than 3 decades, it has circled Earth, offering a window into the depths of time and space. Each of its images is a reminder that the universe is not an abstract concept, but a place of vast beauty, waiting patiently to be discovered. Every patch of darkness hides a multitude of galaxies. If you find a patch of night sky that looks empty and stare deeply into it, you might expect nothing more than blackness. But when astronomers turn powerful telescopes towards such regions, they find something astonishing. Within what seems to be blank space are thousands of galaxies, each containing billions of stars. Every tiny speck of light captured is an entire island universe, unimaginably far away, The realization is humbling. The emptiest corner of the sky is anything but empty. It teems with galaxies stacked across time, their light traveling for billions of years before reaching us. This means that whenever we look at darkness, we are not staring into void, but into abundance. The night's quiet spaces hold more worlds than we can fathom, hiding richness behind what appears to be absence. Emptiness, it turns out, is an illusion. The Hubble Deep Field uncovered thousands in a space no larger than a grain of sand. In 1995, astronomers pointed Hubble at a patch of sky so small it looked utterly empty. For 10 days, the telescope stared into that darkness, gathering faint light. The result was extraordinary. Nearly 3,000 galaxies appeared in that tiny view. Later, deep fields revealed tens of thousands. To grasp the scale, hold a grain of sand at arm's length. The area it covers is about the size of the Hubble Deep Field. If so many galaxies exist in such a minuscule fraction of the sky, then the entire cosmos must hold hundreds of billions. Each galaxy contains billions of stars, each with the potential for worlds and perhaps life. That single experiment transformed astronomy, proving that the universe is richer and more crowded than anyone dared imagine. It showed that the most ordinary patch of black sky hides unimaginable abundance. Time itself flows differently across the cosmos. Einstein's theories revealed that time is not universal. It bends and stretches under the influence of gravity and motion. A clock ticking near a massive star runs more slowly than one far away. A traveler moving close to the speed of light experiences time at a different pace than someone standing still. This means the universe does not share a single rhythm, but countless rhythms woven together. In extreme cases, near black holes, for instance, time slows dramatically, almost to a halt from the perspective of an outside observer. Astronauts in orbit experience a tiny difference from us on Earth, their clocks running slightly faster or slower depending on altitude. Time is not fixed, it is elastic. The stars above remind us that even something as fundamental as time itself is part of the cosmos' strange fabric, shaped by the gravity and motion of the heavens. Every star in the night sky is a glimpse into the past. When you look up at the stars, you are not seeing them as they are now. Light takes time to travel, and even the closest star beyond the Sun is more than 4 years away. Many are hundreds, thousands, even tens of thousands of years distant. That means their light began its journey long before the moment you see it, carrying with it a glimpse of the past. Some of the stars you admire may already be gone, their fuel spent, their brilliance extinguished, though their final light is still en route to Earth. To gaze upward is to look back in time, seeing the heavens not in the present, but as they once were. The night sky is a cosmic archive, each star a page of history written in light, reaching us only after unimaginable journeys across the gulfs of space. Some are so distant their light began before humans existed. There are stars and galaxies so far away that their light has been traveling for millions of years, long before humans first walked the Earth. When you see them, you are gazing into epochs where our planet was ruled by dinosaurs, or even into ages before mammals had evolved. The photons that strike your eyes tonight set out on their journey long before humanity appeared, long before there were even forests or flowering plants. Some of that light began its trek in a universe unimaginably young, when galaxies were only beginning to form. To look at such distant objects is to step outside of human history entirely, into a timeline written in starlight and distance. The stars become not just ornaments of the night, but messengers of deep time, telling stories older than humanity itself, stretching far beyond the span of life on Earth. The cosmic microwave background is the afterglow of creation. In every direction, faint radiation fills the sky, invisible to our eyes but detectable with radio instruments. This is the cosmic microwave background, the afterglow of the Big Bang. Nearly 14 billion years ago, the universe was hot, dense, and filled with light that could not escape the thick plasma. As the cosmos expanded and cooled, that light finally streamed free, filling all of space. What remains today is a faint echo, cooled to just a few degrees above absolute zero, but still present everywhere. First discovered accidentally in the 1960s, it has since become one of the most important clues to our origins. Tiny fluctuations in this afterglow show where galaxies would one day form. To study it is to peer into the universe's infancy, when the first light escaped into darkness, and creation's earliest memory was written across the sky. Though invisible to our eyes, it permeates all of space. The cosmic microwave background is not confined to one corner of the heavens. It fills the universe completely. No matter where you point an antenna tuned to the right frequencies, the signal is there, faint, steady, and ancient. In fact, a small fraction of the static once seen on old television sets came from this background radiation, whispers of the universe's birth arriving in every home. Though invisible, its presence is undeniable. It tells us that the cosmos was once unimaginably hot and uniform, before expanding into the vast, varied place we inhabit now. To know that every patch of space carries this same signature is humbling. It means that no matter where you stand on Earth, or anywhere in the universe, you are bathed in the same relic glow, the quiet memory of a creation that still lingers. Around us, the heavens once held the first galaxies forming at cosmic dawn. Billions of years ago, when the universe was young, the first galaxies began to form. Clouds of hydrogen and helium collapsed under gravity, igniting the earliest stars. These stars were massive, bright, and short-lived, living fast and dying in brilliant explosions. Their deaths seeded the cosmos with heavier elements, the raw material for planets and life. These galaxies were small and chaotic compared to the great spirals and ellipticals we see today. But they were the pioneers, stitching light into darkness. Astronomers call this period the cosmic dawn, the time when the universe first began to glow with starlight. To see them now requires peering across immense distances and timescales, catching their faint glow as it was over 13 billion years ago. They remind us that everything we see today, every star, every world, every living being, traces its origin back to that dawn. The James Webb Telescope peers back toward that dawn. Launched in 2021, the James Webb Space Telescope was designed to look farther back in time than any telescope before it. With its massive gold-coated mirror and instruments sensitive to infrared light, it can detect the faint glow of galaxies that formed only a few 100 million Presti, years after the Big Bang. Already, Webb has revealed galaxies brighter and more massive than astronomers expected so early in cosmic history, challenging our understanding of how the universe grew. Its images show newborn stars wrapped in clouds of dust, planets orbiting distant suns, and light stretched into red by the universe's expansion. Webb peers into epochs we could only imagine before, bringing us closer to the cosmic dawn when the first galaxies sparked. Each discovery reminds us that the universe still holds surprises, waiting to be uncovered in the faint light traveling to us across billions of years. Some stars orbit the galaxy's center at dizzying speeds. At the heart of the Milky Way lies a supermassive black hole, a gravitational anchor around which everything revolves. Most stars circle the galactic center leisurely, taking hundreds of millions of years to complete one orbit. But closer in, the pace becomes astonishing. Some stars, known as S-stars, whip around the black hole at thousands of kilometers per second, completing an orbit in just a handful of years. Observing them has given astronomers direct proof of the black hole's immense pull, an invisible force revealed only by the frantic dance of nearby stars. From Earth, these stars are faint pinpricks of light, but their motion tells us volumes. They remind us that even the quiet night above is filled with furious speed and invisible gravity. Their dizzying orbits are a glimpse into the raw power that lies at the very heart of our galaxy. Hypervelocity stars are flung outward like slingshot stones. Every so often, a star is caught in a deadly encounter with the black hole at the center of the galaxy. If it approaches too closely, tidal forces can tear apart a binary pair, capturing one star while hurling the other outward at incredible speed. These exiles are called hypervelocity stars, and they race through the Milky Way at millions of kilometers per hour, fast enough to one day escape entirely. To the naked eye, they are indistinguishable from ordinary stars, but careful measurements reveal their extraordinary velocities. They are cosmic fugitives, torn from their homes by gravity's violent sling. Each carries with it a history of turmoil, a story of close brushes with destruction. To think of stars themselves wandering into intergalactic space is humbling. Entire suns cast adrift, traveling alone into the endless dark, never to return to the crest. Galaxy that once birthed them. Rogue planets wander invisibly through the night sky without suns of their own. Planets are usually bound to stars, but not all remain tethered. Some are ejected from their systems, sent adrift through the galaxy. These are rogue planets, lonely worlds that wander the dark without a sun to warm them. Invisible to ordinary sight, they can number in the billions, perhaps outnumbering stars themselves. Some may carry thick atmospheres or subsurface oceans, heat preserved by internal energy or radioactive decay. If life could exist in such places, it would thrive in perpetual night, forever hidden from starlight. Astronomers detect them through subtle gravitational effects, watching for the faint bending of background starlight as a rogue world passes in front. Each discovery deepens the mystery of how many such exiles may drift unseen between the stars. They remind us that not all planets belong to familiar systems. Many wander alone, silent and cold, across the cosmic void. Vast clouds of dust obscure entire regions from view. The heavens appear clear and transparent, but vast regions of space are veiled. Interstellar dust, fine grains smaller than smoke particles, floats in great clouds that block visible light. These clouds can obscure entire clusters of stars, turning rich regions of the Milky Way into dark patches. To ancient observers, they looked like holes in the sky, places where stars were absent. But we now know they are nurseries, places where stars are born from collapsing gas. Within them, gravity pulls material together until new suns ignite. Though dust hides their brilliance, it also protects fragile beginnings from harsh radiation. These clouds are paradoxical. They conceal and they create, hiding stars while giving rise to them. Through infrared and radio light, astronomers peer inside, revealing structures unseen to the human eye. The darkness between the stars, it turns out, is full of birth and becoming. Infrared light pierces these clouds to reveal hidden suns. While dust blocks visible light, longer wavelengths slip through. Infrared radiation, invisible to human eyes, reveals the stars and structures hidden within dark nebulae. Telescopes tuned to these wavelengths can see newborn suns glowing in their cradles, wrapped in cocoons of dust. They also expose planetary disks, the beginnings of solar systems forming around young stars. Missions like the Spitzer Space Telescope and the James Webb Telescope have transformed our view, turning opaque shadows into landscapes alive with hidden light. Where the naked eye sees only blackness, infrared shows clusters of suns, filaments of gas, and galaxies veiled by their own dust. It is like lifting a curtain on the universe, revealing what lies beneath. The cosmos is not empty where it looks dark. It is filled with hidden brilliance, waiting for the right kind of vision to bring it into sight. Radio waves from quasars travel across billions of years to reach us. Some of the most powerful signals in the universe come not from nearby stars but from quasars, brilliant, active galaxies with supermassive black holes at their diyar. Centers. As matter spirals into these black holes, it heats to extreme temperatures, blasting radiation across the spectrum, especially in radio waves. These signals cross unimaginable distances, traveling for billions of years before they reach Earth. Quasars are so distant that many shine from a time when the universe was young, only a fraction of its current age. They are lighthouses from the deep past, their steady emissions cutting across time and space. Radio telescopes on Earth capture their faint whispers, transforming them into data that reveals the growth of galaxies and black holes. To listen to a quasar is to hear echoes of a cosmos still in its adolescence, voices carried forward from the earliest chapters of creation. Some quasars blaze brighter than whole galaxies combined. Though they are powered by black holes, quasars are anything but dark. They blaze with such intensity that a single quasar can outshine every star in its host galaxy. Their brilliance comes from matter spiraling inward, heated to millions of degrees as it falls. Some emit jets of particles stretching for millions of light years, colossal beams visible across the universe. To the eye, a quasar looks like a faint star, but behind that point of light is energy greater than entire galaxies. They are cosmic paradoxes, destruction and creation entwined. Quasars illuminate the distant universe, marking the locations of galaxies from the time when the cosmos was still assembling. Their light, crossing billions of years, reaches us as a record of both violence and beauty. To know that such brilliance exists so far away is to realize how powerful the engines of the universe truly are. Gamma-ray bursts shine for moments yet outshine the universe. Among the most violent events known are gamma-ray bursts, fleeting explosions that release more energy in seconds than our sun will emit in its entire lifetime. They are thought to occur when massive stars collapse into black holes or when neutron stars collide, sending shockwaves through space. For a brief moment, their light overwhelms the combined output of every star in the observable universe. Most last only seconds, some just milliseconds, before fading into afterglows detectable in X-rays and radio waves. They are so distant that their light often began traveling billions of years ago, yet they still dazzle our instruments today. Though invisible to human eyes, gamma-ray bursts are caught by specialized satellites, alerting astronomers to their fleeting presence. To witness such power, even indirectly, is to confront the extremes of the cosmos, explosions that briefly eclipse creation itself before vanishing into me. Silence. The night sky is alive with signals across the spectrum. When we look upward, our eyes capture only a sliver of the universe, visible light. Yet the cosmos hums with signals across the full electromagnetic spectrum. Radio waves flow from distant quasars. Microwaves echo the birth of the universe. Infrared warmth radiates from dust clouds, ultraviolet. Streams from hot young stars, X-rays blaze from black holes, and gamma rays flash from cataclysms. Each band reveals a different layer of the same story. The quiet sky is, in truth, buzzing with information, a symphony of light at many frequencies. Astronomers build instruments tuned to these wavelengths, creating a fuller picture of the universe. To see only invisible light is to glimpse just one note of a vast cosmic chord. The night above is not silent or still, it is alive with hidden energy, signals constantly weaving through the dark, carrying the history of everything. Every glance upward is a look into the history of the universe. When you raise your eyes to the stars, you are not just seeing space. You are seeing time. Every point of light is a messenger from the past, its journey stretching across years, centuries, or billions of years. The farther away it is, the older the story it carries. The nearest stars show us years ago. The Andromeda galaxy shows us millions of years ago. The faintest galaxies we can detect reveal the universe as it was shortly after the Big Bang. The sky is a vast archive, its light layered like the pages of a book. Each glance upward is not into the present but into memory, the universe showing us itself as it once was. To lie beneath the stars is to lie beneath history itself, immersed in a chronicle written in light, stretching back to the very beginning of time. The night sky contains stars that no longer exist. When you gaze at the night sky, many of the stars you see are already ghosts. Because light takes years, sometimes thousands of years, to travel to Earth, we are seeing stars not as they are now, but as they once were. A star 500 light-years away could have exploded centuries ago, and we wouldn't know until its final light reaches us. Some of the stars in our sky might already be neutron stars or black holes, invisible except for their lingering glow. This makes stargazing a kind of time travel, where every point of light is a message from the past. It's a reminder that the night sky is not a static picture, but a living story, with stars constantly being born, evolving, and dying. Every glance upward may include stars that no longer shine in the present, only in memory carried by their light. Wormholes could connect distant parts of the universe. Einstein's equations allow for solutions called wormholes, tunnels through spacetime that could connect two distant points. In theory, one could step into a wormhole and emerge instantly in another galaxy or even another universe. Wormholes remain speculative, but the math doesn't rule them out. The challenge is stability. A natural wormhole would collapse instantly unless held open by exotic matter with negative energy. Some scientists suspect quantum fluctuations might create tiny wormholes at microscopic scales, flickering in and out of existence. Others wonder if supermassive black holes could hide entrances. Wormholes have become a staple of science fiction because they seem to offer shortcuts across cosmic distances, turning the impossible into the imaginable. While we have no evidence they exist, their possibility keeps alive one of astronomy's most tantalizing questions. Could the universe hide bridges through space and time? Colliding neutron stars can create ripples in spacetime. When two neutron stars spiral together, their dance ends in one of the most violent events in the cosmos. As they collide, they generate both gravitational waves and bursts of light across the spectrum. This dual signal was detected in 2017 for the first time, marking a breakthrough in astronomy. The event not only confirmed predictions about gravitational waves, but also revealed where heavy elements like gold and platinum come from. The collision created a kilonova, a brilliant explosion that spread newly forged elements into space. In fact, much of the gold on Earth may have been born in such cataclysms. These collisions give us a rare laboratory for testing extreme physics, dense matter, strong gravity, and nuclear reactions all at once. By listening to spacetime itself and watching the accompanying flash of light, astronomers can study the death throes of stars with unprecedented clarity. Magnetars have magnetic fields strong enough to tear atoms apart. Most stars fade quietly, but some collapse into magnetars, neutron stars with unimaginably strong magnetic fields. A magnetar's field can be 1 trillion times stronger than Earth's. So intense, it could erase credit cards from half the distance to the Moon. If one were close to Earth, it could disrupt our planet's magnetic field and electronics instantly. These fields are powerful enough to deform atoms, stretching them into needle-like shapes. Occasionally, magnetars release starquakes or bursts of X-rays and gamma rays that can briefly outshine all the other stars in their galaxy. Fortunately, the nearest known magnetars are thousands of light-years away. Still, studying them helps astronomers understand how matter behaves under conditions that cannot be recreated on Earth. They are cosmic extremes, demonstrating the wild possibilities of what stars can become after their fiery lives end. The universe could one day spawn new universes. One of the boldest ideas in modern cosmology is that our universe may not be the only one. Some theories suggest that black holes could act as seeds for new universes, each with its own laws of physics. Others propose that space itself continually spawns bubble universes in a vast multiverse, each expanding away into isolation. In this view, what we call the Big Bang may have simply been the birth of our particular bubble. If true, our universe is just one chapter in an infinite story. While evidence is hard to come by, researchers look for subtle clues, such as imprints in the cosmic microwave background that could hint at collisions with other universes. For now, the multiverse remains speculative, but it raises a profound question. Is everything we know only a small part of a much greater cosmic landscape? White holes may be the opposite of black holes. Black holes trap everything, even light, but their theoretical opposites, white holes, would do the reverse. A white hole would be an object that nothing could enter, only exit. Matter and energy would erupt outward, unable to fall back in. While none have ever been observed, white holes appear as possible solutions to Einstein's equations. Some theories even suggest they could be linked to black holes, with matter falling into one end and emerging from the other. Others wonder if the Big Bang itself was like a white hole, spewing out all matter and energy at once. For now, white holes are purely hypothetical, but the concept challenges our understanding of time and gravity. They represent a mirror image of one of nature's strangest objects, hinting that the cosmos might hide not only traps, but also one-way fountains of beauty. Creation. The universe once glowed orange before it went dark. The early universe did not look like the black sky we see today. After the Big Bang, the cosmos was hot and dense, filled with a glowing plasma of particles and light. As it expanded, it cooled, and around 380, 000 years after its birth, atoms finally formed. At that time, the entire universe glowed with a brilliant orange light, not unlike the surface of a star. As it expanded further, that light stretched into longer wavelengths, eventually shifting out of visible range into microwave radiation. Today, we see it as the faint cosmic microwave background, a nearly uniform glow across the sky. The discovery of this ancient light in 1965 confirmed the Big Bang and gave astronomers a window into the universe's infancy. The idea that the cosmos once blazed orange and then faded into darkness is a vivid reminder of how much it has changed over time. Pulsars send beams of radiation like cosmic lighthouses. Some neutron stars become pulsars, spinning so fast that they sweep beams of radiation across space. When these beams pass Earth, we detect them as regular pulses, often hundreds per second. Pulsars are so precise that they can be used as cosmic clocks, their timing rivaling atomic clocks on Earth. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, and its regular signals were so strange that astronomers briefly dashed her. Wondered if it was evidence of extraterrestrial life. Today, we know pulsars are natural, but no less fascinating. They help us study extreme physics, including dense matter and strong magnetic fields. Arrays of pulsars are even used to search for gravitational waves by detecting tiny shifts in their timing. Each one is a lighthouse shining across the galaxy, born from the violent death of a massive star. Some gamma-ray bursts are visible across the universe. Gamma-ray bursts are not only intense, but also visible from astonishing distances. Some of them originate over 10 billion light-years away, yet they remain detectable on Earth. That means the explosion was so powerful it outshone the entire galaxy it came from, blazing across most of the observable universe. These distant signals let astronomers study the conditions of the early cosmos, when the first stars and galaxies were forming. In a way, gamma-ray bursts act as beacons, carrying information from times long before our solar system existed. Because they occur unpredictably, astronomers rely on satellites constantly scanning the sky to catch them in action. Each detection is a chance to learn not just about the violent death of a star, but also about the universe as it was billions of years ago. The signal was so small it measured a fraction of a proton's width. When the Laser Interferometer Gravitational Wave Observatory LIGO detected gravitational waves for the first time in 2015, signal was unimaginably small. The distortion of spacetime stretched and squeezed distances by less than 1/10,000th of the width of a proton. To measure this, LIGO used laser beams traveling back and forth along 4-kilometer arms, comparing their paths with extraordinary precision. The fact that humans built an instrument sensitive enough to detect such a tiny ripple is as astonishing as the cosmic event itself, two black holes merging over 1 billion light-years away. The detection confirmed Einstein's century-old prediction and opened an entirely new window on the universe. Each new gravitational wave signal adds to our knowledge of how black holes, neutron stars, and space-time itself behave. It's a reminder that sometimes the smallest measurements reveal the largest truths about reality. Saturn's rings are younger than the dinosaurs. Saturn's famous rings look timeless, but evidence suggests they are surprisingly young, only about 100 million years old. That means they formed long after the dinosaurs first walked the Earth, and may even vanish in another 100 million years. The rings are made mostly of water ice, along with dust and rock, spread into countless fragments ranging from tiny grains to house-sized boulders. They may have formed when a moon or comet strayed too close and was torn apart by Saturn's gravity. Observations show the rings are slowly losing material, spiraling into the planet in what scientists call ring rain. To us, they appear eternal and serene. Yet they are a temporary feature in the life of Saturn. If humanity survives long enough, we may one day witness their gradual disappearance, proof that even the most beautiful cosmic structures are fleeting. Europa's ocean may contain more water than Earth. Jupiter's icy moon Europa hides a secret beneath its frozen surface, a vast ocean of liquid water. Estimates suggest this hidden sea may contain twice as much water as all of Earth's oceans combined. Heat from tidal flexing, caused by Jupiter's immense gravity pulling on Europa's interior, keeps the ocean from freezing solid. The cracked, ridged ice above suggests constant movement, with possible plumes of water vapor venting into space. Scientists consider Europa one of the best places to search for life beyond Earth, because liquid water, energy, and chemical building blocks may all be present. Future missions, like NASA Europa Clipper, aim to study its surface and look for signs of habitability. If life exists there, it could be entirely different from life on Earth, thriving in darkness under kilometers of ice, a second ocean world orbiting quietly in our brood. Solar System. Titan has rivers and lakes of liquid methane. Saturn's moon Titan is the only place in the solar system besides Earth known to have stable liquids on its surface. But instead of water, Titan's rivers, lakes, and seas are filled with liquid methane and ethane, hydrocarbons that are gases on Earth. Its thick orange atmosphere, richer in nitrogen than ours, allows a methane cycle similar to Earth's water cycle, with clouds, rain, and flowing channels. Titan's lakes can be hundreds of kilometers wide, and its rivers carve valleys across the surface. Beneath its icy crust, Titan may also hide a liquid water ocean, making it a world with two very different layers of seas. Future missions, like NASA Dragonfly rotorcraft, will explore Titan's surface directly. Studying Titan is like looking at a mirror of early Earth, alien and cold, yet strangely familiar, with weather, erosion, and landscapes shaped by liquid. Enceladus shoots water geysers into space. Enceladus, another moon of Saturn, is only about 500 kilometers wide, yet it is one of the most fascinating worlds in the solar system. Beneath its icy crust lies a global ocean, kept warm by tidal heating. Along cracks near its south pole, enormous geysers erupt, blasting water vapor and ice particles hundreds of kilometers into space. These plumes contain salts and organic molecules, hinting that Enceladus's ocean may be chemically rich and potentially habitable. The Cassini spacecraft even flew through the geysers, directly sampling the material and confirming the presence of complex molecules. The ejected ice particles feed Saturn's faint E-ring, creating a direct connection between the moon and its planet. Enceladus shows that even tiny moons can harbor dynamic oceans and may even host conditions suitable for life. It's a reminder that habitable environments may hide in unexpected places. Some moons have oceans hidden beneath ice. Europa and Enceladus aren't alone. Other moons may also hide oceans beneath icy crusts. Ganymede, the largest moon in the solar system, appears to contain a deep saltwater ocean beneath layers of ice. Callisto may hold one as well, along with Neptune's moon Triton. Even Pluto may have a subsurface ocean. These hidden seas are kept liquid by internal heat and the tidal flexing caused by their planet's gravity. Unlike Earth's surface oceans, they're cut off from sunlight, meaning any life there would need to rely on chemical energy rather than photosynthesis. These discoveries expand the idea of habitability far beyond Earth-like worlds with surface water. The universe may be full of ocean planets concealed beneath ice shells, waiting to be explored. Instead of being rare, liquid water and possibly life may be far more common than we once believed. Pluto has a beating heart of ice that moves its atmosphere. Pluto, once considered the ninth planet, has a surprising feature: a massive heart-shaped glacier of nitrogen ice called Sputnik Planitia. This icy plain appears to act almost like a beating heart for the dwarf planet. As the nitrogen ice warms and cools, it sublimates into gas and then refreezes, driving winds that shape Pluto's thin atmosphere. This cycle creates weather patterns and moves hazes around the surface. The ice plain itself is geologically active, with convection cells slowly overturning material like a pot of boiling water, even though Pluto is billions of Chambra, kilometers from the Sun. The discovery of this dynamic heart by the New Horizons spacecraft in 2015 transformed our view of Pluto from a frozen relic into a surprisingly active world. Even small, distant objects can have rich, evolving geologies that connect surface, atmosphere, and interior in unexpected ways. Neptune's moon Triton orbits backwards. Most moons orbit in the same direction their planets rotate, but Neptune's largest moon, Triton, is an exception. It circles Neptune in a retrograde orbit, moving opposite to the planet's spin. This unusual path suggests Triton was not born around Neptune but was captured, likely a wandering object from the Kuiper Belt. Triton is geologically active, with geysers of nitrogen gas erupting from beneath its icy surface. It may also contain a subsurface ocean, making it one of the most intriguing targets for future exploration. Over time, Neptune's gravity is slowly pulling Triton inward. In billions of years, it could either crash into Neptune or break apart into a spectacular ring system. Triton's backwards orbit makes it a cosmic oddball, a reminder that the solar system's history is full of captures, collisions, and rearrangements that shaped the worlds we see today. The Sun could swallow over 1 million Earths inside it. The Sun dominates our solar system, making up more than 99% of its total mass. Its sheer scale is difficult to grasp. Over 1 million Earths could fit inside it. The Sun's diameter is about 109 times greater than Earth's, and it contains enough mass to anchor the orbits of all the planets. Powered by nuclear fusion in its core, it releases energy equivalent to billions of hydrogen bombs exploding every second. Yet despite this ferocity, it shines steadily, bathing Earth in life-giving light. The Sun is a middle-aged star, about 6 billion years old, and will keep shining for another 5 billion years before expanding into a red giant. Its immensity gives perspective. Our world, vast to us, is just a speck in the furnace of the solar system's star. Jupiter's gravity saves Earth from doomsday asteroids. Jupiter is not only the largest planet in the solar system, but also a cosmic shield. Its immense gravity acts like a vacuum cleaner, pulling in or deflecting asteroids and comets that might otherwise strike Earth. Without Jupiter, the inner planets would face far more impacts, including catastrophic collisions that could wipe out life. Astronomers believe Jupiter's protective role has been crucial in Earth's long history, allowing complex organisms to evolve without constant reset by giant impacts. Evidence of this shielding is written on Jupiter itself. Its atmosphere bears scars from massive collisions, like the famous impact of comet Shoemaker-Levy 9 in Sucker, 1994, which left Earth-sized marks. Though Jupiter can also occasionally nudge asteroids toward the inner solar system, its overall effect is protective. Our solar system's giant guardian is a reminder that Earth's survival has always depended on forces far beyond our planet. Some asteroids have moons of their own. Asteroids are usually imagined as solitary rocks drifting through space, but some have companions. Dozens of asteroids have been found with tiny moons orbiting them. In some cases, asteroids even have 2 moons, creating miniature solar systems. These moons likely formed when impacts knocked debris off the parent asteroid, or when a smaller object was captured by its gravity. Observations of these systems are valuable because their orbital motion lets scientists calculate the asteroid's mass and density more precisely. One famous example is the asteroid Ida, discovered by the Galileo spacecraft in 1993, to have a small moon named Dactyl. The existence of asteroid moons shows how dynamic and complex even small bodies in the solar system can be. They remind us that gravity works at every scale, sculpting not just galaxies and stars, but even rocks only a few kilometers wide. The largest asteroid is almost a dwarf planet. The asteroid belt between Mars and Jupiter is filled with rocky bodies, but one stands out: Ceres. At merely 1,000 kilometers across, it is by far the largest asteroid, so large that it is classified as a dwarf planet. Ceres contains about a third of the belt's total mass. Its surface is a mix of rock and ice, with evidence of cryovolcanism, volcanoes that erupt not lava, but water and salts. Bright patches on its surface, like those in Okator crater, suggest deposits of salty material left by briny water reaching the surface. Ceres may even harbor a subsurface ocean, raising the possibility of habitability. When NASA Dawn spacecraft orbited Ceres from 2015 to 2018, it revealed a surprisingly complex world, not just a dead rock. The largest asteroid shows how diverse and unexpected even small solar system bodies can be. Comets may have delivered Earth's first water. One of the enduring mysteries of Earth's history is where its water came from. Early Earth was hot and dry, yet today our planet is covered in oceans. Many scientists believe comets may have played a role. Comets are icy bodies that travel through the solar system, carrying water frozen in their cores. When they collide with planets, they can deliver that water. By comparing the chemical makeup of cometary ice with Earth's oceans, astronomers can test this idea. Some comets have water similar to ours, while others are different, suggesting multiple sources. Asteroids may also have contributed. Still, comets remain prime suspects, delivering not only water but also organic molecules. If true, then every sip of water and every living cell owes part of its existence to ancient comet impacts, carrying the seeds of habitability to a young and barren Earth. Comets leave glowing trails hundreds of millions of miles long. When a comet approaches the Sun, its icy surface begins to vaporize, creating a glowing coma and tail. So a wind pushes dust and gas outward, forming tails that can stretch for hundreds of millions of miles, far longer than the distance between Earth and the Sun. Some comets even have two tails, a curved dust tail and a straighter ion tail, glowing in different colors. From Earth, these displays can be spectacular, turning a small icy body into a luminous streak across the night sky. The tails always point away from the Sun, no matter the comet's direction of travel, because solar particles are constantly streaming outward. Comets remind us that even tiny frozen relics can produce cosmic spectacles when they wander inward. Their long, glowing tails are not just beautiful, they are trails of history, marking journeys that began in the outermost reaches of the solar system. Earth's moon was born in a planet-sized collision. A leading theory for the moon's origin is the giant impact hypothesis. About 4.5 billion years ago, a Mars-sized body, often called Theia, slammed into the young Earth. The collision was so violent that it vaporized rock and sent debris into orbit. Over time, that material coalesced into the moon. Evidence for this comes from the moon's composition, which is strikingly similar to Earth's outer layers. The moon's creation reshaped Earth as well, tilting its axis and stabilizing its rotation. This stability has been crucial for maintaining long-term climates, allowing life to develop. The moon is therefore not just a companion, but a direct product of Earth's violent past. Without that ancient impact, our planet might be very different, and life as we know it might never have emerged. The moon carries in its very existence the story of Earth's earliest days. Without the moon, Earth would wobble like a toy top. The moon does more than light up our nights. It stabilizes Earth's tilt. Without it, our planet would wobble chaotically, like a spinning top slowing down. Over long timescales, that wobble could swing Earth's axis dramatically, causing extreme shifts in climate. The moon's gravity also controls tides, stirring the oceans and influencing ecosystems. These regular tides may have been important for the evolution of life along coastlines. Some scientists think the moon even helped shape Earth's seasons, keeping them relatively mild compared to what they might otherwise be. In essence, the Moon acts like a stabilizing hand, keeping Earth's rotation steady. Our planet's balance and the habitability we enjoy is tied directly to the silent pull of our only natural satellite. Life on Earth, in a very real sense, owes its stability to the Moon. The Moon is slowly drifting away from Earth. Every year, the Moon moves about 3.8 centimeters farther from Earth. This is caused by tidal interactions. Earth's rotation drags on the ocean tides, transferring energy to the Moon and nudging it outward. Measurements from lasers bounced off reflectors left by Apollo astronauts confirm this drift with incredible precision. Over hundreds of millions of years, this slow retreat adds up. In the distant past, the Moon was much closer, looming larger in the sky and making tides stronger. In the distant future, as the Moon drifts farther away, solar eclipses will no longer perfectly cover the Sun. They will become annular, with a ring of sunlight surrounding the Moon. Though imperceptible on human timescales, this gradual separation is reshaping the Earth-Moon relationship. The Moon is not a fixed companion, but a slow traveler, inching outward into the solar system. Some moons are shaped like potatoes. Not every moon is round. Smaller moons, with less gravity to pull them into a sphere, often take on odd, lumpy shapes. Some look like potatoes, peanuts, or chunks of rock. Mars's moons, Phobos and Deimos, are classic examples, resembling irregular asteroids more than miniature planets. These shapes tell a story of their origins. Many such moons were likely captured asteroids, pulled into orbit by their planets. Their irregularity also means their gravity is uneven, creating strange surface conditions. Walking on such a world would be disorienting, with gravity pulling in odd directions. The tater-shaped moons remind us that the solar system is full of variety, from giant spherical worlds to tiny misshapen rocks. Each one, no matter how small or oddly shaped, adds to the diversity of landscapes in the cosmic neighborhood. A day on Venus lasts longer than a year. Venus rotates on its axis so slowly that a single day, one full spin, lasts 243 Earth days. That's even longer than its year, which takes only 225 Earth days to orbit the Sun. To make things stranger, Venus spins backward compared to most planets, so the Sun rises in the west and sets in the east. The slow rotation contributes to its extreme climate. Thick clouds trap heat in a runaway greenhouse effect, making Venus the hottest planet in the solar system. Its crushing atmosphere and scorching surface are reminders of how differently planets can evolve. Venus may once have had oceans, but today it is a hostile world with a sky of acid clouds. Studying Venus helps scientists understand Earth's climate as well, showing how delicate the balance of habitability can be. Its long day and short year make it one of the strangest neighbors we have. Mars once had oceans deeper than the Atlantic. Billions of years ago, Mars looked very different. Evidence from ancient river valleys, lake beds, and mineral deposits shows that the red planet once had vast oceans. Some estimates suggest these seas may have been deeper than the Atlantic Ocean. The northern hemisphere, with its lower elevation, may have held an ocean covering nearly a third of the planet. Over time, Mars lost its magnetic field, and with it, protection from the solar wind. Its atmosphere thinned, water evaporated, and much of it escaped into space. What remains is locked as ice, underground, and at the poles. These ancient oceans may have provided the right conditions for life to emerge, even if only in microbial form. Today, rovers and orbiters search for chemical signatures that might confirm this. Mars reminds us that even dry, barren worlds can hold memories of once blue oceans. Mercury shrinks as its core cools. Mercury, the smallest planet in the solar system, is shrinking. Over billions of years, its massive iron core has cooled and contracted, causing the surface to wrinkle and crack. These wrinkles, called lobate scarps, stretch for hundreds of kilometers across the planet. NASA Messenger spacecraft revealed thousands of them, showing that Mercury is still geologically active on a small scale. The shrinking has reduced the planet's diameter by more than 7 kilometers. Unlike Earth, with its complex tectonics, Mercury has only this one global process shaping its surface. These scarps are geological time capsules, recording the slow cooling of a small world over billions of years. Mercury's shrinkage is a reminder that planets evolve not only through impacts and volcanism, but also through the quiet contraction of their interiors as they beat prior, radiate heat into space. Even the innermost planet is still settling into its final form. The coldest known place in the universe is a Boomerang Nebula. The coldest natural place we've discovered isn't on Earth, but in deep space. The Boomerang Nebula, a cloud of gas about 5,000 light-years away, has a temperature of just 1 Kelvin, colder than the background. Temperature of space itself. It formed as a dying star ejected gas at incredibly high speed, expanding so rapidly that it cooled beyond what seems possible. Light from the nebula is scattered by dust, giving it a ghostly glow and the shape of a faint bow tie. This bizarre object challenges our understanding of how stars die and how cold matter can become. Astronomers study it as a natural laboratory, since no conditions on Earth can replicate such extreme cold. The Boomerang Nebula is a reminder that even the death of a star can create strange and beautiful environments, some colder than the deepest vacuum we can imagine. The hottest known place exists around quasars. At the other extreme, the hottest natural environments in the universe are found around quasars, galaxies powered by supermassive black holes consuming enormous amounts of matter. As material spirals inward, it compresses and heats to unimaginable temperatures, reaching hundreds of billions of degrees. These hot plasmas release radiation across the spectrum, outshining entire galaxies. Quasars are visible from billions of light-years away precisely because of this extreme heat. Some of the hottest regions are in the accretion disks just outside the black hole's event horizon, where gravity and friction combine in a cosmic furnace. No material can withstand such conditions, but they provide astronomers with a way to study matter under extremes that can't be reproduced on Earth. Quasars remind us that the universe is not only vast, but also wildly intense, with environments hotter than anything we could create or survive. Some regions of space are expanding slower than others. The universe's expansion is not perfectly uniform. Observations suggest that some regions are expanding slightly faster or slower than the cosmic average. Astronomers call this the Hubble tension, because different methods of measuring the expansion rate give different results. One possibility is that local variations in matter, clusters of galaxies or cosmic voids, affect the measurements. Another possibility is that our current model of the universe is incomplete and new physics may be at play. Some scientists suggest that dark energy itself could vary across space, causing different rates of expansion in different regions. If true, the universe might be more uneven and dynamic than we imagine. The mystery is ongoing, and solving it could transform cosmology. It's a reminder that even with the most powerful telescopes, we are still piecing together how the universe truly behaves on the largest scales. Space has a temperature just above absolute zero. Far from stars and galaxies, the universe is not completely cold, but hovers at a steady background temperature, about 2.7 Kelvin, just above. Absolute zero. This faint warmth comes from the cosmic microwave background radiation, the leftover glow of the Big Bang. Space feels empty, yet even in the deepest voids, this radiation fills every cubic centimeter. Though it is invisible to our eyes, radio telescopes detect it as a faint hum. Compared to Earth's environment, space is unimaginably frigid, and any object without heat of its own quickly radiates energy away into the cold. For astronauts or spacecraft, managing this heat loss is a constant engineering challenge. The background temperature is also a cosmic relic, a memory of the universe's fiery beginning stretched into cold microwaves by billions of years of Kumpel. Expansion. Space is both vast and nearly frozen, a silent reminder of the universe's ancient origins. Time passes differently in space than on Earth. Einstein's theory of relativity showed that time is not absolute. In space, time can flow differently depending on speed and gravity. A clock orbiting Earth ticks at a slightly different rate than one on the surface. Near a black hole, time slows dramatically due to its immense gravity. This is not just theory, but measurable fact. Satellites, astronauts, and even planes experience tiny differences in time compared to people on Earth. Though the variations are small, over long periods, they add up. The idea that two people can experience different amounts of time simply because of their position or motion challenges our everyday intuition. It means the universe has no single now. Time is woven into space, flexible and relative, stretching and bending under gravity and speed. Relativity turns time from something rigid into a living dimension that changes depending on where you are. Astronauts aboard the ISS age more slowly. Astronauts living aboard the International Space Station orbit Earth at nearly 28,000 kilometers per hour. Because of this high speed, they experience a tiny effect predicted by relativity: time dilation. Their clocks tick just a little slower compared to those on Earth. After 6 months in orbit, the difference amounts to only milliseconds, but it is real. At the same time, the weaker gravity in orbit makes their clocks run slightly faster than on Earth, partially cancelling the effect. The combined result is that astronauts age very slightly less than people on the ground. While the difference is too small to matter in daily life, it demonstrates the reality of relativity in practice. Over longer journeys, like trips near black holes or speeds approaching light, the effect could become dramatic. For now, astronauts are living proof that even time itself is relative. GPS satellites need relativity to stay accurate. Every time you use GPS, you rely on Einstein's relativity. GPS satellites orbit Earth at high speeds and at higher altitudes where gravity is weaker. Both effects alter their onboard clocks compared to those on Earth. The satellite's clocks tick faster by about 38 microseconds per day. That may sound small, but if uncorrected, GPS positions would drift by kilometers within a single day. Engineers account for both special and general relativity in the system's design, constantly synchronizing the satellites with ground stations. The fact that your phone can tell you where you are within a few meters is thanks to Einstein's theories working behind the scenes. Relativity isn't just an abstract idea about black holes and the cosmos. It's something that makes modern technology possible. Every time GPS guides you, it proves that time truly flows differently in space than on Earth. Black holes can twist space like taffy. The gravity of a spinning black hole does more than pull. It drags space-time itself. This phenomenon, called frame dragging, twists space around the black hole like taffy. Anything nearby, even light, is forced to swirl in the direction of the spin. The region where this occurs is called the ergosphere. Within it, nothing can remain still. Everything is dragged along by the rotating fabric of spacetime. This effect is not just theoretical. Satellites around Earth have measured tiny amounts of frame dragging caused by our own planet's spin. Around black holes, the effect is extreme. It may even allow energy to be extracted from a black hole by objects interacting with the ergosphere. Frame dragging shows that black holes don't just bend space and time, they also spin it, turning space-time into a cosmic whirlpool. The cosmic microwave background is the oldest light in the universe. The faint glow that fills all of space, known as the cosmic microwave background, is the oldest light we can see. It dates back nearly 14 billion years to just 380,000 years after the Big Bang. Before this moment, the universe was a hot fog of particles and radiation that scattered light endlessly. As the universe cooled, atoms formed and light could finally travel freely. That ancient glow still exists today, stretched into microwave wavelengths by cosmic expansion. It is everywhere. No matter where you look in the sky, you see the afterglow of creation. It's not visible to the eye, but radio telescopes detect it as a faint background hum. This relic light provides a snapshot of the infant universe, a frozen picture of its structure, density, and temperature. To look at it is to see as far back as we can, nearly to the dawn of time. It is a faint glow left over from the Big Bang. When astronomers first detected the cosmic microwave background in 1965, they thought it might be interference from pigeons nesting in the telescope. In reality, it was the most important discovery in cosmology, proof of the Big Bang. The glow is unimaginably faint, just a few degrees above absolute zero, but perfectly uniform across the sky with tiny ripples. These ripples are fossils of the earliest fluctuations in matter, the seeds of galaxies. Without this discovery, the Big Bang theory might have remained uncertain. Today, spacecraft like COBE, WMAP, and Planck have mapped the glow with incredible precision, showing its delicate structure. This faint whisper of light tells us about the age, shape, and fate of the universe. It is literally the afterglow of creation, a reminder that even the emptiest corners of space still carry the memory of a fiery beginning. Tiny fluctuations in this glow shaped all the galaxies. The cosmic microwave background is not perfectly smooth. It contains tiny fluctuations in temperature, differences of only a few millionths of a degree. But these minute ripples carried the seeds of all future structure in the universe. Regions slightly denser than average attracted more matter, slowly growing into galaxies, clusters, and cosmic webs. The map of these fluctuations is like a baby picture of the universe, showing where the great cosmic structures would one day grow. Without them, matter would have spread evenly, and no galaxies, stars, or planets would exist. Scientists call this the primordial blueprint of the cosmos. Observing it is like seeing the script of the universe before it unfolded. These faint patterns, frozen in light nearly 14 billion years ago, determined where you, I, and every galaxy would eventually come to be. Earth passes through comet dust every year to make meteor showers. Every year, Earth's orbit carries it through trails of dust left behind by comets. As these tiny grains hit our atmosphere, they burn up in brilliant flashes we see as meteor showers. The Perseids in August and the Geminids in December are among the most famous, dazzling with dozens of meteors each hour at their peak. The particles are often no bigger than sand grains, yet they glow brightly as they streak through the sky at tens of kilometers per second. Some showers come from comets, others from rocky asteroids that shed debris. Each meteor shower is like a cosmic anniversary, marking Earth's yearly return to a familiar trail of dust. Watching them is to witness our planet sweeping through the remnants of ancient celestial travelers, leaving behind glowing streaks of fire in the sky. Meteors heat the air until it glows. When a meteor enters Earth's atmosphere, it does not burn because of friction, as is often said. Instead, the immense speed compresses the air in front of it, heating it to thousands of degrees. This superheated air glows, creating the streak of light we call a shooting star. Most meteors are small, no larger than a pebble, and they vaporize completely high above the ground. Larger ones may survive to become meteorites, delivering pieces of space rock to Earth. The glow of a meteor is brief, but in that instant, you are watching both air and cosmic dust transformed by raw energy. Every meteor is a reminder that Earth constantly sweeps through space, colliding with debris that has been drifting through the solar system for billions of years. A meteor once shattered windows across Russia. In February 2013, a meteor the size of a bus exploded over Chelyabinsk, Russia. The blast released the energy of nearly 500 kilotons of TNT, brighter than the sun for a moment. The shockwave shattered windows across 6 cities and injured over 1,000 people, mostly from flying glass. Yet the object itself was only about 20 meters across. It entered Earth's atmosphere at nearly 60,000 kilometers per hour, breaking apart about 30 kilometers above the ground. Fragments rained down, later recovered by scientists from a frozen lake. Events like this are rare, but not unique. Earth is struck by such objects once every few decades. The Chelyabinsk event was a dramatic reminder that even small space rocks can unleash enormous power, and why astronomers keep careful watch for near-Earth asteroids. The largest impact crater on Earth is hidden in South Africa. 2 billion years ago, an asteroid more than 10 kilometers wide struck what is now South Africa, creating the Vredefort crater. With an original diameter of around 300 kilometers, it is the largest confirmed impact structure on Earth. Over time, erosion and geology have softened its features, but from above, you can still see the ring-shaped patterns left behind. This cataclysmic impact would have shaken the entire planet, vaporizing rock and altering Earth's climate. It is thought to have shaped the geological history of the region, influencing where gold and other minerals were deposited. The Vredefort crater is so old that it predates most complex life on Earth. Studying it helps scientists understand not only our own planet's violent past, but also the potential effects of large impacts that may still threaten Earth's future. Another giant crater lies beneath Antarctica's ice. Beneath kilometers of Antarctic ice, radar surveys have revealed a buried crater more than 200 kilometers across. Scientists believe it was created by a massive asteroid impact tens of millions of years ago. If confirmed, it would be among the largest known impact sites on Earth. Such an event would have had global consequences, throwing dust and debris into the atmosphere, disrupting climate, and possibly affecting the evolution of life. The ice covering it makes study difficult, but satellites and ice-penetrating radar continue to reveal more details. The discovery reminds us that Earth still holds hidden scars, even beneath the remotest and most inaccessible regions. Giant craters are not just relics of the distant past. They are warnings that impacts are part of our planet's ongoing story. Interstellar clouds can be big enough to swallow solar systems. Between the stars lie vast clouds of gas and dust, some stretching dozens of light-years across. These interstellar clouds are so large they could swallow entire solar systems. Despite their size, they are incredibly diffuse, with densities far lower than Earth's best vacuums. Yet over time, gravity can cause them to collapse. birthing new stars and planets. Some glow with light from nearby stars, while others are dark, blocking the light behind them. They are the raw material of the universe, the wombs of future suns. When we look at nebulae like Orion or Eagle, we are seeing the colossal nurseries where countless solar systems will one day form. These clouds are reminders that the emptiness of space is not empty at all, but filled with hidden structures shaping the future of the cosmos. Some clouds of gas stretch for hundreds of light years. The largest interstellar clouds are true giants, spanning hundreds of light years. The Orion Molecular Cloud Complex, visible in the night sky as part of Orion's belt, is more than 300 light-years away, but vast enough to fill the field field of view of telescopes for centuries. These clouds are stitched together by gravity, turbulence, and magnetic fields, creating knots and filaments where stars ignite. Their sheer scale defies imagination. Hundreds of trillions of kilometers across, yet delicate enough that starlight and shockwaves can sculpt them into new shapes. Inside, new stars form while older ones explode, recycling material back into the cloud. These enormous structures are living ecosystems of creation and destruction, reminding us that galaxies themselves are shaped by processes occurring within these sprawling, unseen clouds. Stars are born in violent explosions of collapsing clouds. Star birth is not gentle. It begins when a giant molecular cloud, cold and dark, collapses under its own gravity. Turbulence and shockwaves, often triggered by nearby supernova, squeeze regions until they become dense enough to ignite nuclear fusion. As the cloud collapses, material spirals inward, heating up, glowing brighter, and eventually forming a newborn star surrounded by a disk of gas and dust. Within this disk, planets may one day form. The violence of the collapse often drives out jets of material, shooting across light years at hundreds of kilometers per second. What looks like a serene, twinkling star in the night sky is the product of immense chaos. Every star we see, including our Sun, was once born from the collapse of such a cloud, forged in a cosmic storm that turned darkness into light. They lived fast and died young in giant explosions. The first stars in the universe were monsters, hundreds of times more massive than our Sun. Fueled by their enormous mass, they burned through their nuclear fuel in just a few million years, a blink compared to the Sun's expected lifespan of 10 billion years. These titanic stars lived fast and died young, collapsing and exploding as supernova that scattered heavy elements into space. Without them, the universe would be barren, filled only with hydrogen and helium. Their explosive deaths seeded the cosmos with the building blocks for planets, oceans, and life itself. Astronomers cannot see these first stars directly, but their fingerprints linger in ancient gas clouds and the chemical composition of old stars. They were the fireworks that lit up the universe after the Big Bang, setting the stage for everything that would follow. The first gravitational wave detection came from merging black holes. In September 2015, scientists detected a signal so faint it stretched space by less than a fraction of a proton's width. It was the first direct detection of gravitational waves, ripples in spacetime predicted by Einstein a century earlier. The source, two black holes, each about 30 times the mass of the Sun, spiraling together and colliding over 1 billion light-years away. The collision released more energy in an instant than all the stars in the observable universe combined, though most of it was carried away as invisible gravitational RLN. Waves. The discovery confirmed Einstein's prediction and opened an entirely new way of observing the universe. With gravitational waves, astronomers can now listen to cosmic collisions, not just see them. It was a moment that changed astronomy forever, revealing a new cosmic messenger whispering through the fabric of spacetime. The fate of the cosmos may depend on dark energy. The universe is not just expanding, it's expanding faster and faster. This acceleration is driven by a mysterious force called dark energy, which makes up nearly 70% of the cosmos. No one knows exactly what it is, but its influence may decide the ultimate fate of everything. If dark energy remains constant, galaxies will drift endlessly apart, leaving a cold, dark universe. If it grows stronger, it could eventually rip apart galaxies, stars, and even atoms in a cataclysm called the Big Rip. If it weakens, gravity could one day slow expansion, leading to a big crunch where the universe collapses back into itself. Our entire cosmic future, trillions of years into the unknown, rests on the properties of this invisible energy we barely understand. Dark energy is perhaps the greatest mystery in science, a shadow force shaping destiny itself. Dark energy pushes the universe apart. When astronomers studied distant supernova in the 1990s, they expected to see that the expansion of the universe was slowing down under gravity's pull. Instead, they discovered the opposite. Expansion was speeding up. Something unseen was pushing galaxies away from each other, stretching the fabric of space itself. This force was named dark energy. Unlike matter, it doesn't clump or collapse. It seems to be an intrinsic property of space, growing stronger as the universe expands. Today, dark energy drives the accelerating expansion, with galaxies rushing away faster the farther they are. In billions of years, distant galaxies will vanish from sight, carried beyond the cosmic horizon by this relentless push. Though invisible and poorly understood, dark energy is the engine behind the universe's expansion, ensuring that space itself is not static, but restless, ever growing. We don't know what dark matter really is. Dark matter makes up about 85% of all matter in the universe, yet no one knows what it is. It does not emit, absorb, or reflect light, making it invisible to telescopes. We only know it exists because of its gravitational effects. Galaxies rotate too quickly to hold together without it, and galaxy clusters bend light more than visible matter alone could account for. Physicists suspect dark matter might be made of undiscovered particles, perhaps whimper, weakly interacting massive particles or actions. Others suggest it could be something stranger, like primordial black holes. Despite decades of searching with sensitive detectors deep underground and in space, no dark matter particle has been directly observed. It is one of the greatest mysteries in modern physics, an unseen framework holding the universe together. Without it, galaxies would fly apart, and we would not exist. Galaxies move faster than they should because of dark matter. In the 1970s, astronomer Vera Rubin made a discovery that changed our view of the cosmos. She studied how fast stars orbit the centers of galaxies. According to Newton's laws, stars farther from the center should orbit more slowly, just as planets farther from the sun move more slowly. But Rubin found that stars at the edges of galaxies move just as fast as those near the center. Something unseen was providing extra gravity to hold galaxies together. This was the clearest evidence for dark matter. Without it, galaxies would spin themselves apart. Today, we see its signature everywhere, in the way galaxies cluster, in the bending of light from distant objects, and in the cosmic web of structure. Galaxies are not just made of stars and gas. They sit within vast invisible halos of dark matter that shape the universe. Dark matter could form its own stars. Some scientists speculate that dark matter may not just sit invisibly in halos, but could clump together to form structures of its own. In theory, If dark matter particles can interact in certain ways, they might form dark stars, objects powered not by nuclear fusion, but by the annihilation of dark matter particles. These exotic stars would emit little to no visible light, glowing instead in forms of radiation we cannot easily detect. If they exist, they could have formed in the early universe, growing to enormous sizes before collapsing. Dark stars remain hypothetical, but the idea pushes us to imagine a cosmos richer and stranger than we can see. Somewhere out there, entire structures could exist in the dark, unseen but real, hidden alongside the familiar galaxies of ordinary matter. Or it could fade away and leave the universe frozen. Another possibility is that dark matter may not last forever. Some theories suggest that dark matter particles are unstable, slowly decaying into other particles over billions of years. If so, the invisible scaffolding that holds galaxies together would gradually disappear. Stars would drift apart, galaxies would dissolve, and the universe would become more and more diffuse. Combined with the relentless push of dark energy, the cosmos could eventually become a vast, frozen expanse, with no stars, no galaxies, and no warmth. This scenario is speculative, but it reminds us that even the eternal structures of the universe may not be permanent. Everything we see is balanced on the behavior of forces and particles we still do not fully understand. Most of its history hasn't happened yet. The universe is about 13.8 billion years old, and that is just the beginning of its story. If dark energy continues to drive expansion, the cosmos will last for trillions upon trillions of years, far longer than its current age. Most stars that will ever exist have not yet been born. Most galaxies have not yet finished their journeys. The vast majority of the universe's history still lies ahead. In the distant future, new stars will shine, new planets may form, and entirely new possibilities for life could arise. Eventually, stars will fade, black holes will evaporate, and the universe will enter an age of darkness. But even then, the cosmos will persist. When we look at the stars tonight, we are not just seeing the past, we are standing near the very beginning of a story that is only just unfolding. The universe is nearly 14 billion years old. Astronomers measure the age of the universe by looking at its oldest light, the cosmic microwave background. This faint glow is a fossil left behind from when the universe was just 380,000 years old. By mapping tiny fluctuations in this ancient light, scientists can calculate how long the cosmos has been expanding. The answer: about 13.8 billion years. This age lines up with the oldest known stars and star clusters, which are nearly as old themselves. To put it in perspective, Earth and our solar system formed only 4.5 billion years ago, so we've been here for less than 1/3 of cosmic history. The universe is ancient, beyond imagination, yet still young compared to what lies ahead. Most of its life has not yet unfolded, making us early witnesses in a story that will continue for trillions of years. Interstellar magnetic fields thread through the entire cosmos. Space may look empty, but it is woven with invisible threads of magnetism. Across galaxies, weak magnetic fields stretch for thousands of light years, guiding charged particles and shaping the structure of interstellar clouds. These cosmic fields are much weaker than a fridge magnet, but on vast scales they influence how stars form, how cosmic rays travel, and how galaxies evolve. Astronomers map them using polarized light and radio waves, which reveal the alignment of dust grains and electrons spiraling along magnetic lines. The origin of these fields is still uncertain. They may have been seeded in the early universe and then amplified by the motion of plasma in galaxies. Without them, the universe would look very different. as these unseen forces subtly sculpt the behavior of gas and matter across the cosmic web. They are the hidden framework beneath the starlit sky. Cosmic rays rain down on Earth from deep space. Every second, invisible particles called cosmic rays bombard Earth from space. They travel at nearly the speed of light, slamming into our atmosphere with energies far beyond anything human-made accelerators can achieve. Most cosmic rays come from exploding stars, their shockwaves hurling protons and atomic nuclei across the galaxy. A few may originate from even stranger sources, like active black holes or distant galaxies. When they hit the atmosphere, they create showers of secondary particles that cascade toward the ground, some passing right through our bodies. Fortunately, Earth's magnetic field and atmosphere shield us from their most dangerous effects. Still, these cosmic bullets leave subtle imprints, from influencing cloud formation to posing radiation risks to astronauts. Cosmic rays are a reminder that space is not a silent void, but a restless ocean, constantly sending energetic messengers crashing into our world. Some galaxies are older than the universe's first stars. This sounds like a paradox. How can galaxies be older than the stars they contain? The answer lies in how we measure age. Some galaxies we observe today appear to have formed surprisingly early, just a few 100 million years after the Big Bang. Inside them, astronomers have found stars rich in heavy elements, the products of earlier generations of stars. This suggests that star formation may have begun even earlier than we thought, reshaping our understanding of cosmic history. The James Webb Space Telescope has revealed galaxies so ancient that they challenge models of how quickly matter clumped together. In some cases, their stars seem to have lived and died before galaxies should have existed at all. These discoveries push astronomy to the edge, forcing scientists to rethink how structure emerged so rapidly after the universe's birth. The Whirlpool Galaxy is colliding with its neighbor right now. The Whirlpool Galaxy, also known as M51, is one of the most photographed galaxies in the night sky, a stunning spiral with sweeping arms. But it isn't alone. Right now, it is colliding with a smaller companion galaxy, NGC 5195. The encounter is pulling on the Whirlpool's arms, triggering waves of star formation and giving the galaxy its striking appearance. Over millions of years, the two galaxies will continue their gravitational dance, pulling at each other until they merge into a single, larger system. Such collisions are common in the universe and play a key role in shaping galaxies. Even though it looks violent, the stars themselves rarely collide, since space within galaxies is mostly empty. Instead, the gas and dust crash together, lighting up with bursts of new stars. The Whirlpool is a cosmic snapshot of galaxies in mid-embrace. We can see galaxies as they were billions of years ago. When you look at a galaxy in the night sky, you're not seeing it as it is now. You're seeing it as it was when the light left it. For nearby galaxies, that may be just a few million years ago. For the most distant galaxies we can see, their light has traveled for over 13 billion years. That means we are observing them as they existed not long after the Big Bang. Telescopes like Hubble and James Webb act like time machines, capturing light that has crossed almost the entire history of the cosmos. In some images, we see galaxies still forming, clumping together in ways they no longer do today. Looking into deep space is literally looking back in time, giving astronomers a chance to study the universe's childhood and piece together how it grew into the vast Gubal. Structure we see today. Rogue planets drift through space without suns. Not all planets orbit stars. Some are cosmic wanderers, rogue planets, drifting alone through the darkness of space. These worlds may have been born around a star and later flung away by gravitational chaos, or they may have formed on their own from collapsing clouds of gas. Without sunlight, they are frozen and dark, though some may still glow faintly with leftover heat from their birth. Astronomers estimate there could be as many rogue planets in the Milky Way as there are stars, meaning billions of lonely worlds roam the galaxy. Some may even have moons, atmospheres, or underground oceans warmed by internal heat. Though they seem inhospitable, rogue planets remind us that not all worlds fit the pattern of neat solar systems. They are the castaways of the cosmos, carrying secrets of planetary formation into the interstellar night. There may be more planets than stars in the universe. For centuries, people wondered if other worlds existed beyond our solar system. Today, thanks to space telescopes like Kepler, we know the answer is yes, and the numbers are staggering. Nearly every star seems to host at least one planet, and many have entire systems. Some planets orbit close and hot, others far and frozen, and some lie in the habitable zone where liquid water could exist. Extrapolating from what we've found, astronomers believe there are likely more planets than stars in the Milky Way alone, perhaps hundreds of billions. Across the universe, that number could climb into the trillions upon trillions. Planets are not rare. They are the cosmic norm. For every star you see in the night sky, imagine at least one world circling it. Some barren, some strange, and perhaps some alive. Asteroids hold clues to the solar system's birth. Asteroids are often seen as mere space rocks, but they are more like ancient time capsules. Most formed over 4.5 billion years ago, during the chaotic birth of the solar system. Unlike planets, which melted and changed, many asteroids have remained unchanged, preserving the raw ingredients of our cosmic origins. By studying them, scientists can learn what the early solar system was made of. Some asteroids even contain water and organic molecules, hinting at how the building blocks of life may have been delivered to Earth. Space missions like OSIRIS-REx and Hayabusa have brought back samples, giving us direct evidence of these primordial materials. In their craters, cracks, and chemistry, asteroids carry a frozen record of the solar system's first days, reminders of the storm of dust and fire that shaped the worlds we know today. Earth's atmosphere shields us from most meteors. Every day, Earth is bombarded with tons of material from space. Most of it is tiny, sand-sized grains of dust that burn up harmlessly in the atmosphere, creating fleeting streaks of light we call meteors. The atmosphere acts as a shield, absorbing the energy of these incoming fragments before they can reach the ground. Without it, Earth would look like the Moon, scarred by countless impact craters. Larger objects do sometimes survive the plunge, but they are rare compared to the millions of meteors that vanish in fiery trails each night. This shield of air makes our planet unusually safe, protecting us from a constant cosmic rain. The next time you see a shooting star, you're watching the atmosphere at work, a fiery defense system that turns dangerous rocks into brief sparks of beauty across the sky. Some theories suggest the universe has no edge. It's natural to imagine the universe as a giant bubble with some kind of outer boundary. But according to Einstein's general relativity, the universe may have no edge at all. Instead, space could be curved like the surface of a sphere, finite in volume but without a border. If you traveled forever in one direction, you might eventually loop back to where you started, never hitting a wall. Other models suggest space is truly infinite, stretching endlessly in all directions. The mystery remains unsolved because we can only observe the observable universe, the portion from which light has had time to reach us. What lies beyond may be larger, stranger, and perhaps endless. The possibility of a boundless cosmos challenges our intuition, a universe without edges or limits, stretching into forever, leaving us adrift in a space with no boundary at all. Others suggest it may be infinite, but repeating. Another idea about the universe's shape is that it could be infinite, but not unique. In this model, space might repeat itself like a cosmic video game map that wraps around. Because matter is arranged in only so many ways, an infinite cosmos would eventually recycle patterns. That means far beyond our observable universe, there could be regions of space almost identical to ours, galaxies, stars, even versions of Earth. The distances are so vast we could never reach them, but the math makes the idea hard to dismiss. Some cosmologists suggest that if you travel far enough in a straight line, you might encounter a copy of the Milky Way, or even a copy of yourself. It sounds like science fiction, yet it's a natural consequence of infinity. An endless universe may not only go on forever, but repeat itself endlessly too. Space is not completely empty. When people picture space, they often imagine a perfect vacuum, but even the emptiest parts of the cosmos contain matter. A single cubic meter of empty space usually holds a few hydrogen atoms, the most common element in the universe. In denser regions like interstellar clouds, that number can climb into the thousands. On top of that, space is filled with particles, radiation, magnetic fields, and the faint glow of the cosmic microwave background. Even dark matter and dark energy, which we cannot directly see, may pervade every cubic meter. Truly empty space, a perfect void, may not exist anywhere. Even the vacuum of space-time itself isn't empty, since quantum physics tells us that particles constantly flicker into and out of existence. What we call nothing is actually a restless, invisible sea of energy and matter. Space, it turns out, is never truly empty. A single cubic meter of space can contain hundreds of particles. In the vast emptiness between galaxies, space still contains atoms. Astronomers have found that even the loneliest cubic meter of intergalactic space may hold hundreds of stray particles. That doesn't sound like much, but across billions of light years, it adds up. These sparse particles are remnants of the Big Bang, stretched thin by the expansion of the universe. They quietly drift, carrying with them information about the early cosmos. Telescopes can detect their faint signature when light from distant galaxies passes through them, revealing how matter is distributed across space. In fact, the discovery of these particles helped confirm the Big Bang model. What feels like an infinite void is actually filled with ghostly matter, whispering reminders of creation. Even in the emptiest reaches, the universe is never truly still. Every cubic meter holds the faint afterglow of cosmic history. The universe could one day spawn new universes. Some cosmologists believe our universe may not be the only one. In theories of eternal inflation, new universes constantly bud off from quantum fluctuations, forming a multiverse. Black holes might also play a role. Some models suggest that the core of a black hole could collapse and rebound into a new expanding universe hidden from us, beyond the event horizon. If so, our own universe might have been born from a black hole in another cosmos. These ideas are speculative, but they're taken seriously because they naturally emerge from equations describing cosmic inflation and quantum mechanics. If true, it would mean the Big Bang was not a unique beginning, but part of an endless cycle of births. Each universe could have its own laws of physics, some hostile, some fertile. Ours might just be one bubble in an infinite cosmic sea of realities. You are a way for the cosmos to know itself. Carl Sagan once said, "We are a way for the cosmos to know itself." This is more than poetry. It's a scientific truth. The atoms that make up your body were forged in stars, scattered by supernova, and recycled into new worlds. Through you, those atoms have become conscious, capable of reflecting on their own origins. When you look up at the night sky, you are literally the universe examining itself, aware of its own existence. This connection means our curiosity is not separate from nature, but an expression of it. Conscious life may be rare, but where it exists, the universe gains eyes, ears, and thought. Every observation, every discovery, is the cosmos learning a little more about its own story. In you, in us, the universe has awakened to itself, a fleeting spark of self-awareness in the vast dark. The Sun makes up more than 99% of the solar system's mass. Our solar system is dominated by the Sun in more ways than one. It doesn't just provide light and heat, it also contains over 99% of the system's total mass. That means everything else, planets, moons, asteroids, comets, together, make up less than 1%. Jupiter, the largest planet, is massive in human terms, but tiny compared to the Sun. This immense gravity well keeps the planets locked in orbit, shapes the paths of comets, and even influences interstellar visitors passing nearby. Without the Sun's overwhelming presence, the solar system would scatter into chaos. Its mass also fuels the nuclear fusion at its core, converting hydrogen into helium and releasing the energy that sustains life on Earth. The Sun is not just the center of the solar system, it is the system. Everything else mere crumbs around its blazing bulk. Some stars can outshine entire galaxies. While most stars are modest in brightness, a rare class known as hypergiants can erupt in explosions so powerful they briefly rival entire galaxies. In these moments, one star can shine with the light of hundreds of billions of stars combined. Events like supernova and gamma-ray bursts release unimaginable energy, visible across the universe. Some of these stellar beacons are so bright that ancient astronomers recorded them appearing suddenly in the night sky, visible even in daylight. Today, telescopes capture these outbursts in exquisite detail, revealing the violent deaths of massive stars. These explosions scatter heavy elements into space, seeding future generations of stars and planets. When a single star briefly outshines a galaxy, it's not just a display of power, it's a cosmic act of creation, forging the raw materials for life in the ashes. Of destruction. Supermassive black holes sit at the centers of most galaxies. At the heart of nearly every large galaxy lurks a monster. A supermassive black hole millions or even billions of times the mass of the Sun. Our own Milky Way's central black hole, Sagittarius A*, is relatively quiet, but in other galaxies, these giants blaze with energy as they consume craft, gas, and stars. They shape their galaxies by launching powerful jets of radiation and winds that can blow away star-forming material. Astonishingly, the growth of galaxies and their central black holes appear linked, suggesting they evolved together. We can't see black holes directly, but their presence is undeniable. In the orbits of stars near the core, in the glow of falling matter, in the ripples of spacetime they send across the cosmos. They are the hidden engines of galaxies, vast gravitational hearts beating at the center of cosmic cities. Gravitational waves were predicted a century before we found them. In 1916, Albert Einstein predicted that massive objects in motion should send ripples through space-time, like waves spreading across a pond. He doubted they would ever be detected, since the effect is incredibly subtle. For decades, they remained a mathematical curiosity. Then, in 2015, the LIGO Observatory made history, by detecting gravitational waves from two merging black holes over 1 billion light years away. The signal was unimaginably small, a distortion less than the width of a proton, yet it confirmed one of Einstein's boldest ideas. Since then, gravitational wave astronomy has opened a new window on the universe, allowing us to hear collisions of black holes and neutron stars. These ripples carry information no light can provide, revealing events otherwise hidden in darkness. A century after prediction, Einstein's vision became reality, and spacetime itself became part of our cosmic conversation. As our journey through space comes to a close, it's worth pausing with the scale of what we've drifted through together. We've wandered across distances so vast that light itself struggles to keep up. We've brushed past stars that live fast and vanish young, and others that collapse into forms so dense they bend time around them. We've watched galaxies move, collide, and reshape the sky, and felt how much of the universe lies forever beyond reach, not hidden, just carried away by the slow bar, stretching of space itself. Taken together, these ideas form a picture that is both immense and humbling. Space is not a static scene. It is a long, unfolding story, filled with motion, change, and cycles far older than Earth. And yet, here you are, listening from a small world, connected to all of it by light, gravity, and time. Now, there's nothing more you need to hold on to. Let the images soften. Let the vastness fade into a calm sense of perspective. Your breathing can slow. Your shoulders can rest. The universe will keep expanding. Stars will keep burning and fading. And you don't need to follow any of it right now. If you've enjoyed this journey, you might take a moment to support the channel by liking or subscribing, or leaving a comment if a thought lingers. And if you're still awake, there's another video waiting on your screen, ready to carry you a little further into wonder. Otherwise, allow your attention to drift inward. Let the day loosen its grip. Let the night take over gently, without effort or expectation. Sleep well, and good night.